AA. AA. Welcome to the first international workshop of high-resolution thermal Earth observation. My name is Ana Isabel Bolea Lamagnac. I'm the LSTM project manager on ESA site. The mission will be presented later by one of my peers. And I'm very happy to chair this first session of the international workshop together with Michel. Michel, maybe you want to introduce yourself?
Yeah, good morning, everyone. I'm Michel Massard from the European Commission, and I have the pleasure to co-chair this first session with Anna. Of course, this thermal workshop is very important for the European Commission and for Copernicus, as we have, as you know, a mission which will fly at the end of this decade. So it's a good opportunity for us to frame this future LSTM mission in the international context.
Thank you, Michel. So in order to provide you with a deeper context of this workshop and to give you all the welcome to this international workshop, I have the pleasure to introduce you to Benjamin Kutz. Benjamin is the head of the Sustainable Office Sustainable Initiative Office in ESA. He's based in Esrin, and we are very happy to have him as the mission scientist for the LSTM. And he's been the key organizer of this workshop. So thank you, Ben, and please, the floor is yours.
Thank you, Anna, to introduce us to this first opening session of the workshop. I have the pleasure to welcome you here in Esrin, and on behalf of Rune Floberhagen, my head of, head of the Science and Application and Climate Department, who is unfortunately not able to join us today because he has another obligations, but he sends his warm regards to all of you, and hopes that we can, build on all the different inputs we're getting here in this conference, and he wants to have the feedback from all of us coming out of this conference. I also would like to welcome you on behalf of the co-hosts of this conference that has been hosted, organized, and we hosted here, but co-organized by 5 different space agencies, because there is a very high international dynamic in the moment, investing into thermal Earth observation. So there's NASA, JPL, but NASA is as a space agency, CNES, ISRO, ASI, and ESA here represented, because there are big missions coming up, and we will see that in the opening session in the next few minutes, how that is evolving, and I think that will be exciting for all of us. So just one slide, because you're here in Esrin. This is the headquarters of Earth observation within ESA. We built here the Earth observation systems together with the European Commission and global partners. We welcome you all here to bring the different expertise together and make out of this data the right intelligence, I would like to say, to respond to scientific and social challenges. Just one example, because we're really talking here about the land surface temperature. Sentinel-3 is already, as part of the Copernicus program, taking land surface temperature measurements operationally, globally, in 1 kilometer resolution, and you see already very much why we need that kind of information. Last year we had heat waves quite impacting the whole continent, and not only Europe, but when you see here temperatures in France up to 50 degrees, but actually also in UK 45 degrees, Spain even hotter, causing wildfires in France, but also droughts in Spain. So I think there's a lot of reason why we need to have this type of information. And if we go to the next point, how that is then actually happening on the global scale. So Europe is one part, but India, also other parts in the globe, is very much affected or even more affected in these type of changes in our climate. And with that, I go to the next point. I think we all hear about taking the temperature of the Earth, and I think that is making it very sensible to link that to climate warming. And these climate warming stripes you all have on your lanyard, and we put it also on our website as one of the drivers of these missions. And in the last assessment report from IPCC, just published a few weeks ago, you see this kind of graphic showing what has already happened in terms of changes relatively to the 1850 to 1900 reference period. So the changes is represented here in the forecast, and how that is actually impacts the different generations. Some of us will see only the part of it, but I mean, if people are born nowadays, they really will have the full impact on it, and that we should keep in mind. If that's then broken down into into the different impacts, you see here that one of the points is water availability in food production, and that is very much, for example, the objective of LSTM. That has impacts not only on crop production but also on livestock and fishery, but then there's also direct impact on our health. All of that has been scientifically studied under IPCC reports and quantified, and in terms of forecasts also giving a probability to it. And finally, in terms of ecosystems and biodiversity. We see here a global, let's say, timeline of temperature, but we want to really bring this down to manageable entities, geospatial units where we can make impact. And I don't have to preach to you that this is why we need Earth observation, to make that available to decision makers and make out of that the right conclusions. And here we basically have the current status. We have Landsat already since quite some decades taking thermal information. EcoStress is amazing prototype who's leading the way, and we will see many examples, I think, during this conference how to make this work. But we have now in the pipeline Trishna from CNES and ISRO. We have SPG, the thermal part, NASA and ASI here from Italy. And then from the European side, we have from ESA and European Commission proposed the LSTM missions. All three of them will provide quite significant amount of data to respond to these challenges I just outlined. And I think we are in a very strong position as a community to respond to that. Having said that, there's also new space type of activities, and we have a dedicated session on that this afternoon, where we think we can all learn and work together how to make these different type of space approaches work together and create synergies, and we look forward to that as well. So with that, I think I just wanted to highlight that we had enormous feedback from you as a community, unexpected in a sense. We got 164 abstracts, 300 participants. There will be people online on top because we had to close 2 weeks ago the registration, and so we're streaming that as well. You come from 39 countries, and we will have altogether 11 missions, 7 of them new space. So I think we have a lot of things to share and to discuss. I really look forward to also the feedback coming back to us. We really want to use this workshop as a conversation and learn from you on what we can do as Space Agency for you in the coming years. With that, I would like to welcome everybody again and hand over to Anna, and then we will go to the more objectives. Thank you.
Thanks a lot, Benjamin, for setting the scene of this workshop. So now we proceed with Giuseppe Ottavianelli, I hope I have pronounced that correctly, who is the head of the application section of Earth observation in ESA. and he's going to further go in detail into the workshop objectives to help us understand why we are here these 3 days. So please, Giuseppe, the floor is yours.
Thank you, Anna. Thank you, Michelle, for the welcoming. And again, it's really a great pleasure to see this room completely filled up. And as Ben said, we had to open to online streaming as well to make sure that we allowed a further audience as well to benefit from today's and the discussions of the workshop. So I like to always to put things into context. So by starting showing some more higher resolution data, and here it's EcoStress Hub, so courtesy NASA, thank you, Simon. We're looking at some images from a few years ago, but all taken around the same period. And we can quickly see immediately the streams of the rivers, the green patches around the cities. Here you have Rome, you have Madrid, you have the border across Switzerland and France, across Geneva. And clearly you see the gradients in temperature of LST. Please note the difference as well of scale, just to show these gradients and to highlight this. And the same applies if you look at evapotranspiration. So clearly we see immediately how forests and water bodies have an immediate impact on evapotranspiration, and clearly such data would allow seeing patches of water-stressed areas and water-sufficient areas in the different areas. And here it's northern of Italy, again, in the same time period. This immediately shows the great potentials. And as Beth said, we're not here to preach, but again, to reinforce this message of how high resolution in terms of space, but it's also in time revisit, will be absolutely critical to respond and prepare ourselves and adapt ourselves to future heat waves, to future drought conditions. We are seeing in Europe and across the world record temperatures in the various seasons. And in 2022, as shown by Ben, a third of Europe was put into a warning or alert status by the different environmental agencies, and this is matching as well the fact that we have severe precipitation deficits in many areas of the world, and together these two effects bring very critical elements such as fires raging across the different areas of the world. We have seen also in northern latitudes in Europe how this was very critical last year. We're seeing reduced yields forecasts as well, especially in Europe. We are seeing almost 15% of major cereals. This is even linked to drinkable water supplies. And in about 100 municipalities in France last year, drinkable water had to be supplied by trucks. So it's something that is having a real impact on everyday lives and a real impact on operations and logistics. In terms of operations, not to be forgotten that even from the energy suppliers, there was an example, again, last year in France, where a couple of nuclear power supplies had to be reduced in terms of energy production because the cooling systems were not as effective as usual due to the higher temperature of the water in the rivers. And of course, actual deaths. The graph here on the top right is showing deaths in the UK and Wales, in England and Wales, and the strong higher of about 6% with respect in correlated time of heat waves. Of course, we should not forget that the more data we have, the better models we can bring as well in future predictive activities. And of course, as well, if you think about all the efforts that we have in front of us with the digital twin Earths, modeling of the Earth, additional data with higher frequency will certainly bring this higher capacity that we have at hand. Often we are seeing these striped figures. We have it on our badge. But I also want to show something that came out also recently with the same illustrative effort of showing that indeed, an increase of LST is one of the key drivers and impact factors to biodiversity and biodiversity loss. So the main work objectives. Today and in the couple upcoming days, we are here to really strengthen the international collaborations and coordination efforts that we have across the space segment, but also in the ground segment activities. And these are also including the calibration and validation efforts that we will have to put in place, finding synergies and bringing together different know-hows and different resources that we have across the various space agencies, and also with regards to product definition and harmonization, to facilitate the downstream utilization that the larger community will have, and bringing the data towards the end users in an easier way, and bringing new knowledge and information. Of course, we're here to share the various updates on the latest results from projects and activities from the community. And we hope that the setup of the program will allow us to have the full interchange of, let's say, thoughts and discussions during the sessions, but also during the coffee breaks, to make sure we have these knowledge-sharing activities during the event. And finally, we are here absolutely to make clear recommendations to identify high-priority topics for future R&D activities that will have to be implemented. And make an example of what ESA does. We have a dedicated full program, the Future EO program, within which we will build roadmaps of activities with respect to science, applications, industry growth, also digital innovation and tools that are needed to allow the data exploitation, looking at disruptive technologies, and also a new element in the program, which is the Sentinel user preparation activity. Let me spend a few words on this. The SUP initiative, it's an ESA initiative funded by the ESA member states, but in close collaborative synergy with the EC. We have responded to a number of recommendations that industry and also end users have highlighted and strengthened in the last few years, to make sure that we put in place a preparatory program that will allow both the capacity building in the value-adding entities, whether academia or value-adding companies, and also downstream activities merging not only EO data. So we have the capacity building and also the awareness of the end users that new information, new information products and knowledge will be derived by all these upcoming missions. And this effort takes time. It's not something we can anticipate just in 6 months or even a couple of years. It takes time to build the framework. It takes time to bring the community up to speed. And in a way, that readiness level is something really to be anticipated, so that on the one side, we maximize return on investment, and on the other side, we are ready on day one at the end of the commissioning phase of each of these missions. So we will be launching a number of what we call enabling actions on applications of fundamental research in terms of bringing together the different data sets and also new innovative methods with a multi-mission approach. And of course, one of the core and common activity that we'll have to do is to bring representative data sets to the community to make sure that new applications and new science will be pioneered and will be explored in the coming years. Just a couple of examples, but again, I don't want to go through all of this, spanning from agriculture, and again, with a multi-mission approach, not only looking at a single mission, so it not only will be LSTM by itself, but bringing together various assets from space. And this, agriculture, ecosystem and biodiversity monitoring, soil management, from forest management, cities, as we've seen before, critical infrastructure, mining, and so on. So this is a big effort that ESA will bring forward in the coming years. Now, in front of us, we have a very rich 2.5-day program. If you're not done so yet, please do upload your presentations here in the control room that we have at the back of the room. The ESA conference support team at the registration desk will be there as well to support you on specific logistics that you may have. For example, if you need to book a taxi in the coming days and so on. Also, in terms of exit, there are only those exit doors that can be used and not the other ones on your right, because there are scaffoldings outside, and so please do only use the ones on the left. Finally, lunch, further logistics. We have to be at lunch at 1:30, not early than that, due to the other people working at ESRIN, and we have arranged that so that we will be efficient in the short break that we will have for lunch to accommodate the 300 people on site. There will be a group photo that will be taken at the first coffee break, so don't disappear into coffee. Coffee and poster area is all outside in the tent, so here. So make sure you'll be here at the first group photo. And finally, I want to thank absolutely the various teams. Oh, yes, one key word that I want to stress again is to make the best of the discussion recommendation sessions. So this is where we can really extract and distill your inputs that will drive the roadmap of future activities, future R&D investments that ESA will do, but also the other space agencies will do. As I was saying, I want to thank the full team, of course, the organizing committee, the scientific committee, the session chairs that will help us in run and keeping the presenters strict to your schedule, and the on-site team. We have Sabrina, Ulla, Irene, Riccardo, and the many others, Fabrizio, that help us to make this happening. So thank you all very much to be here today.
Thank you, Giuseppe. So we will have now a keynote speech. Agriculture is, of course, a very important application of thermal data. And we have the chance to have in Rome the Food and Agriculture Organization. And so I will give the floor to Livia Peiser, who is a project officer at FAO. She's working on land and water division, and specifically on monitoring water productivity, but I understand that it will go beyond, your speech will go beyond the water productivity. So the floor is yours.
Thank you. Good morning, everybody. I'm Livia Peiser. I work in the Land and Water Division in FAO, and particularly in the Water Data and Information System team. And I will be illustrating why thermal data is important for us. And through that, I hope I will convey my gratitude to you, to this community of data scientists and Earth observation experts that make it all possible, so that really make it possible for a UN agency like FAO to use very sophisticated and complex data and transform it to critical knowledge and information, so that with that we can support our member countries. If you think about it, that is really remarkable. So when Benjamin asked us to speak here, we immediately, of course, focused our intervention on water, on evapotranspiration in particular. That's what we do, but that's also maybe the single most important application of thermal data that we use at FAO. But there's a lot more, and we've seen that already mentioned in the previous presentations. And luckily, in FAO, we now have a tool, a geospatial platform, that puts together, that combines all the geospatial work that is being done at FAO. So that made my work easier in terms of trying to track different applications of thermal data in FAO. And it was very good to see that there's so many, out of the different topics that are represented in our catalog, there's so many that most of them, I would say, are used in one way or another thermal data, starting with monitoring crops and vegetation. This is the Agricultural Stress Index. It's a long-term drought monitoring tool that uses land surface temperature in the index. There's applications that use wildfires to monitor biomass impact on biomass availability for livestock, but there's many more applications that could be designed together with you for livestock, we think. There's, of course, for climate, we'll look at anomalies of land surface temperature, for forestry fires, and then food security and fishery. I haven't found images, but I know that there's colleagues that use thermal data for monitoring, for example, the health of water bodies and fishing areas. So there's a lot of topics and areas in which FAO works that benefit from thermal data, and there's a lot more that we can do together. But focusing on water, indeed, that's where I work, but that's also where we mostly use thermal data for monitoring evapotranspiration and soil moisture and water productivity. And the reason why we heard some of these numbers before, of course, but I think it's important for us as FAO to set a little bit the background against which we work. And we have, FAO produces these flagship publications, so the status of food and agriculture, status of food insecurity, and so on, that help us framing a little bit the context where we work. And unfortunately, we see growing numbers, to start with, growing numbers of insecure people in the world. We're now at about 828 million people that suffer from hunger, and this number is increasing, mostly because of conflicts and climate change. There's also 3.2 billion people that live in agricultural areas with very high water shortage or scarcity. And we also need to produce more food for a growing population, but at the same time we saw that the current patterns of intensification are not proven sustainable. And one of these indicators is also that is relevant here is that if you look at the last 20 years, 85% of crop increase was irrigated cropland increase. So that's a very important sign of where the world is going and what challenges we need to face. And if you, of course, put it in what Benjamin was just showing, the fact that the latest IPCC report puts water really at the center of the climate crisis, and it's we can now see that with every with every degree of increased global warming, we can expect additional water-related risk. That very clearly shows that we need to be able to produce more food with less water and measuring water use in agriculture. But the countries we work with, and in general, it's very difficult to monitor water use in agriculture, particularly if you have instruments like those that you see in this picture, but even with more sophisticated instruments, to be able to monitor that over large areas and time is not feasible unless you use remote sensing, and that helps us doing it in cost-effective ways. So that's why FAO in the last 7-8 years or so has been putting efforts, and thanks to the support of the government of the Netherlands, but also several other donors, and we started producing the VAPOR database and portal that I hope is at least familiar to some of you. And that's through that, in collaboration with IHE Delft, IMI, and ELIF, we produce data on evapotranspiration and biomass production, which combined help us monitor land and water productivity at different scales and in different areas of the world. So we currently publish the data for the whole of Africa and the Near East at 100-meter resolution and 250-meter resolution, and we will grow globally before the summer. And in selected areas that you see here in these orange spots, we also produce data at 30 and now 20-meter resolution. And we make them publicly available on the FAO website and accessible through APIs, which makes it usable for many different types of users and users, depending on the scale and on the needs. So we there's a catalog of applications. I just selected one or two examples to show that the data that we produce is used at the field level by farmers to improve their water, the water application, and at irrigation scheme level and water use association or basin authorities to better monitor the water use and irrigation performance, but also, and that's where FAO is also mandated for monitoring SDG targets and informing water allocation strategies. So I'll just provide a couple of examples in that sense. The first one, of course, needs to be SDG 6 on clean water and sanitation, for which FAO is custodian agency of two indicators. 641 that is on water use, in changing water use efficiency, and 642 that is on level of water stress. And if you read the latest UN Water report on the indicator, it says that the main challenge for this indicator is obtaining enough information. Only 86 countries regularly report on water use, and that makes it impossible for many countries to decouple the economic growth from the water use. That is exactly the purpose of this indicator, understanding how the water use is linked to the economic growth and try to decouple that in a way. So that's where remote sensing can definitely play a very important role in trying to fill these data and information gaps. And luckily we're also in a good moment for that, because the interagency an expert group on SDG indicators is going to revisit the methodology for calculating this indicator, and we hopefully can collectively influence in a way that remote sensing can have a bigger role in the monitoring the indicator from 2025 onwards. But then on the other, let's say, end of the spectrums, the data that we provide can also be used for mobile applications. There are several, we don't do them. Mostly they are done by third parties, because the data that we provide is just distributed for free and through APIs, so it can be very easily integrated with other data. And I think that's the beauty of mobile application, that they can very easily integrate global data with users' information and other type of information. But there's also many contexts where mobile phones are not the preferred, let's say, source of information for farmers. So this is one example in Sudan, where technical staff from the Hydraulic Research Center is discussing the findings of the water productivity analysis that they're running using our data, and have been comparing this assessment of water productivity with prevailing with the common agricultural practices in the scheme. So comparing what's the water productivity for different types of land leveling, planting density, irrigation scheduling, and discussing with farmers if they see how they see this different performance, and then trying to identify best practices and upscale it in the scheme that is huge. It's the largest irrigation system in sub-Saharan Africa. That is, to summarize, I will not spend more time on other examples, but just wanted to conclude saying that knowledge-based water management I think is very high on the agenda at the moment, and we need to seize this opportunity. There was recently a publication launched by the World Bank and FAO on irrigating from space, on how to use remote sensing for agricultural water management. The League of Arab States included evapotranspiration mapping in their water allocation guidelines in the region. We recently had the UN Water Conference in New York. There was a very good moment also to highlight the role for water data and information. There's several commitments taken at this water conference that rely on water data and evapotranspiration mapping. So it's really a good moment for you and us to join efforts to make this happen. To support this process, I just mentioned that we we're just launching a third version of the Vapor portal and the database, but there will be two presentations tomorrow and posters that explain that more in particular, more in detail, so I will not spend time. I just wanted to mention that we are going global. We will offer a global coverage at 300-meter resolution of evapotranspiration at a decadal time step, and that will be available in the summer. And the methodology is openly accessible, and including the Python scripts and everything behind it. And I hope some of you will be interested in trying it. And just very quickly, some of the new topics in version 3. Some of the new data that we are using, and some of the advancement in the methodologies and the preparation of input data. But again, there will be presentations tomorrow that explain that in detail. But the point I want to make here is that we still need a lot more in terms of high resolution LST, because we work on fragmented landscapes like this one that you see in the picture, because those are home to the smallholder farmers who need better information and advices to cope with the climate crisis. And the spatial resolution and frequency of observation can help us address challenges like cloud cover and of course, this very, very highly fragmented agricultural landscapes. And that's where it's needed the most, and that's where we need to put additional efforts together. But as said, we cannot do this alone. We build on a long-term collaboration, and that, to conclude, goes back to the gratitude that I wanted to express for this community. This long-term collaboration is built on, well, it's framed, for example, through a memorandum of understanding between ESA and FAO, through which, for example, the ET4FAO initiative helped us improve the methodology of version 3 that now includes, for example, the thermal sharpening that was developed under that initiative. That is also will be presented through posters and presentation, and that is also reflected in PyVapor. That's the open source Python package that runs the evapotranspiration. Of course, we use EcoStress for validation of the data and quality assessment. Our partners, IHE Delft and also at ELIF, they use it for quality assessment and informing the changes and of the new methodologies. We are being involved as champion users and been providing field data for initiatives that are very relevant to us, such as World Cover and World Cereal. And, well, of course, we look forward for using the new product of the Global Land, Copernicus Global Land Service that will include a product on global evapotranspiration map of at 300-meter resolution. That's the plan, and we're really excited and can't wait for seeing that available, and it's a nice continuation of the work that we've been doing in the last years. And lastly, of course, we are very much interested in collaborating for trying and testing this precursor LST satellites and sensors, and start using those in our methodologies. And with that, yeah, I conclude, and I hope there will be possibilities for discussion. Sorry. Thank you.
Thank you very much, Livia, for this keynote speech that I think has very well set the frame of what we need, why we need this type of missions, and why we are here today and these 3 days. So now we are starting the second part of the first session, which will be devoted to several missions that are already on their way to be able to provide this data. So we start with the Trishna mission. So I have the great pleasure to introduce you to Philippe Gamet. Philippe Gamet is the project scientist for the Trishna mission from CNES and CESBio, and he will be explaining to you in no more than 20 minutes, please, Philippe, where we are with this exciting mission. Please, the floor is yours.
Thank you, Anna. So this presentation is an overview of the Trishna mission, and I will tell you where we are and the current activities related to the mission. The title of the presentation is Towards Daily Evapotranspiration from Remote Sensing Thermal Data, because we think that's where Trishna will be a front runner to build this time series of daily evapotranspiration. So quickly, how the Trishna mission is built around science and applications. And high repeat, field scale, global, thermal and solar and low latency data is the objective of Trishna. And the main themes that we address, you already know, so it's water management and agriculture, also ecosystem health, draft, fire monitoring. Coastal and inland waters is also a design driver of Trishna. And obviously, when you get this high-resolution LST data, you can also address other themes that are also crucial, like cryosphere, urban heat, and solid earth issues. So science is concerned, and surface temperature and its dynamics are what we are tracking. And so what's important is the continuity and the density of the time series. As far as applications are concerned, we're dealing with rapidly changing processes which have potential severe impacts. So the quick decision making is needed. So the latency is also a key feature of this kind of mission. Just one slide on the acquisition mask that we have built, starting from the Sentinel-2 mask and extending it to extend the coastal areas up to 100 kilometers and even more from the coastline. And of course, we're working with the other missions to harmonize these masks so that to make sure that when you get data from one of the missions, then you can also get data from the other missions. These are the key features of Trishna. The distributed products start from level 1C with the top of atmosphere reflectances and radiances in the thermal infrared. Everything is geometrically calibrated and auto-rectified and resampled on Sentinel-2 tiles using Copernicus DEM, and this also is harmonized with the different missions. Level 2A products are surface reflectances, LST, SST, emissivity, and also the masks. We also plan for Trishna to go to downstream products, produce vegetation variables, albedo, and also evapotranspiration. And then level 3 is our ready-to-use product with a time series of daily evapotranspiration. So these are the key features of Trishna. It's a 5-year lifetime, global coverage, land and coastal, 3-day visits, 60-meter resolution. The overpass time is now 12:30. I will tell you about this in the next slide. What's a key feature of Trishna, which is important to notice, is that we're going to have different observation angles, and this is different with LSTM. And this goes up to 38 degrees. So dealing with directional anisotropy, especially in the thermal infrared, is a key feature to address with Trishna. Just a few updates on the project status. We got the mission approval by the Indian Space Agency this year. So this is a very good news to go forward with the cooperation with India. As I was just telling you, I'm very happy to announce that now the mean local time at descending node of Trishna is 12:30 p.m. And this is in the objective of harmonizing things with LSTM and SBG. And we think that is a key change for cross-validation and cross-calibration of data from the three missions. Now, this year, we have an ongoing series of technical face-to-face meetings with very, very detailed discussions with India, who is going to implement the French instrument into the Indian platform. So bus instrument interfaces are being discussed. And of course, ATBDs. The development with India is that India has his own mission ground segment, and France has his own mission ground segment, but we're developing based on common written ATBDs. As far as the tier instrument is concerned, we have the critical design review, which is planned before the end of this year. And for the system, we have a review that we call System Interfaces Performance and Validation Review, which will also take place before the end of this year. Just a teaser of the different things that you will see during this workshop of ongoing activities for Trishna. L2 processings and associated CalVal will be presented by Émilie, Thomas, Sébastien, and Vincent. So you have here on the left illustration of the RadCalNet station in Lacroix. You have a poster that you'll have. No, it's a presentation by Sébastien that will explain you what we are doing in this Lacroix site. On the right, you can see a processing flow chart for the level 2 data. The idea that we are having for Trishna is that dedicated processings are possible for day, night, land, water. Depending on this configuration, we have a potential of 4 different processing for level 2. So please see the poster by Émilie explaining what we foresee for this, and of course we open for a discussion. For the ecosystem stress team led by Gilles Boulet, there are different areas of work. The first one is of course ATBD, where we foresee that we have a contextual energy budget ensemble platform, which will be presented by Albert. It's called EVASPA. We have STIC also, which is the single pixel energy budget model. And Gilles will also present a poster about SIMK-CET, simple water budget model forced by Meteo and remote sensing data. It will be used for interpolation and flagging of EVASPA results on evapotranspiration. The CalVal activities will also be explained in a poster. Assimilation of ET into hydrological models is of course a major area of work for this team, and the forest activity is also presented in a poster. This is just an overview of the activities of validation that take place in India, and the current issues that we are dealing with. You also have a poster by Nesrine that will explain that the statistical analysis which is done to estimate the uncertainties, which is one of the major outputs that we are expecting to build the products. For the coastal and inland waters team, you'll have a poster by Emmanuel Autré, which will introduce the Trishna mission on the angle of coastal ocean and continental waters observation. You can see on this illustration the obvious added value of high resolution data when looking at intertidal sailfish beds, for example. And you have to add to this the temporal aspect that you will also be able to follow the evolution of these kind of features. On the bottom of the slide, it's extracted from the poster that will be presented by Elia, explaining the validation data set that is being built based on observation on the French coasts. as far as the Trishna urban team is concerned, there is a poster, there are 2 posters actually on the CAMCAT field experiment, and the activities involve improving the computation of LST and LSE over urban areas, the air temperature estimation, and all the activities around LST disaggregation to manage to get better resolution than better information than this native 60-meter data. For the cryosphere team, you have a poster by Ghislain Picard, who is leading the team, about modeling surface temperature. The poster gives an overview of the models that I used, and the presentation by Sarah will give a better understanding of snow surface temperature variability in mountain regions with the 3 axes: observation, modeling, and data assimilation explained. So please go talk to them. I don't have much more to present. I just want to focus on a few points of attention for that we have to still some work ahead. The first one is to deal, of course, with thermal infrared signal with directional anisotropy. And really, Trishna aims at exploring this with the different observation angles. We believe that it's worth having normalized LST for people that will directly use LST. Of course, when you assimilate LST into a hydrological model to build evapotranspiration, to compute evapotranspiration, you can take the different angles into account. So this is still a major area of work, and we really expect a lot on the campaign, on the airborne campaign that will take place very soon from now, and I think you'll have presentations about this. Another thing that I want to focus on is that now we're going really to deal with time series. So from Trishna on, I think it's important that to consider the product. The real product is a time series. It's not an image. So this really has to be kept in mind when dealing with the data, because if you really want to extract all the added value of the product, it has to be considered as a time series. So the goal is a continuous time series of daily evapotranspiration. So we plan to produce this in the Trishna mission ground segment. Of course, there will be a lot of interpolation to start with only Trishna, with the cloud coverage and with the 3-day revisit. And the idea is that this processing chain will take LSTM data and then SBG data, and so we have this day-to-day daily evapotranspiration, which is the final product to be used by farmers. Timeliness is also a key feature of these missions. If you're going through LST means being able to detect water stress within hours of the occurrence of the water stress. So it's very important to have this in mind, that the whole processing chain and the distributing of the added value product to the user shall be quick for decision making. So this is the whole constraint to be taken for the whole processing and for distributing the data. Another thing that I want to focus on is what I call side variables. It's a crucial part of the performance if you want to do energy balance. And well, we have to deal with this, how to build the right albedo to be used in the net radiation computation, which downward fluxes to use, how to have them quickly. And this is really important if you want to produce, to quantify an amount of water. What's important is how much energy you bring into the system in the first place. So if you make a huge error on this amount of energy, then you propagate this huge error. So it's really also a point of interest that we should have together to get the best possible performance on these side variables. Interoperability, we've talked about this already. We're really working together with ESA, with JPL, with the Indian Space Agency to bring this to the user, products that could be used together. And last point of attention is that we have lots of data. So this is kind of an issue for Trishna to deal with all this data volume. So for all missions, this has to be anticipated, that lots of information means lots of data that we have to deal with. That's basically it. This is some of the people that are here in the workshop, so please go talk to them. It's very important that we get as much feedback as possible, as was said previously. So they'll be very happy to explain what we're doing and to take feedbacks to prepare the mission the best way. That's it. Thank you.
Thank you, Philippe, for the good, complete, and well-integrated presentation. It was also a teaser for the poster session, I think. So I think for the presentation, we will take the questions at the end of the three presentations of the different missions. So now we will move to the US side. With new missions, or more a set of missions and instruments, going from the current EcoStress to the airborne eye test and the future SBG thermal. And this will be presented by Simon Hook. As I said, I will not present his CV because it's 6 pages on internet, so you can read them. He's just, well, I will just say that he's PI of EcoStress and HITEST, and also the project scientist at JPL for the SBG thermal mission. So the floor is yours for, I hope, 20 minutes.
Okay, 20 minutes then. So good morning, everyone. It's really fantastic to see everyone here. I guess a lot of people have seen the light, or perhaps I should say felt the heat, which is a little bit more appropriate. So what I'm going to do today is talk to you a little bit about EcoStress, SBG, and HITEST. And you'll also see these instruments featured throughout the course of the next 2.5 days. So this next slide just gives you a quick update of what I'll talk about. First of all, I'll say something about EcoStress, and then after that, I'll get into SBG. And then finally, I'll talk about the HITEST campaign. I will cover a lot of material, and I'll go fairly quickly, but I do plan to be here for the full 2.5 days. So if you've got any questions, please come and ask me them. So here's a little bit of information about EcoStress. EcoStress was an instrument that was built very rapidly. It was selected in 2014. We had it up on the space station in 2018. It was supposed to be a 1-year mission. And then that 1-year mission got extended to 2023. And then that recently we heard that it's been extended until 2029. So that's absolutely fantastic, and really it's a credit to all of you using the data and making people realize how important it was to have these data. It's a thermal infrared instrument with 5 spectral bands. Some of you in the audience who've used the data may know that currently there is only 3 of those bands working, but we have just got all 5 bands working again, and so now if you go and try and download some data, you'll be getting the 5-band data as well, which is also great news. Now, the goal of EcoStress was to look at stress in plants and basically look at evapotranspiration and see how it was changing over time. And one of the big advantages of being on the International Space Station is that the orbit time changes. So unlike these missions that are coming up, SBG, LSTM, and Trishna, with EcoStress we get data at different times of the day, and so we can use that to decide the optimum time to look at stress. So happens the optimum time is 12:30, and it so happens that all the missions have now selected 12:30 as their overpass time. And of course that's really not happened by chance, it's happened by all the work that we've been doing together. This just shows you the mission life cycle for EcoStress. Basically, we build the instrument, we launch it, and then we start making measurements. And the idea was, after that first year, to literally take the instrument off the station and then release it into the atmosphere and burn it up in space. And so fortunately that didn't happen, and we are continuing to make measurements until 2029, hopefully. So this is just an early result with EcoStress, and it kind of illustrates the value of the data. Basically, because you have this unusual orbit on the ISS, you sometimes get days where you actually get 2 images in a day. Now, there are other times where you'll get images every day, and then there may be other times where you get images every couple of weeks. So it's very variable because of being on the ISS. But when you look at these data, what you can see is in the morning, the fields, which are sort of lightly colored in cyan, are not stressed. They are not evapotranspiring a lot. But if you look in the afternoon, the fields that are dark blue are the fields that are really evapotranspiring a lot, and not all of those fields that you saw in the morning are evapotranspiring. And that's because those particular fields are not irrigated, are stressed, and obviously we can see that with these data. Now, I thought I'd show a few examples of how we use EcoStress, and I couldn't resist showing this particular one because it involves producing wine. And in this particular case, there is a period of time which is called veraison, where the grapes are stressed in order to produce the best quality wine. And in this period, you really need very intensive monitoring of the grapes themselves. And one of the problems was, with prior instruments, you would only get data every couple of weeks. And so that wasn't sufficient data. But once EcoStress came along, we were able to get several images in succession over a very short period of time, and then they were used in this particular application. Now, here's another application. You saw an example of this with one of the earlier speakers, but here we have a company, EriWatch, and basically what they do is they take all the EcoStress data in, and then they use it to determine how much water farmers should put on their field, and farmers can subscribe to the service, and then they can have an app and they download the information on their particular field, and they determine how much water to put on that field. And that's a great example of actually using these data in real sort of life applications. Oftentimes, I think in the remote sensing community, we're quite far removed, literally, given that it is remote sensing, from what it is that we're doing. But with EcoStress, we really have an influence on the people. Here's another example. This one is from Las Vegas, looking at urban heat. There was a press release associated with this. One of the things that you can see straight away is the grid associated with the road network, and that's because we've got high-resolution data. So we've got to have this combination of a high revisit with high spatial resolution data. And when we do, we can see things like this grid, where the roads are obviously much hotter, and you'd really like to do something about the fact that the roads are indeed much hotter. And in fact, if we look at this next example, this is something where people are actually doing something about it. And what it is an EcoStress image from Los Angeles. And in LA, one of the things that's happening, obviously, is we have these heat waves, and it can get very hot. And in order to combat that, we've started painting the roads white. And we paint the roads white to reflect the heat and keep the area a little cooler. And what happened was we acquired an EcoStress image over this area before and after they painted the roads white. And what we could see immediately was that the painting the road made it significantly cooler. And in fact, the local agency that had done this and was working with us with the EcoStress data were able to take this image to their to the federal level and to the state level and get additional funding to paint more of these roads white. And so this is a sort of direct example of how we're actually using the satellite imagery to see a change that's been made in order to improve things and see how much it's improved and then use it to get more resources to do more work. And I think that's another great example. And here's another one looking at wildfires. One of the nice things, again, when you've got high spatial resolution and you've got a frequent revisit, is you can see the perimeter of the fire and you can see the rate at which that fire is moving. And in this particular case, the fires are moving in an area where the teal lines are, which are power lines. And obviously, once the fires approach the power lines, they have to turn them off for safety reasons. So it has a big impact. This is actually from Oregon, and the power lines coming down in through California. And so when the power gets turned off, you know, people are pretty unhappy. So they really want to know when this is going to occur. And EcoStress gives us data that can really help with that. But as was mentioned by the previous speaker, when it comes to firefighting, you need to get the data to the person in charge at 6 a.m. the morning of the day that they are particularly fighting the fires. If you get it 2 or 3 days later, it's no good. So one of the things that we have to do with all of these instruments is make sure the data are available in a timely manner, as Philippe mentioned. And certainly when we talk about SPG, one of the things that we're doing is making sure that we have these low latency products available in less than 24 hours. So just to summarize there with EcoStress, we're back with the 5 bands. We're on the station until 2029. Hopefully everything will continue to work well. We're acquiring far more data than we expected initially. We're acquiring about 3 times as much data. And EcoStress currently is the highest spatial resolution thermal infrared instrument in space, but hopefully there'll be several more joining it soon. And as I mentioned, it has these 5 thermal bands. So that's a little bit about EcoStress. Now I'm going to talk a little bit on SPG. So for those of you who are familiar with the American system, you'll know that we do something called a decadal survey. And then in that decadal survey, missions are recommended. In this particular case, there were 4 missions recommended. 3 of them have been moving forward. And one of those is SPG, or the Surface Biology and Geology Mission. And now, recently, NASA announced that it was going to refer to all of these missions as the Earth System Observation, or Observatory. And then this is just a schematic showing those and showing the different missions. Now, when we do the decadal survey, we actually look and go to the community and see what particular science questions need answering and which ones are the most important and so on. And we do this with both science questions and we do it with applications. And what's quite interesting with SPG is there are several here that you can see very important science questions identified in that decadal survey related to hydrology, to ecosystems, to solid earth, that an instrument would be able to address. And that was why the particular performance specifications of SPG were chosen. But in that survey, these were the research questions, and there was also a similar table produced with applications questions. And if you look at the applications, and I've highlighted in the yellow boxes, you'll see there are many, many more applications highlighted there. And it's because that the thermal infrared data really lends itself to these particular applications, whether it's figuring out how much water we're going to be able to, we need to put on a field to have the maximum amount of food, or whether it's looking at volcanic plumes and deciding what impact it's going to have on aviation. You can use these data for a very wide variety of applications. Now this next slide just shows you some of the key parameters for the SPG instrument. I'm not going to go through these in detail, but I did want to highlight a couple. Recently, so EcoStress has 8 bands in the thermal infrared. Sorry, not EcoStress, SPG has 8 bands in the thermal infrared. 2 of those are in the mid-infrared part of the thermal infrared, and the other 6 are in the thermal infrared. Before, we had 1 band in the at 1.6 micron, and we moved that. Now, one of the great things about SPG is it's a partnership with the Italians, with ASI, and the Italians are providing a visible near-infrared instrument to go with that thermal infrared instrument. And that visible near-infrared instrument will have 30-meter spatial resolution. So we'll have this really nice complementarity between the visible near-infrared and the thermal infrared, with the visible near-infrared at 30 meters and the thermal infrared at 60 meters. And we can use that to do things like sharpening, thermal sharpening that was mentioned before, which is something that we'd really like to do. Now, obviously, we're putting a lot of thought into how we're going to calibrate and validate SPG. And so we've been doing a lot of this work with EcoStress, and we have sites set up at places like Lake Tahoe, where we continuously monitor the temperature of a target and then compare that with what we will see from space. Recently, we added radiometers at the LaCroix site, and so we've added that. And in addition, we're going to add a radiometer in the Venice Lagoon, at the Venice Lagoon site. So we're now building up this calibration and validation network to go with SPG, but this same network can be used for Trishna and also for LSTM. So we obviously want to work together to share all of these data so that we all agree that we're getting the correct temperatures. Now, a few people mentioned something about masks. So there's a mask which determines where the instrument is turned on and where the instrument is turned off, or whether the instrument is put into a lower resolution mode. On this particular mask, anything that's in black or grey means we are going to get it at full resolution, 60 meters. Any of the white areas, we're going to get at much lower resolution, 1 kilometer. Now you'll say, well, why is it called a universal mask? And the reason is because LSTM has a mask, Trishna has a mask, SPG has a mask, and so what we decided to do was merge all the masks together in one that overlapped all of them, so everyone was satisfied, and we've referred to that as the universal mask. And our plan is, in fact, to get data with the universal mask. So this just sort of shows some of the characteristics. Obviously, getting those data down is a challenge, and so we have to make certain assumptions. Now, one of those is how we define day. That's when we're downloading the visible near-infrared data from ASI, and so that is shown when the solar elevation angle is greater than 20 degrees. There are other things involved in order to make sure that we get the data down, but we have run the scenarios, and we think that we will be able to get the data down. As I mentioned before, we have these low latency products as well as standard products. And so the low latency products are available in 24 hours. And so the low latency products, they don't involve any of exchange of data between Italy and the US at the moment. So they sort of act independently. But then once we get the Italian data, we use that to improve the registration as well as get the NDVI for the thermal products like ET, and that processing takes about 72 hours. So we have our standard products in 72 hours and our low latency products in 24 hours. It may be that those low latency algorithms are not as good as the algorithms that are used to produce the WANT products in 72 hours, but we feel that it's worth that in the sense that we get the data when it's needed. We are intending to produce a whole suite of products, and the products are listed here. Key things include things like the land surface temperature, the reflectance, But in addition to that, we are getting evapotranspiration. We're producing it in a whole different variety of flavors. You heard stick as one of the examples that was used in an earlier presentation. We're using a few other methods as well to get ET. And we're going to make that all available as an ensemble product, the same way that we do with EcoStress. We're also going to get other things related to geology, for example. We have things related to volcanoes, looking at gases, looking at volcanic plumes. We have geology products, looking at the different mineralogy of the surface. So a wide variety of different products, and you know, those products can be used in a wide variety of different applications. And so there's a set of visible near-infrared products. I'm not going to dwell on these. And then there's also a set of thermal infrared products, and they are low latency and standard products. So what I wanted to do now is talk a little bit about international partnerships. Obviously, SPG itself is an international partnership between Italy and the US, which we're very excited about. But then in addition, we have Trishna, which is a partnership between KNES and ISRO, and LSTM from ESA. And these missions are all launching at different times. But it's not unreasonable to expect that they will continue to work beyond the end of their nominal 3-year period. Now, if that happens, we will get a situation where we have all 3 systems in space at the same time. And when that happens, provided we are, how can you say, we work together, then we will be able to time things such that we get a global 60-meter resolution image every day. So sort of think about what it's like now where, you know, maybe you can get a 1-kilometer resolution image every day. We will go to getting a 60-meter global image every day. It'll be absolutely amazing in terms of what we can then do for agriculture and other areas. So that's one of the things that's really exciting about this international partnership, which is just highlighted there. And of course, through some of that, we hope to have EcoStress data overlapping. We want the missions to overlap so we can cross-calibrate and things like that. So there's a lot of potential there. Now, each of the instruments have different swath widths, but you'll notice that LSTM, Trishna, and SPG are all these wide swath images. That's what allows us to get the frequent revisit. As I mentioned before, we picked 1230 to get the maximum stress, as is indicated here, and this was information that we gathered in part from EcoStress. Now, all of these instruments have their own some slight differences. So, you know, SPG, Trishna, and LSTM. Now, one of the differences with SPG is we have these 2 mid-infrared bands, which allow us to look at very hot targets, wildfires, volcanoes, things like that. And then this table just gives you a comparison of the specifications for all 3 instruments. And you'll notice that the 1230 is highlighted for Trishna because, as we just found out, that now all 3 instruments will have the same overpass time. So 60-meter data globally every day. That's what we hope for. And then lastly, I want to spend a couple of minutes talking about the European Airborne Campaign. That's something that's underway at the moment. We're bringing an instrument from the UK and also HITES from the US, and we're flying them on 2 aircraft very close to here. The idea is to look at different angles and their impact on retrieving LST. This is just the characteristics of HITES. It's got 256 bands instead of the 6 or so bands that we might have on SPG in the thermal. So it gives us a lot more detail. It's much higher spatial resolution. And as I mentioned, there's going to be 2 instruments flying, one on the British Antarctic Survey Twin Otter and the other on the Canadian Borak Twin Otter. We're interested in looking at these angular effects. As you can imagine, when you look off to the side, you see a certain amount of shadowing associated with any sort of topography, whether it's trees or whether it's furrows like this, and this affects the temperature and it'll affect our retrievals, and we want to understand the impact of that. And so in order to do that, we have these two aircraft. Both aircraft will fly over the same spot at the same time, but just spatially separated, obviously. And in fact, they have to be separated by a fair amount just for safety reasons as well. But we'll be able to see a particular angle with one instrument corresponding to the nadir measurement with another instrument. And so this is really the first time that we've ever done anything like this, so we're really excited to do it. We have a whole series of sites in Italy, as I mentioned, but the plan is also to go to France and fly the Le Creux site and several other sites in France as well, Toulouse, for example. And these are the sites in France that we're looking at. So basically, we plan on spending a few days there, sort of flying across there. So I've gone through a great deal of information very quickly, and I'm just going to make a few highlights here before I finish. So firstly, EcoStress has now been extended until 2029. We go through a process where we get funding every so many years, and we've got our funding out until 2026. We've also gone back to being able to use all 5 bands, so that's all very exciting. NASA has announced the Earth System Observatory with these 4 different anchor tenants, one of which is the Surface Biology and Geology mission. SBG, which is this partnership between Italy and the US, is moving forward. We've just had our MCR and KDPA, and we're now in phase A with a currently planned to launch towards the end of the decade. And we're having this European campaign, which is going to take place literally in the next few weeks, and we'll be making much higher spatial resolution measurements at very different angles in order to look at this angular variation. So I'm going to stop there. Thank you very much.
Thanks a lot, Simon, for this summary of all the activities that NASA is undertaking in the thermal infrared area. And also thanks a lot for highlighting the importance of the international collaboration in this topic that impacts worldwide, as indicated by Livia in the first of the presentation. That was very inspiring. Thank you. So now we go through the last presentation for the morning session, who is going to be done both by Benjamin and by Ithier. Ithier Barat is the LSTM System and Performance Manager on ESA site. So please, the floor is yours to introduce us to the LSTM mission.
Okay, so that will be the last presentation of this session. I think there's a lot of information here. But we want to conclude now with the LSTM mission to make the LST trio, or 3 musketeers, or I don't know what you want to call them, complete. You've seen a lot of information already being passed on these missions. I just want to highlight here that this is a real team effort, also by missions, but we also make sure, even the names here is the team of the LSTM project, but also the mission advisory group behind it, and there are many scientists sitting here in the room, but also Simon and Philippe are part of it, so we're really trying to get everybody connected to make these missions most useful for the community. Just to set the scene, LSTM is part of the Copernicus program, and it will be joining the big family of Sentinels with of the new 6 expansion missions of the Sentinels. They will go then from 6 to actually 12 Sentinels. That's the plan. That's what we're preparing together with the European Commission to fill in the observational gaps which we have identified together with the European Commission some years ago. That shortly introducing these 6 different missions, they all trying to address burning or critical observation gaps, and with that also applications and policy drivers. You see LSTM between climate change, and we made this case before, and the food security and water management sector, let's say. And I think we have already a lot of reasons why we should be doing that. That is saying here that there actually is also CHIME and Roselle, others, they are contributing to these different observations, and we all need to make the case with our, let's say, decision makers to get the right funding for these missions as well. So I also have a plea here that if you want these type of missions to go forward, we need to also make the case and the advocacy in your countries and your member states. Just, okay, that's, we have made the case here already why we want to do that. Just wanted to re-highlight here that there's 3 different climate risk, which we can address with high-resolution thermal observations. One is the human heat, the heat stress, basically, which humans have to deal with within heat waves, but then also the kind of the synergy between crop production and water productivity, which we have seen from Libya very clearly, and that is, at least here in the example of Europe, even under low and medium adaptation, a case which we have to really deal with in the upcoming days and years. That is the driver why we have started to develop and design and actually build the LSTM mission. The main mission objective is in support of agriculture management services, and I stole here the more crop for drop slogan from FAO. It is really where I think the biggest impact of this mission can be made, but at the same time there are a range of additional applications which we will support. It just means that we design and focus the capabilities on the agriculture part. That doesn't mean that we cannot support the other objectives. Good. Just as a short overview, that what is the key features of the mission. That is responding to a number of user requirements which were coming from a consultation together with the European Commission. We translated that from user requirements into mission requirements, and then there is a whole engineering effect to make the instrument and the mission as a system to build around that, and Itzia will in a second introduce you to the details to that. Just to say that there also is these type of applications we are focusing on. It comes back to the drivers which I just introduced. Water productivity means that we need to have the evapotranspiration, and this product here has been also being developed together with FAO to make sure that we have the right information at the right resolution to make the right decisions on the farm. There's, I think, also a lot of private sector people interested in that, because agriculture is one of the biggest commercial sectors in the world, and on top of it is, I think, the only open-air factory where we can actually go and spy, so that it makes a difference. And then where we live is our cities, and they are really under stress in the moment, and eco-stress, again, makes a very nice case. Thanks, Simon, for these images from last year. So just bring that together from emission to the products, and LSTM really focuses on the main base products, so level 1C and level 2A products, to develop the basis so you can use this type of information and build your own information products, for example, ET and services based on that. And that is following very much the downstream type of services which the Copernicus program is supporting. We really try to develop these products to be operational, because LSTM as a Copernicus mission has to be operational. And that, I mean, we heard a lot about latency. The latency timeliness part of this mission is important to get this information from a very dynamic parameter into the hands of people who make decisions as fast as possible. And you see here our goals and thresholds of latency for level 1 and level 2, which are very challenging, but I think making a big difference. And both my previous speakers made this case very clear why that is so. Yes, I think with that, we want to make sure that we can develop these kind of products in the right way, I mean the best way, so we need to have data. Simon already said there is an airborne campaign which we work together with JPL since a couple of years actually already. That's not the first time HITEST comes over here, but this time we make sure that we have this dual view because directionality is very important. Philippe made the point. We really want to have these data sets so we have the right means to develop them, the algorithms, and we also will make sure that these data will be available for the community so you can also do your science and your development of algorithms appropriately, because I think we really need to build on your expertise as well. That just gives you an example what was already done in 2021. And that data set, there should be Dirk Schüttemeyer in the room. He's responsible for the ESA airborne campaigns. These data sets are available to be shared, so we can also make that available. That tries to give you the directionality, but it's done over, I think, half an hour or more to make this data available. So we need to have this dual view to make it co-located. With that, I hand over to Itzia to give you the real insight of the missions.
Thank you. Thank you very much, Ben. Okay, so I will introduce a bit how we are going to realize all these nice requirements into what is the mission. We kicked off the Phase B2 nearly 2.5 years ago, so it's when all the fun started. And we recently passed our preliminary design review end of last year successfully. This gives us the go-ahead to continue to our Phase C and D, and means that we have now a design that we are going to refine, and hopefully by the end of I think it's a mistake, by the end of 2024, sorry, it's a typo, we will have a complete design, a full design that will allow us to move forward and to start building satellite integrated, testing the satellite. So hopefully the satellite is ready at the end of 2028, so we can launch early 2029, so you can have this beautiful mission flying. I will try to show more or less how the mission will look like. The mission actually is 2 satellites. The reason is that we need to have a 2 days revisit. Cannot be done with 1 satellite, so we'll have 2 satellites, each of one with 4 days revisit cycle. And as has been already said, the mean local stellar time will be 12:30 as the rest of the missions. We have a resolution of 50 meters. Our level 1C product will be resampled at 50 meters, but the native resolution at Nadir will be 37. So it's really high resolution. Very high challenging pointing requirements to get absolute geolocation accuracy up to 25 meters if we have ground reference points. As our view angles will be an elevation angle of 20.7, that means that the observation zenith angle will be depending on the part of the orbit in the order of 30 degrees plus minus, but this will be the order. And then you can see in the video more or less how is the global coverage that we get with both satellites once they are in orbit. We will cover quite a huge mass, meaning that we have the land, but we extend the coastal areas up to 100 kilometers. I need to emphasize that this generates between 1.2 to 1.5 terabytes of data per orbit per satellite. That means we need to process up to 3 terabytes every more or less half an hour and provide the results in 6 hours for level 1C, 12 hours for level 2A. It's really a big challenge with all the geolocations and all the the calculations that to deliver a product of good quality. Yeah? So we are putting a lot of effort on this part. You will see later more in detail. The instrument is a Wishbone acquisition concept, as the rest of the tiered channels. On our mission, what we have is also the visible channels are part of the same instrument. So it's one instrument, one aperture with three different optical paths, 3 different optical detectors. And we cover a swath of a bit more than 700 kilometers every 5.6 seconds. So the idea is we swap the Earth. This swapping is 4.5 seconds. Then we keep moving our scan mirror, and then we will point to deep space. So we have a cold target for calibration. Then we keep moving, and then we have a black body for calibration as a hot target. And then when we come back to the deep space, and then start again. So it's a repetition. So every repetition, we have 2 calibrations with deep space and 1 calibration with the black body. So that gives excellent radiometric accuracy. For the visible channels, what we will have is calibration with sun diffuser once a month, as normally Sentinel-2 does and all the satellites that. Oops, sorry. A bit more detail on the instrument. We are flying 11 bands. As I say, all of them are in the same instrument. All of them are one same aperture, 3 detectors, and they are collocated one on top of the other. We have very challenging requirements in both geometrically. We have an MTF between 0.2 and 0.3 requirement, and also in terms of NEDT and ARA. So really challenging. I just put here a bit more details of the center bands and that you can look at the detail later. And just to finalize, to say that it's not only ESA, we have a great consortium. We have put together a great consortium that is led by Airbus Defence and Space in Spain as a prime of the mission. And then Airbus France is our instrument prime developing the instrument. And I think it's also quite remarkable that 36% of this big consortium, because they are more than 60 companies underneath these primes, are small and medium enterprises. So it's a huge boost also for small and medium companies in Europe. And then finally, I would like to present on behalf of the 3 missions all the efforts that we are putting together to really work together. And I will hook on your 3 musketeers. Is really all for one and one for all. Global coverage, daily revisit is not possible if the 3 missions are flying together. That means 4 satellites. So we are really looking forward to see these 4 satellites flying together, and you can really see its daily coverage, and we will provide you the data. So I hope you makes you very happy and keeps you busy for a long time. So with that, we conclude the presentation, and yeah, thank you very much.
Okay, so maybe we have 5 minutes for questions, or 10, yes? So are there questions in the audience? Don't be shy.
So the microphone's going through the room. If
Yeah,
you just raise your hand. And Philippe, can you come up so we can have your answers?
Hello. Good morning. Thank you very much for your presentation. Very interesting. I have a quick question. You talk a lot about the international cooperations. Will you harmonize the data formats between all the levels of products across the missions?
It's a difficult answer to find because it's, no, actually the answer is very simple. Yes, we do. We just had yesterday the mission advisory group coming together on LSTM. We do have a table where we look into all the different missions, comparing the different product formats, and we do try to align them. We plan to have an internal workshop on that between the missions to make sure that they really are aligned as much as possible. So yes, we're doing our utmost to make that work.
Potentially a follow-up to that question. I saw that Trishna listed some bands for split window, some for tests. So if anyone would like to give some thoughts ahead on where those two different algorithms will be most appropriate and most heavily used.
Yeah, thank you for the question. The fact is that we're still benchmarking different algorithms. There's no final choice that has been done. I think for Trishna, it will be done very quickly this year, and also for LSTM, it's by the end of this year. But obviously, we're benchmarking different algorithms. Eventually, we cannot guarantee that all missions will come out with the same algorithms. But anyway, you'll have level 1C products distributed and freely available of all missions to apply any algorithm you think is more relevant in your field.
Hello, my name is Stefano.
Actually, let me just add a little point to that question, because one of the issues that we face is not just the algorithms being the same, but making sure that all the inputs that go into the algorithms are the same. And so even in some cases, we're using multiple algorithms, and we're going to give example data sets with the different algorithms, but we're also going to try and make the input data available. So if there are differences, people can actually use that input data to recreate something themselves.
Regarding the algorithms, what about the clouds? That will be a problem for all the three missions. Do you plug?
That's true, but we will. We can develop fairly sophisticated cloud identification algorithms, so that we can mask out any cloudy areas. And of course, one of the reasons that we want the high revisit frequency is to make sure when there's a clear day, we get it, as opposed to waiting a couple of weeks and hoping that the days are going to be cloudy. So one of the things that makes it possible, for example, to get weekly ET is because the studies have been done, and those studies indicate that if you have a sufficiently high revisit, every couple of days, then it is possible to get sufficient clear data that you can produce things like a weekly ET. So yes, obviously clouds are a problem, but we can identify them, and by having the frequent number of missions, or by having several missions, we can make sure we get the clear days.
Perhaps just one additional comment to that one. I mean, we have presented here the main three, let's say, gold standard missions, but we look forward also to the new space session this afternoon, where there will be many more frequent observations coming from these small sets. So let's hope that could help us as well to fill some of the cloud gaps.
Hello. Hi. So I have a question about the harmonization. You mentioned that that you should have like similar input, but how about the output? Will the data will be tiled and gridded? How about the format? Or you will just, guys, especially for that Copernicus side, leave us with that quite user, very unfriendly Sentinel-3 curvilinear product, which is, yeah, not what we would like to have. So what we can expect?
You know, it's going to be very challenging to have everything in exactly the same format because each of the instruments have their own idiosyncrasies and things like that, and we obviously want to report on those. So what I would say is that every pixel will have a lat long, and we will produce things in a consistent way, such as temperature and things like that, and we will look at whether or not we are getting the same temperatures or there are some differences because of the algorithms and things like that that we're using. But we currently don't have plans for, if you like, a universal format. That's not something that we can't continue to look at with all three missions and see what can be done. You know, at the moment, sort of the emphasis has been more on figuring out ways how we can agree on the algorithms and figuring out things like the inputs and so on, because you know, we want to address that. So we don't really have a universal format, if that's what you're asking.
My question has something to do with the validation activities planned. There was discussions at length about looking at agriculture, but I was wondering whether or not urban areas were going to be assessed at all, because when considering directionality and the number of different emissivities encountered in the urban environment, it is as complex, if not even more so, than agriculture. And if indeed, if you're going to be providing these high-resolution LST products, what kind of activities are planned to ensure that those are going to be accurate?
I'm sorry, I don't know where the speaker was, but okay. You mean now when we run our urban campaigns, for example, we plan agricultural areas, but we are also planning urban areas also during the night to observe directionality effects on urban areas. So we try to cover a range of very different acquisitions, very different scenes, so at the end we can have a very nice data set of urban campaign that we can work with later. So this is for CNDG areas.
Perhaps shortly to complement, there is, I mean, we're relatively early still in this mission cycle, let's say, or lifetime, but there is just recently started a level 2 project preparing the algorithms, but also preparing a dedicated CalVal plan, which is taking into account these kind of requirements for the right information. That's, having said that, yes, it will be challenging. We need to do that in a community type of effort, and that is including the different space agencies. So that is something which needs to have good preparation, and we have also a session on Friday morning on that to go into more detail, and there will be some more information on the different test sites, networks, and so on shared on that.
So I'll just add to that. Number one, we want to get the radiance sensor right. And so in order to do that, you know, we'll have a small number of sites which are extremely well instrumented that we can do the forward calculation. Once we get the radiance sensor right, number two is going to be the temperature and emissivity. And so we will have some temperature and emissivity sites, but our knowledge of the ground measurement is not going to be as good as the number of sites expand. And really that's going to be true when we go, for example, to evapotranspiration and things like that. The uncertainties are going to increase, the quality of the measurements made at the sites are going to go down, and that's just simply a resource issue. And will we cover every single biome? Will we cover every single emissivity? Probably not. Well, in fact, I'm sure we won't. But we will try and hit a lot of the key biomes, and we will obviously look to the community and the community data sets, and we'll be encouraging space agencies to make opportunities available for other people who are doing similar or related validation work to be able to propose and get funding to do that.
Hello. I have a simple question about the eco-stress. And there was a picture of the first fire in the Oregon. And then I'm wondering whether if we take the image of the forest fire and the volcanic eruption and it is saturated or not. And I want to know about the max temperature can be retrieved with the eco-stress.
I can't remember the saturation temperature for eco-stress off the top of my head, but it's on the order of, I think, about 460 K. Now, all the instruments that have been talked about here so far, LSTM, SPG, Trishna, are all going to have saturation temperatures in that region, 400 to, say, sort of 375 to 460 K, something like that. And obviously, the highest saturation temperatures are going to be in the longest wavelength bands. But the one exception to that is SPG, which has a band in the mid-infrared that's designed to saturate at 1200 Kelvin. But I think eco-stress saturates around 450, something like that.
Thanks for the questions. I think that reveals the high level of interest that we have in the audience. Nevertheless, I think it's due time for a break, right? So I will advise all of you to not be shy and try to reach the different speakers of this morning session during the coffee break if you have additional questions. I would just like to recap a little bit what we have seen in this morning session. So we started after the welcoming of our ESA colleagues, we started with Livia, who presented the needs for this type of missions in terms of agriculture and water sustainability. I take the word that Livia mentioned regarding the crop drop. So we have to maximize the amount of crops that we obtain for each amount of water that we use. And then we continue with the presentations of several important missions from ECNES, CESBio to NASA SVG and ESA LSTM, which are three important missions that cover the needs expressed at the beginning of the session and that are going to be either currently developed or they are going to be launched in this decade. And I think it was a very good conclusion, the harmonization that all these missions are trying to have with this daily revisit, and which ties very well with the questions of the audience regarding product harmonization and algorithm harmonization. So I think this ties very well the needs of the user expressed in the audience and the volunteer of the different agencies to set up this joint effort. Thank you very much for your questions and your attention this morning.
Okay, thank you. Just 1 second. We are taking a group picture. So we will be facing the back of the room. And I ask the people in the front to stand up. And the people in the back, please, to advance a bit. And we'll be facing the end of the room for the picture. Please. Thank you.
Now let's go and stand up here.
No, you should be in the front, actually. The speakers is better, yeah. Okay. Please, retreating, coming back here a bit more. Okay. Okay? Okay. We will be taking a picture from the front and then from each side. Thank you.
prova, 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 Dario, 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 Dario chiama Jacopo, Jacopo chiama Dario, Dario chiama Jacopo, mi senti Dario? Dario, 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 mi cago nella puttana, Dario, 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 Dario. Sì, sto presentando ai miei fonici il fischio di prima che non mi è piaciuto. Sì? Sì? Ho detto. Veniva a 3.000 euro. Guarda, da un giorno o a una settimana, 103.000. Perché sai che c'è è il montaggio alla fine. C'è Liro. Comunque non è tanto, non mi ricordo, guarda se lo vedi sul primitivo comandato a cosa, che mi sembra che ho 2008 o 3.000, comunque lo vedi l'ultimo primitivo che ho fatto a cosa. Ho detto che era bello, faceva il suo effetto. Eh. Ok, grazie a te. Sì, sì, prova, 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 prova. Prova, 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 prova microfono, prova microfono, prova microfono. Dario? Dario, quanto devo provare? Dario? 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 Quanto tempo devo stare qua? Dario? Senti, quanto tempo devo stare qua? Mi spieghi quanto devo stare qua? Prova, prova. Sì. Prova. Ok. Lei sarà così. Qualcosa allontanerà, non è...
Hello, hello, hello. Hello. Can we please all reconvene and take our seats? Thank you so much. We have a very tight schedule, so we'll try not to be too much delayed. So can we please all reconvene? Thank you. Before I start calling names, Ferrand Gascon?
Welcome. Does it work? Can you hear me? It's working? Yes, good. Okay, so welcome to this second session on harmonization of an international mission that has been well introduced by the previous section, and we have seen that there is a lot of interest in this international harmonization. So my name is Simona Zoffoli. I'm at the Italian Space Agency, the program manager for the surface biology and geology thermal infrared. And we have...
And I'm Philippe Gamet, project scientist for the Trishna mission.
Okay, so we can start with the first talk on LSTM level 1 processing chain that will be presented by David Almodovar, that is the ground processing prototype leader for LSTM. So you have 15 minutes, and we think to take all the questions at the end of the session. Thank you.
No, it's okay. All right. As said, I'm David Almodovar. I'm from Airbus Madrid. We are the prime of the LSTM mission, and I'm going to talk about the level 1 processing chain and the products up to level 1C. So I want to recap, first of all, in the latest slide we have seen by Isa about LSTM, because I want you to be clear on the scan system and how the satellite works and how it acquires the product, so we can then understand better the product. So as said before, this is a very important mission, and we are going to be able with these two satellites to acquire a lot of data and to revisit the globe in 2 days. And we are talking about that we are going to process around 3 terabytes of data every 2 hours, more or less. So it's a huge amount of data, and it's a big deal to obtain this a full orbit of level 1C products in less than 6 hours for the user. These 6 hours means from the acquisition to the final level 1C product obtaining. So it's not just the processing, but also the time in which we download the data and we process it. So this is the mask we have seen before. The satellites are flying and acquiring in these areas. The tier bands are going to be working during day and night, and the visible one just during day. This is the baseline, and this is the mask. We are going to have a couple of connections per orbit with the K-band to download the instrument data, and one to the TMTC to control the satellite and to check the housekeeping telemetry. So in this diagram, we can see both satellite flying and well, the connection with the missions operation center and with the processing data. So as said, we will have a couple of stations downlinking these 3 terabytes of data. And then this data will be moving to the operational ground processor, and it will drive to the final level 1C product. this latency requirement of COs, as said, is from the acquisition to the obtaining of the product. So this is the chain. We obtain the level data product. I'm going to explain a bit more the products later on. The data is processed from the level 0 to the level 1A to the level 1B and finally to the level 1C in this prototype. This should be done within 6 hours. And we have this high priority data over Europe and Africa, and the goal is to acquire it and process it within 3 hours. With this threshold, but with the priority, this is the goal, which is such a big deal. So to understand the products, in this diagram, you can see the satellite motion along track is this line in the middle. And in the scan motion, you can see some basic repeat cycles. And this is the pure acquisition the satellite does. As explained by CR, this is the basic acquiring of ground. And later on, after this scan motion represented here, the satellite will look into the deep space and into the black body to obtain the calibration parameters to apply later on the processing chain to the product. So to understand the products, the level 1A and level 1B products will be stored as a BRC. So each basic repeat cycle the satellite do, we will have one level 1A and one level 1B product containing the information for all of the bands, the 5-tier bands, the 4 visible bands, and the two shortwave infrared. And later on in the processing, we will have the level 1C products, which currently the approach is to be coincident with the Sentinel-2 grid. So we will have 100 per 100 kilometer tiles with the LSTM bands information that we can put along with the Sentinel-2 visible product, so we can geolocate the product very well, and we can check quite good the area we are covering. This is the scan basic repeat cycle as explained before. As you can see in the picture, you have the Earth swath range, which is these rectangles in this picture. And later on, you see to the deep space to obtain cold thermal values, and the black body, which is fixed at fixed temperature. So for each rectangle here, we will have values from the deep space and from the black body. So we can have specific calibration values for each BRC to be calibrated in the processing chain. So this is summarizing the product data flow. We download the telemetry and we convert this raw telemetry into the level 0 product. The level 0 product is basically translated raw telemetry. In the level 0, we have the ordered packets in time and also uncompressed data to be processed later on in the chain. So this is the input for the level 1A processor, which convert these packets, extract the information from these packets, and build a table with the information per each pixel. So for each pixel, we obtain the digital counts acquired by the instrument, and we have this map here in the level 1A with these digital counts and calibrated. Just let's say the data extracted from the packets and now organize it in the VRC structure. Once we have this level 1A, for each pixel, we also have the calibration data appended to this product. So the calibration data is not yet applied, but is appended and linked to each VRC. So once we have level 1A, we start having heavy processing steps, such as the radiometric correction, straight light correction, pseudo-noise correction, and geometric refinement. These processing steps are very heavy in terms of software, and we are struggling and working hard to reach this 6-hour latency latency time, because it's a huge amount of data and the algorithms are not easy at all. So from level 1A, what we do is, first of all, we apply the physical units to each pixel. I mean, we convert the digital counts to the radians or brightness temperatures. And once we have these units, we start applying the radiometric corrections, such as the straight light correction and pseudo noise corrections. This process is working per each BRC, and we are still obtaining for level 1B the size of a BRC of the satellite. And finally, once the product is radiometrically corrected, we go through the triangulation algorithm, and we improve the geolocation of this level 1B product. And this level 1B product finally is exported into the instrument reference frame. So we split up the level 1B into two different level 1B products, the level 1B0 and the level 1A, and the level 1B, sorry, because of this heavy processor I just mentioned. And so we can have a quick level 1B product, and we can check the product in advance, and we don't have to wait until the full process is done. So we have this shortcut, let's say, so we can obtain this level 1B0 faster than the final product. And once we have several level 1B zeros, I'm going back to this slide. So if you see, the level 1C tiles are covering not one BRC, but several. The best case is covering just 3 BRCs. So we need several BRCs computed and exported with the final units and geometrically corrected to perform the conversion to the level 1C tile. The level 1C tile, we get this level 1B data, and we put it on ground, auto-rectified, and coincident with the Sentinel-2 grid. So this is also a heavy processing step, because you need to resample the pixels and to put it in that grid. You need to change the instrument geometry to the ground geometry. And in here, in the processor prototype, we reach up to the level 1C product, but we work in the interfaces with the level 2, so we can get a clear interface and the input requested, so the rest of the teams can proceed with the level 2 and the level 3 products. Well, this is what I have explained of the product structure. And I want to recall on the satellite design, because we have some requirements, especially for co-registration and for geolocation, and we can reach this requirement of a strong co-registration because of the satellite design. It's just one pupil redirecting the light to each sensor. So thanks to that, we can achieve this co-registration accuracy. And for the level 1C tiles, the geolocation accuracy we are going to reach is 1 pixel. So we are talking about 50 meters, which is less than 50 meters, which is a very good accuracy, and is such a big deal, and we are working hard to achieve this performance in just 6 hours, so we can feed the scientific community with very well quality products and very fast, and revisiting the areas every 2 days. And with this, I end the presentation. I know there's a lot of information here, so do not hesitate in searching for me later in the coffee breaks and ask me whatever you consider. So thank you very much.
Thank you for your very comprehensive presentation. And now the next speaker is going to talk a little bit more about the surface biology and geology. Ralph Basilio from JPL NASA is the project manager of the SBG tier element of the SBG tier mission, and is going to present the USA-Italy Surface Biology and Geology Thermal Infrared Joint Project. Thank you, Ralph. 15 minutes.
Okay, I have to keep an eye on time. Thank you very much, Simona. So I'd just like to understand my audience. So I'd just like to see a show of hands as to how many people identify as being a program manager, project manager, or engineer. So can I just see a show of hands? Okay, how many people are scientific researchers? Can I see a show of hands? Okay, and then last but not least, how many people identify as being a data applications scientist? Okay, so I did this about 10 years ago, and there wasn't that many people doing data applications. But I think this is the sign of the times, that the data that we get from space is now being turned into information so that people can make better informed decisions today and for the future. So thank you for that. I would be remiss if I did not acknowledge the other individuals that helped me prepare this material. So Simona Zoffoli, who is my counterpart here in Europe, Simon Hook, that you've heard from earlier this morning, and then Maria Fabrizia Bongiorno. She is the lead scientist here in Europe for SBG tier. So I just wanted to point out that Simon had mentioned earlier, all this starts, at least in the United States, with the National Academy's Decadal Survey. The most recent one was done in 2017 and was published in 2018, and obviously there was one that was produced 10 years earlier. You'll see that the origin of SBG tier really has its roots not in just 2017 Decadal Survey, but also the 2000 Decadal Survey with the history type of mission concept. But we depend on this in the United States, especially with NASA, to provide some guidance and some framework. It helps define an integrated approach to research, environmental monitoring, and of course, data applications. And thank you again for those that raised their hands saying that they identify with scientific data applications. So SBG is obviously in the Decadal Survey and called out as one of these designated observables. So SBG really has 5 focus areas. It's climate, ecosystems and natural resources, hydrology, solid earth, and weather. And SBG tier focuses a great deal on the hydrology elements of this, with the evapotranspiration, land surface temperature, emissivity. But in the Decadal Survey for 2017, it also called out a complementary element. So this hyperspectral imagery is now broken up basically into a visible and shortwave infrared element, and also broken up into a multispectral thermal infrared element. These were some of the key parameters that were defined in the Decadal Survey, and you'll see a little bit later that we meet these expectations that were called out in this survey. So SBG is now officially part of NASA's Earth System Observatory. NASA made this announcement in May of 2021, so 24 months ago, 2 years ago. And the month after, June of 2021, SBG was formalized at NASA as an official project. We entered what we call pre-phase A, or this early formulation phase. And we are now in phase A, and so that's the first step in the formulation process. But you can see here that the ESO, or Earth System Observatory, SBG is on the left. On the lower left, you see surface deformation and change. There was an earlier chart that said NISAR, which will be launching as early as February of 2024, actually is going to form that cornerstone for surface deformation and change. In the upper right-hand corner, there are actually two elements now that have been connected, joined. That's the aerosols, clouds, convection, and precipitation. That's now called the Atmosphere Observing System, or AOS. And then last but not least, we have a mass change. And for those of you who have been following along, the GRACE mission, the GRACE follow-on mission, mass change is the next incarnation, basically, of that unbroken data record. So the SBG mission is comprised of two complementary primary instruments that are manifest on two separate satellite systems and operating in two different orbit planes. We saw earlier that SBG Tier is going to be taking data at 12:30 p.m., just like LSTM and Trishna. For the VSWARE element, we're actually collecting data late morning, so somewhere between 11 and 11:30 a.m. And there was some question about clouds, and clouds did come into consideration in determining when the VSWARE instrument was going to be collecting data. But together, these two separate platforms are going to provide complementary information, and you'll see a little bit about what I mean with the complementary information. So it's not just harmonization with emissivity, land surface temperature, and other data products, but there are other synergies involved with just SBG itself. So let's talk a little bit about the SBG Tier satellite system. So on the left-hand side of the page here, you see the SBG Tier satellite system in its stowed launch configuration, and then in the center there's an artist rendition of the satellite system in flight. On the right-hand side, there are some of the key parameters, and we've seen that all three gold standard instrument satellite systems now have a local time of data acquisition of 12:30 p.m. descending node. For SBG Tier, we have a ground sampling distance or a spatial resolution of 60 meters or less. Our swath width is relatively large at 935 kilometers, which is a little bit more than 2 times the swath width of EcoStress, and that allows us to get a repeat time of 3 days or less. And you'll see later that this harmonization or coordinated flight with LSTM and Trishna will actually reduce the collective data set revisit time to closer than a day. The launch is as early as 2027, and we have a 3-year prime mission. So on the lower part of the page here are some of the data products, and these should be very familiar to this particular audience. So, and looking at radiances and emissivity, there's land surface temperature, and then there are derived products, higher level data products like the water use efficiency, evaporative stress index. And one of the neat things about SBG Tier is that we do have 2 wavelengths in the mid-wave infrared area. So it's at 3.98 microns and 4.8 microns. That allows us to look at hotspots like wildfires and elements of volcanic activity like lava, and also plumes like sulfur dioxide and those types of things. So you'll see how we do that in the next 2 slides here. So the primary instrument for SBG Tier, it actually has a name, and maybe some of you have seen the name in the posters that are out there, and it's poster number 58 for reference. So that's a shameless plug for later on this afternoon or early evening. And the Tier instrument name is called OTTER. So it's the Orbiting Terrestrial Thermal Emission Radiometer, OTTER, O-T-T-E-R for short. So that poster will provide much more information than what I've shown on this slide, but I just want to highlight that we do have 6 bands between 8 and 12 microns, and then we have 2 bands again in the mid-wave infrared. So we have an accuracy of 500 millikelvin, and our noise equivalent delta temperature is 200 millikelvin. And the field of view is 34.4 degrees half angle, and that gives us our 935 kilometer SWAT. So the presenter just before me was showing how LSTM does its observations. SPG TIER is very similar. We have a constantly rotating mirror that provides the cross-track observations. I think it operates at around 15 RPM or so. And the satellite motion gives us the along-track direction. So we call that a push-whisk system. And that's something that we've taken advantage of from the EcoStress design. Now, the one other neat thing that we've done here in working with our colleagues here in Italy is that we've incorporated a visible and near infrared instrument. So it's a V-Near camera that has 2 bands. It uses the same scan mirror. So basically, we're able to take simultaneous measurements. And for those who have done retrievals of evapotranspiration, you know that the vegetation indice is very important, so NDVI. On EcoStress, we actually look at other data. So it's contemporaneous data sets here. We have simultaneity, so we can better determine or basically co-register the 2 images to make sure that they're cloud-free and the data taken are basically at around the same time. The other neat thing is we have the spatial sampling resolution about 30 meters, so allows us to do downscaling and does image sharpening for us. SNR is there at its radiance reference or radiance level reference point of SNR is 100, and the absolute radiometric accuracy is 10%. Here's the SPG architecture. So just really quickly from left to right, so counterclockwise from the upper left-hand corner, we'll be launching SPG TIER on a Vega C launch vehicle. The satellite system comprised of both the TIER instrument or Otter and the V-Near camera will be mounted on the spacecraft that will be provided by Aussie. Telecommunications will actually be provided by NASA through the Near Space Network, and mission operations will be jointly shared between Aussie and JPL. And then finally, each specific instrument has its own science data system. This is a chart to show you that in addition to NASA and Aussie, our extended partnership extends beyond just those of us working at JPL. There are actually 5 NASA centers that are working on SPG TIER. They're providing complementary services like calibration and validation, algorithm development, data applications. You'll see a presentation, I think it's tomorrow, on data applications, so that's being led by Marshall Space Flight Center. And here in Italy, there's a number of different organizations also involved. Most recently, in the past several months, Thales Alenia Space was selected, and Leonardo was also selected as industry partners for Aussie and the other government agencies. So the international collaboration is here with SPG TIER and SPG TIER, Trishna, and LSTM. So I won't belabor the point here, but just suffice it to say that we're looking at a 1-day repeat cycle as opposed to a 3-day repeat cycle in being able to fly in a coordinated manner. So for SPG TIER's, SPG's 2 satellite system, both satellites produce data, but they're also joint data products. And down on the bottom, just to kind of give you an idea of the harmonization just within SPG, the 2 satellites will actually give us a better understanding, a more complete understanding of surface composition, like the silicate materials that we could see with SPG TIER, and also snow physics, by looking at snow grain size and also the temperature of the snow. And then I think I have one last page here, the closing remarks. Just really quickly, so SPG TIER is responsive to the objectives of the decadal survey. SPG TIER is an excellent example of an international partnership between NASA and Aussie. I have a kind of a simple timeline here that says that we started the project about a couple of years ago. We're now in phase A, and we have every intention to be able to launch at the end of this decade, as early as 2027, and JPL is working with NASA headquarters to the best of our ability to make that happen. And the one other neat thing is I really thoroughly enjoyed this international collaboration that we have here with all three missions. And if you'd like to avail yourself of some additional information on the NASA Earth System Observatory, there's a QR code there. So thank you very much for your time and attention.
Thank you very much for the presentation. We'll keep the questions for the end of the session. Next talk is by Delphine Leroux from CNES. She's responsible for downstream activities related to the Trishna data, which basically deals with the added value products, services, and applications that we can build from this high-resolution thermal infrared data. Delphine, the floor is yours.
Thank you, Philip. Well, thank you, Ralph, first of all, because you did a little survey of the audience, and as a former scientist, now as a current engineer manager, I'm going to talk about applications. So the context of it all is that Trishna has been designed to get a better understanding in various domains. So we have the ecosystem stress and water use, we have coastal and inland waters, urban climate monitoring, solid earth, cryosphere, atmosphere, all of these domains. And during the Trishna days that happened last year, we've seen potential applications in all those various fields, and I'm going to go through them in this presentation. Maybe. Okay. So, of course, Trishna is going to bring new features with different resolution, better resolution, with a revisit period, and this will bring new opportunities for new applications. So here on the left-hand side, I've put on the x-axis spatial resolution, and on the y-axis the revisit period, and all the different previous missions that we've all seen before this morning, Landsat 8 and 9, Sentinel-3A and 3B, Aster, and also EcoStress. And we see that Trishna is going to bring new resolution around 50-60 meters, and also a revisit period of 2 to 3 days. So this is an old schematic, so you read 1 p.m. For the revisit time, but it's going to be 12:30 p.m. as you've seen this morning. Trishna products, we've already seen all of the different listings. So L2A is going to be about land surface temperature, land surface emissivity, surface reflectance, and the L2B, the evapotranspiration, the water stress, surface albedo, all vegetation, different indices. And Trishna will definitely open the path for SBG and LSTM, which will be operational. So the big message here is that preparing for Trishna also means preparing for the next 10 plus years of TIER observations. So here at CNES, we've been working with a human and social scientist. His name is Sylvain Lanfre, and I've taken some of his messages here to you. So data products are a solid foundation, but making them available is just maybe not good enough to answer a specific issue, even through the best portal or the best platform ever. So maybe we should consider separate how data become added value products and how they are brought and used to help taking the best decision for the end user. So here, service providers are essential to bring the right information in the best possible way that fits the user needs at the proper level of details. So he also says that it would be illusionary to think that just making an image available, and in the best case scenario it is optical, so we can relate with what we see with our own eyes, and for TIER images maybe it's a bit different. To a non-specialist, such as a city manager or a farmer, it definitely needs proper interpretation and tuning depending on the use case, and also adapted to their specific needs. So it could be, do I need to plant more trees in a specific street to cool down the temperature? We've seen the image from the EcoStress with the $4 million image. We've seen this street really cooling down. Also, it could be how much irrigation is enough, on when should I irrigate to optimize my crop yield. So these are the real issues we need to answer. There is also another schematic where we put the instrument at the center. So this is the basis, the foundation. The top layer is physics of what is measured, what is observed, so interpreting level 1, level 2 products. Another layer is modeling the environment. This is where the added value products can be placed. Then you have the layer of the application models in order to reach these end users that are city managers, farmers, could be military or transport industry, or watershed managers, could be anyone. And so Sylvain calls this layer the death valley, but because this is very hard to reach those end users. This is exactly where CNES is actually putting a lot of effort these last few years through multiple programs such as SCO, which means Space for Climate Observatory, in order to answer climate change issues. We have a program starting this year called France 2030 in order to answer the institutional needs. And we have all sorts of downstream programs called Ambition Aval, meaning ambition downstream. This is where Trishna downstream program is. And here the goal is to support and encourage the companies to reach those end users and provide the proper level of information to answer their needs. So as I said, for Trishna downstream program, the main objective is to support those companies, those service providers, to build new applications and services using tier satellite observations in response to the end user needs. So if we divide it into 3 steps, first identify those end users, collect their needs, and develop a service to answer them. So we have actually published an RFI, a request for information, last year, asking those companies to describe the services they envisage to answer their client or the targeted user's needs. In response, CNES provides financial and technical support, and we've stressed that all the developments will be carried by those companies to build their service so that they can be autonomous for the future. And we also have a downstream program for a satellite called CO3D, for Constellation Optical 3D. It consists of 2 pairs of satellites, which would be launched next year. And the goal of this mission is to derive 3D products at the world scale at 1 meter resolution. And we've seen great potential to combine 3D products with the tier data. So we've actually encouraged those companies to submit projects merging those 2 products. The main challenge now is that we do not have Trishna data yet. So 2 options were considered. The first one would be to simulate Trishna data, but very dependent on the use case. And also instrument specification are still to be finalized, so maybe it's a bit too soon to talk about Trishna simulation. The second option would be to just use what we call proxy data, meaning data that already exists with Landsat, Sentinel, Aster, and EcoStress data. So for now, we have focused on the use of tier data. Maybe later we will focus on the combination of simultaneous having visible and tier data available. So during this RFI, we've collected 29 projects. 9 were pure tier projects, and 13 were combining the tier and the 3D potential data. So I've listed them all here, but what I wanted to see here is that we have collected various different projects in different fields, and also in fields that were not envisaged maybe at the beginning, such as forests, fire, and also environments with information about illegal dumps or disaster monitoring. Then we evaluated those projects based on technical proposition, clear description of the user need, and the availability of this proxy data. So we've selected 3 fields of interest. The first one is the ecosystem stress and water use, about irrigation optimization, and we've also seen a project on wine crops. The second one is going to be the urban climate monitoring with the urban island, heat island monitoring about thermal comfort of the inhabitants, and also urban vegetation, should I plant tree in the street or not. And the third one is going to be about fires, about the risk management and monitoring if we are lucky enough to have data during a fire. So those ITTs are being written at the moment and should be published before this summer. Then the future topic of interest, but maybe needs a little bit more of prior investigation would be about coastal and inland waters, especially about water quality, and also on the cryosphere side about the snowpack status. So last year, I've been brought the SBG study written by RTI company. So they interviewed many different end users and service providers in order to map the key users and also use cases of SBG data and products. And we have found a lot of common topics, of course, but this is already a good thing, and also a common will to actually support the creation of new applications and services to answer these needs that have been expressed by the end users. So we see here a great opportunity of collaboration between the Trishna, SBG, and LSTM teams. So maybe we should talk about how do we emulate all the companies all together with all this data that we're going to have available. So to conclude, the possible outcome of this first RFI that we've published and the first projects that are going to start with the ITTs, that could be a need for a new product or also a new feature, like the near real-time product with a quick call algorithm maybe, or also more insight on alternative algorithms to retrieve ecosystem stress or any other variable. But the overall goal of the Trishna Downstream program is to stimulate companies and support the creation of new applications and services to answer the end user's needs in preparation for Trishna, but also in preparation for all the other missions that are ahead of us. And more generally, CNES and the French government are putting a lot of effort on application and services development through different current programs that I've cited before. So even if we have different strategies on the way of collecting the needs, we really want to put a lot of effort on this. So thank you for your attention.
Thank you very much, Delphine. Lots of information here, so please stay around for questions at the end of the session. Next speaker is Albert Olioso from INRAE. Albert is a well-known scientist working on evapotranspiration and forest, evapotranspiration retrieval from remote sensing data. And he's also a very active member of the Trishna science team and of the LSTM MAG. I can also say a key member of the Trishna science team.
Yeah, thank you.
Go ahead, Albert.
Okay. I'm going to talk about the combination when we try to estimate evapotranspiration that we need to have continuous monitoring of evapotranspiration. And of course, if we combine the different satellites, we may improve the monitoring of evapotranspiration. So evapotranspiration is a major component of the water cycle, and we need it for many applications in hydrology or agricultural monitoring or agricultural water status. And we know that we can get evapotranspiration from remote sensing data using thermal infrared band. But at the moment, it's very difficult to do that, to have continuous monitoring in particular for agricultural application, because the only satellite we really have to do a continuous monitoring is the Landsat, and the 2 Landsat or the 3 Landsat at the moment, which are coming with a revisit which is very low, like 16 days. Or we can work with MODIS data, and it is 1 day, but the resolution is 1 kilometer, and it's not possible to apply for agricultural monitoring. And also, the cloud coverage can reduce the revisit possibility, the acquisition, the frequency of acquisition of data that can be used for monitoring evapotranspiration. So solution for that, the first things we were doing before in the community is to develop interpolation procedures, which means that in between the acquisition, we develop some very simple algorithm in order to reconstruct evapotranspiration on day we don't have the satellite data. And of course, now, one of the solutions is to develop the new satellite missions that will have a better revisit. So I'm going to talk about 3 of the 3 missions, we are talking about this workshop mainly is, so Trishna, I've been involved in the Trishna program and the program before for, I think, 15 years. LSTM and SBG, but I don't know very well SBG, so I have less information on this mission. So what we wanted to do in this work is to analyze the impact of the new mission Revisit and the combination of this new mission for deriving continuous monitoring of ET. When people are working to analyze the Revisit impact on monitoring ET, usually they are using ground data. So that means that we don't have very much, a large number of ground data to use. Plus, on agricultural areas, we often have discontinuity in the data. So what we are going to do here is to use a model to simulate the sequence of evapotranspiration, and we can do that for many situations. Also, in most of the Revisit studies that were done before, the impact of the error in estimating evapotranspiration at the time of the satellite was not included, which means the people were just looking at the problem of the interpolation error problems, not to the full range of error. And also, most of the studies are looking at the result at the seasonal scale without accounting really on what may happen on specific days where the error in evapotranspiration can be large because due to clouds, for example, we miss the possibility to monitor the fact that there was rain. So we were doing simulation on 3 sites. One is in Lonze, it's in Belgium, one in Grosseto in Italy, and one in Wankama is in Niger. So these 3 sites have very different characteristics. So different characteristics in terms of revisit. So here on this slide you have at the top the numbers for the revisit at the equator for the 3 missions plus Landsat. So it's very different from one mission to another. And on the right part of the top part, you have what happened when you are in Belgium. And the revisit is changing because there is an overlap with the different tracks. And what you have on the right is, so each box is 1 day for the different satellites. And you can see if you start from the bottom, where the revisit is low, close to the equator. When you go up, the revisit is increasing, and for example, if you have LSTM with the 2 satellites, you have a full daily revisit. And of course, if you combine some of these satellites at a different latitude, you will improve the revisit. Just a small point on Trishna. Trishna has a strange cycle because I will explain later in the talk. But if you see, so it's a red box, the red boxes, and you have the design is at the equator is 3 acquisition every 8 days, but it's not on a regular. Within this 8 days window, it's not something regular. So there is the interval between the acquisition is different. So it's 1 day or 2 days or 3 days. Oh, 1 day or 3 days. No, 2 days or 3 days. Sorry. Other differences for the 3 sites are the cloud coverage. So if you look in Lonze, you have clouds almost all the year. It doesn't mean that there is no sun there, but it means that there is a regular proportion of clouds during the year. So which means that we have clear day only 20% of the time. If you go in Lonze, in Grosseto, it's in red, you have less clouds, of course, and in particular in summer, you have almost 80% of clear day. And if you go to Wankama, In winter, there is almost no cloud. There may be other problems, but there is no cloud. But in summer, it is a monsoon time, and there is a lot of cloud. So, of course, this will interact with the revisit in order to determine the number of, or the proportion of acquisition which are available for monitoring ET. So, to do this simulation, we were using a model, a SVAT model, which is a land surface parameterization from Météo France, which is called ISBA, or ISBA AGS. And this model is able to simulate evapotranspiration, is able to simulate the water balance. So it's possible to do simulation on the long term using reanalysis data for meteorological input, like here we were using ERA5. And by changing parameters for the soil or for the vegetation, it's possible to simulate different places or also to simulate the different type of crops. This is what we get. Yeah, I didn't say that also when we have the simulation with the model, we add a remote sensing error, which is related to the error that we have when we estimate evapotranspiration, when we have remote sensing data, which can be something like, let's say, 0.5 millimeter per day or 1 millimeter per day or something like that. Okay, here you have, in red, it is for 1 year, the real sequence of evapotranspiration. And in black, you have the reconstruction that is possible when you, so at the top graph is for Landsat. So it is one Landsat, so it is worst case. As there is a revisit time of 16 days, it's possible to make 16 different reconstructed sequence from this. So all the black lines are the reconstructed sequence. And at the bottom is Trishna, and Trishna with the 8-day cycle, we have 8 reconstructed sequence. What is important here is that after that we define the range of the reconstructed sequence we define as an uncertainty. So the full range is twice the uncertainty. And the difference between a reconstructed sequence and the real sequence is we define as error. So now I'm going to show some results. So here it is the uncertainty for 2 years, where in black you have Landsat in the worst case, so 16 days revisit, and in red you have the other satellite. So what you can see is that, okay, so there is LSTM, Trishna, and SBG. What you can see is that, of course, with a better revisit, the uncertainty is decreasing because we have less possibility to reconstruct a sequence of ET. So, and if you look there, the 3 satellites have almost the same impact on accuracy, on uncertainty, on the decrease in uncertainty. And here it is what happened when we combine several satellites. So at the top is the 2 LSTM. The results are in, yeah, I didn't say, in Grosseto, so in the middle of the 3 sites. So with 2 LSTM, the uncertainty is decreasing a lot, even compared to LSTM, just 1 LSTM. LSTM plus Trishna is decreasing a little bit more, and LSTM plus Trishna plus SBG is decreasing more. And if we end, in this case, to having a daily revisit, there will be no more uncertainty in the reconstruction. So I didn't test the 2 LSTM plus Trishna plus SBG, but it's close to 0. Here, it's something related to the error, but on this graph, you have the proportion of days with an error which is larger than 0.5 millimeter per day. This graph is just to show you the grouping of the different satellites. So Landsat, of course, has the highest proportion of large, no, it's not large, but error larger than 0.5 millimeter per day. But after that, if you look, there is a group of the three satellites, Trishna, SBG, and LSTM, which is indicated in red on the left, which decrease a lot the number of days with this error. And after that, you have, when you go down, you have what happened with the 2 LSTM, which is decreasing the error or the number of days. And after that, when combining more satellites, the decreasing of the error. So here it was for a low error, but here it is what you have if you look at large error, like here I put 2 millimeter per day. When we have an error of 2 millimeter per day, that often means that we missed one reweighting event in the acquisition. That means that, for example, we have one data before, another data sometime later, but we cannot see that the evapotranspiration is re-increasing because there was water applied to the crop. And we cannot see also that evapotranspiration is decreasing after this rewatering. On this graph, there is something which is interesting. Okay, I didn't say but what you have on the x-axis is the error in the estimation of evapotranspiration directly from the remote sensing data. So I say, like, for example, 0.5 millimeter per day, 1 millimeter per day. Here it's going to 1.5 millimeter per day. And so what you can see is that the proportion of error is not changing between 0 and 0.5, which means that in this part of the graph, you have the impact of revisit. And after that, after 0.5, it's increasing, and this is related to the increase in the original evapotranspiration error from the satellite data. Maybe it's a bit tricky, so if you want, we can talk later. Okay. There is one point which is tricky also, is a question of hotspot. So the hotspot, okay, I will come back. Okay. The hotspot is something that happens when the viewing direction from the satellite is close to the sun direction. And in this case, the temperature which is derived from the thermal measurement can increase a lot. It's what you have on this graph, where you see the difference in temperature between the direction of viewing and what you have at nadir, if the sensor was at nadir. And you see that there is this peak, which is the hotspot. And the problem is that we don't know how to interpret this peak in terms of computing evapotranspiration at the moment. So that means that in this range, so I put the red line to say maybe in this range, we cannot use the data to estimate evapotranspiration. And here, in this case, the range is like plus minus 10 degrees of viewing angle. Okay. So now if you look at the cycle, so I didn't say what. So on the left, you have a Trishna acquisition cycle, and you see something which is strange. You have, so when there is an acquisition, the next acquisition is at another direction of viewing, and so on. And this was a specific design in order to avoid hotspots. So that means at the top graph, you have the bottom line, the bottom cycle is in hotspot, but the two others are not in the hotspot. So that means that on the Trishna cycle, we have data without hotspot. If you look at LSTM, so this is 3 different tracks on the place in one camera, and the bottom, the tracks at the bottom is in the hotspot. And for this track, there won't be any available data for maybe a long time. In some places, maybe it's going to be 3 or 4 months without data for this place. The people from LSTM, we can discuss of it, of course. Okay, so now I'm in the conclusion. I think I'm late, right? Okay, so just the two last lines that if we put the different satellites together, we're going to have something better for monitoring evapotranspiration, which was what we were thinking at the beginning.
Thank you, Albert. It was very interesting, and I'm sure that Simon and Fabrizia will share with you more information about SBG mission if needed. So the next speaker is Michele Lazzarini, and is going to talk about the security and other interconnected domains using high-resolution thermal Earth observation, and is coming from the European Union Satellite Center.
Thank you. Thank you. I'm Michele Lazzarini. I'm a project manager of the European Union Satellite Center, and it's a real pleasure to be here for SATSEN, also personally, because before joining SATSEN I was working on thermal data, so it's nice to see some former colleagues. My presentation is from a user point of view, so the idea is showing you some application that you can have with the thermal data for a specific domain, which in this case is security. I'm going to give you a brief overview of the European Union Satellite Center, having today an international SA audience. I'm going to speak about some advantages of high-resolution thermal sensor for the security domain, showing what we can do with this data in this domain. I will also introduce the concept of new security, which is maybe a bit different from the classic concept of security, and I will end with some user needs from our domain. The European Union Satellite Center is based in Madrid. Is an agency of the European Union, and the mission of SATSEN is to support the decision-making action of the European Union in the field of common foreign security policy, basically providing joint products, so geospatial intelligence information. We are normally tasked by our stakeholders, who are the EU member states and other EU agencies, and we provide some product on the specific area that we have been tasked. We are an operational center, but we also have a capability development division. Maybe you know Satellite Center because we are the entrusted entity to operate the Copernicus Security Service in support to external action. And personally, I belong to a research innovation unit called RTDI. Our aim is to identify and implement a new solution to improve SATSEN capabilities. We work on different research lines, mainly developing Earth observation applications and tools. We are very active in H2020 and now Horizon Europe projects, and we cooperate with the main entities in space in Europe, like ESA or European Commission or EDA. The advantages of the thermal sensor, well, you know better than me. Probably we didn't use it so much in the past because when we have a very high resolution due to some airborne campaign, you don't have revisiting time, and vice versa. When you have like a satellite on orbit, the resolution was above 50 meters, let's say, so it was a little bit limited for security. But now with the new actors coming, especially in the new space field, I think we're going to have some new interesting application, especially when we talk about constellations. I'm going to show you now some application in the security domain. I will talk mainly about the first and the last point, so human activity and new security. Human activity, something is mentioned also in the other presentation regarding building temperature mapping or industrial activities of pattern of life. Disaster monitoring, I will not talk about this because maybe it's more related to emergency. Sometimes there's a very thin line between emergency and security. Maybe you talk more about security when you talk about rescue operation or this kind of thing, if not more in the field of emergency, let's say. Military activity, I didn't put any application like this because sometimes you go through some complication with confidential information. But I think for the audience might be very interesting this new security concept we use to define application different from the classic security. For building temporal mapping, I took some images from the web, from Satellite Vu. I think they're going to present something in the afternoon, so I'm really keen to see what they're going to offer. And of course, the improvement with very high resolution, of thermal data is quite significant. So we're not going to go to check, let's say, area where the temperature might be higher or lower, but we're going to identify specifically the building or the critical infrastructure in the case of security that are active, they are of the moment where some activities are ongoing. Also in terms of thermal comfort, we talk many times during the day for the urban heat island is very important also in the field of security because we are talking about also some discomfort of the population or death to identify the area of the city where the temperature is higher or lower. Industrial activities, of course, in the security domain is very important to monitor industries, especially critical infrastructure. I think you can find in the web many examples, especially with respect to the nuclear field. It's very common to verify the activity of an active nuclear reactor with measuring the temperature of the water discharge, so which is clearly visible if some reactors are active or not. So all the things that are useful for us to monitor industrial activity is very interesting, and we would like to have like more products and more images on this type of things. Now I'm going to pass to the concept of new security. Probably if you think about security, you have in mind all this kind of topic, plus probably the military and defense one. So humanitarian aid, or the one I showed you before about critical infrastructure monitoring, disaster. And in this case, let's say security is quite a closed silo, meaning you get your image, you do your analysis, you can infer some information, and that's it. In the last years, we are trying to move also in the field of the new security. One of the biggest topics is climate security. For instance, you can have some effect on the security of the citizen from climate change. Effects can be like or food insecurity situation, how can they lead to migration, conflicts, or environmental activities. I think I saw in one of the slides this illegal dumping or illegal waste sites, health security, energy security. So when we consider, let's say, security with other interconnected domain, we try to have this kind of using this new definition called new security. I'm going to show you some example here of some work we did at the Satellite Center. So basically, the idea is, for instance, from what I also saw this morning, the thermal remote sensing could provide more information about vegetation stress, vegetation status, especially in the food security domain. We're trying to correlate this information with other type of data, not necessarily from Earth observation. We use World Bank data, so economical statistical data, ACLED, which is a database of conflict, and MDAT, which is a database of disaster, and try to understand the causality between them, meaning, for instance, how you can correlate drought with migration. And we did actually a first preliminary test with our own interface, focusing on floods. So we use maps coming from Sentinel-1 and Sentinel-2, related to floods, and we try also to verify this kind of correlation in the Sahel region to see if there is a straightforward correlation. That actually is very difficult to demonstrate, also because normally there are many causes concatenated to cause this kind of security concern. But I mean, it's a first step. There's a lot of work to be done, especially to aggregate data coming from different sources. Regarding the needs, some spatial resolution, many of the missions today are working, represented with a resolution around 50, 60, 40 meters, which is more than enough for, let's say, for environmental feature and the climate security domain. Of course, when we want to have, to understand better some man-made structure characteristic like buildings, we have to go with a high resolution, which can be around 5 meters. And of course, this is like a wish, having something around 1 meter for vehicle activities to verify which vehicles maybe have been used recently or not. This is something which is quite relevant for us. Revisiting time, I think in terms of constellation and all this type of mission, we are merging it, so it's important to have like more passing above the same area during the day and also during the night. And maybe something which is different with respect to other things I've been talking today is that for us the absolute temperature is important, but might not be so important with respect to relative temperature, because at the end what we are more interested is to understand the difference between different object temperature more than the temperature itself. Of course, if you are working in the climate domain, probably the absolute temperature is way more important, but for us, in some cases, the relative temperature is enough. And one other point that maybe came to my mind after seeing the presentations of today is that we probably need, let's say, advanced product, like level 3, level 4, because if you try to correlate the LST of evapotranspiration to security issues is difficult. But if you have, like, for instance, something like was mentioned from FAO, agricultural index or agricultural stress, in this case, maybe there are more correlation with the security. To conclude, I hope it's clear, it was very short, that the thermal sensors are very important in the security domain, and we think the availability of high resolution thermal data will be a sort of game changer in our domain. Not only the classic security domain, but also in this kind of new application that are rising now in the last year, like climate security. And it's very important for us to be like involved in the first phase, to provide our needs and probably also to validate the products in order then to have to foster the future updates of the development service. And that's it. Thank you.
Thank you, Michele, and please stay here, and I would invite also the other speakers to join the stage, because I think we have, even if we are a little bit late on the schedule, maybe we have 10 minutes to get questions from the room. So don't be shy. Are there any questions for the speakers?
Yeah, maybe to help things started, I have a question for David about this level 1C processing. Did you get a specific allocation for the latency for the processing itself? Because I know it's 3 to 6 hours from acquisition to delivering the information to the user, but for the processing itself, do you have a specific allocation?
Sorry, who's speaking? Sorry about that. No, we don't have an exact value for the ground processor prototype. The baseline is to be workable for the in-orbit commissioning. So we don't have the products in an order of days, but we can work with them. We don't have any specific value, and we are working on obtaining some numbers with the algorithms we have currently, and we are working hard to optimize it as much as possible, and we will get values very soon.
I have a question for Michele. You mentioned at the end that you need a sort of level 3 to level 4 product for security needs. I just wonder how you balance that with the needs for latency and low latency in security applications.
So is it the last part, which kind of product?
How you balance that, and if you could comment on the needs around latency and lower latency for security applications.
Well, I think it depends on the type of application. If you're like using industrial, if you're monitoring some industrial site, the latency is very important. You have the data very quick. Probably maybe the same day will be very good. If you're monitoring the climate security, where let's say the trends are what you observe, like if it's a longer time scale, it doesn't really need to be the same day also, because these are a sort of more exhaustive study about the situation, how it can evolve in the future. And at the end, the ultimate goal is to, let's say, try to predict possible conflict or migration based on the climate conditions. So climate, you know, it's not like something that's changing from one day to another.
Thank you.
I have a question for Delphine. You talked briefly about an invitation to tender on 3D and thermal imagery. So again, when will it be released, and what is expected? Is it specifically for 3D and TIR, or could be TIR and something else?
Thanks for the question. So the ITT should be published before summer, if everything goes to plan. And the invitation would be to use TIR data plus something else, and we encourage 3D when it's relevant. If it's not, then it could be something else, but at least TIR data, sure.
I also have a question for you. I have seen that the SCO program released an international call, maybe last year or 2 years ago, I don't remember. So do you plan to do something similar for the Trishna program?
You mentioned the SCO, right?
Yeah, the SCO.
SCO is every year something around September, I believe. So for Trishna, we've published the first RFI last year, and the first intention was to publish something every year, but yeah, this year was not possible, so maybe later this year. But yeah, so this was the first RFI, and this is something we want to do it on a year time period.
But will it be open also for non-French actors?
For now, we've only thought about French actors, but open to discussions.
Maybe it's time to go to lunch.
Yeah, I just have a question for Albert. Well, actually, it's more a comment than a question. You mentioned something about the hotspot configuration and LSTM. So just to make things clear, there will be LSTM data available everywhere, every second day. It's just that for some period of the year and for some places, the configuration of acquisition is such that it will be close to the hotspot configuration, which means that the performance will rely on how well we model the directional effects. But just to make things clear, there will be LSTM data available all the time.
Yeah, I was fast at the end, so the comment is welcome.
No more questions, so thanks to all the speakers.
Perhaps just a short comment. We all now deserve a nice lunch break. So the canteen, who knows where it is, it's out of this building and down the road, and then take a right turn. But I wanted to highlight, we have a very big group actually, and the canteen asked us to, as much as possible, to use cash when you pay. Otherwise we will have a very long line waiting to get our food. So if it's possible, please pay in cash. And with that, please be back here at 2:30 so we can start our afternoon program. Thank you.
I. Sa. I. I, prova. I, sa, I. Prova microfono. 1, 2, 3. Ok. Prova, prova, prova. Ok.
we're going to start in 1 minute. Okay, everyone, please take your seat. We're going to start in 1 minute. They're still like... All right, everyone, please take a seat. Please take a seat. We're starting. Am I just too gentle? I know, or a whistle. Okay, everyone, we're going to get started. Welcome back from lunch. Hope you all got some lunch break. And we're starting like right now. All right, I'll start with introducing myself. All right, we're starting the session. Please. Okay, thanks everyone. We're starting the afternoon session. I'll start with introducing myself. I'm Zhouting Wu from U.S. Geological Survey. It's exciting time. We're going to hear about new space for thermal EO this afternoon. I'll pass it to Ferran to introduce this afternoon's talks.
Good afternoon, everyone. Hope you had a good lunch. So I'm Ferran Gascon from the European Space Agency, mission manager for the Sentinel-2, LSTM, and CHIME missions. And this afternoon, well, we saw this morning an overview of the missions, existing and future missions from the public sector. And in this afternoon, we are moving towards the private sector, looking at what new space from the private sector is proposing us in complement of the public missions. So very exciting session ahead of us. And we start the session with Andreas Brun from Constella IR, which will give us an overview of the high-resolution vegetation monitoring mission. So please, Andrea.
Thanks a lot. Yeah, welcome back from lunch. And I want to bring over a little bit general information, especially on our mission, on the data products, what we have in mind for HIVE, which is, yeah, the next Constellar mission on multispectral with near and tier information. So a little bit about the background. We are expecting approximately a 20% drop in crop yields by 2030. This is nothing new for today. We heard that, we heard that before. Land use generally is responsible for 20% of the CO2 emissions, 70% of the fresh water on the globe is used for agriculture, and 60% of it is wasted. So, and also 55% of the climate mitigation potential lies in the agricultural soil. So, turning agriculture as early victim towards an opportunity fighting climate change. And what we want to do is, or what we can do to mitigate that, is to create reliable information of temperature, water, and carbon on a global scale. So Constellar has built a data fusion platform for comprehensive crop monitoring. So in this platform, it's a multi-data source platform holding our own LISA information, but also holding information from publicly available data, be it Landsat, EcoStress, all these kind of things. The system is globally scalable. It delivers affordable data. So we just think about a few euros per hectare per year for the farmers to get the necessary information to use or to get more effectivity in their use of the fields. Additionally, the data needs to be reliable, so we really need physical measurements at field levels. That's why we are also spending a lot of time and effort in Calval activities and also in the accuracy of our detectors themselves. What we want to detect is the symptoms instead of the damage when it already happens. So we want to see in the plant status, in the soil, already very early, okay, this is a point where we still can do anything against, and not when things are broken already. Our main product is Celestar. So Celestar is already available. This is a platform, a computing platform, which puts together information from a lot of satellite systems to get high revisit land surface temperature information. We are also providing evapotranspiration information. So this is on a field precision or even on a subfield precision. And we are looking into soil organic carbon. So for this soil organic carbon, we took part in a Bayer carbon competition where we were the only Earth observation company. Everybody else was in the field, was looking with tremendous field instrumentation on the ground, and we made the 3rd place. So I think we can be pretty proud on this. Good. But all the public missions seem to be not really enough, at least for now, when all LSTM and Trishna and all the information we got before is in space and operational. So we are in the process of building our own satellite constellation. I go into a little bit more detail about how this constellation looks like. But we are building a constellation with thermal and hyperspectral satellites. We are looking into global mapping of the planet with a daily revisit. So daily revisit in this context means we can spot every place on Earth every day, but we do not image a full, the full Earth coverage every day. So planned launch for the 1st and the 2nd flight model is in 2024. So in June next year, we will have 2 satellites in space and start with commissioning and bringing that thing in operation. So from late next year on, the data will be available. The first constellation comes with with a multispectral Vis-near and long-wave infrared thermal imager. And the space segment for the first generation is under development in a constellation, in a consortium. So we do not build the satellites our own, but the payload is built by OHB, the bus by NanoAvionics, Fraunhofer, where we are founded out of, is building the onboard computers. Everything is co-financed by DLR via the InCubes program. This is the rough architecture and the deployment pipeline. So as I said, June 2024, the first two, 1 year later, or 1.5 years later, approximately, then satellite 3, 4, and 5, and a growing constellation until 2024. So this also shows that we will have 10 Vis-near bands, so identical to the, or nearly identical to the Sentinel-2 bands, at least the ones below 1 micron, and 4 thermal bands with a spatial resolution of 30 meters. Our performance goals are, we will have a swath of 20 kilometers, spatial resolution, or GSD 28, sampled to 30 meters in the thermal, an accuracy for 5% for the Vis-near and 2% at sensor radians, at the tier level. The main products will be land surface temperature, surface reflectance, and surface emissivity, and derived products. We've seen that before, evapotranspiration and soil organic carbon. For Calval, we are, as announced, spending a lot of effort and will still spend a lot of effort until things are running smoothly. We have to do a PRNU correction with deep space images and side slither information. We do absolute calibration with vicarious calibration for the Vis-near. In the tier, similar things for PRNU. We do false light correction with deep space images and dark current, and we do absolute calibration, which is the cross calibration, and vicarious calibration is under development. So we are really happy to talk to everybody operating calibration sites which are suitable for the thermal infrared. This is the result of the cross calibration. So we tested that before we launch, and we found out, so for most of the data sets, so let's say 95%, we are really well within our accuracy levels. On the left side, some tests we did with calibrating LISR to Severi and eco-stress. On the right side, comparing that on a temperature level with Landsat 8. Our processing workflow, very general, so nothing really fancy on this one yet. So we will downlink all the satellite data, we'll catalog it with the necessary information, and only for the data which we really need, where we have orders for, we will go up to level 2, land surface temperature, emissivity, and surface reflectance. This is the geometric correction, also here. Excuse me. Pipeline solution which we have outsourced, pretty standard, using GCPs and cross-referencing, and also the onboard navigation and attitude information. Our land surface temperature algorithm, it is basically development, an in-house development, but close to a TESS algorithm on board. So this graph shows, so to say, some tests, and it shows really, okay, for most of our use cases, we are well within our 1.5 Kelvin temperature accuracy. Good. As a summary, we already have our first payload in space, which is LIDAR, or had our first payload in space. We plan to launch and operate multispectral and hyperspectral satellites for Wisnia, SWIR, and Thermal. The first launch will be next year. Calibration is a big deal for us. And yeah, our main product, high accuracy land surface temperature, provided for the agricultural industry. Good. Thank you very much for your attention right after lunch.
Thank you, Andreas. I think we're going to hold all the questions till the end for discussion. So this afternoon is a faster pace, so we're going to have a temporal revisit of every 10 minutes. So we're going to try to keep like 10 minutes time. So next talk we'll have Mark Seifert to talk about calibration and validation of FOREST-2, precursor for a large constellation of TRR imagers.
Okay, thank you. Yeah, thank you also to the organizers to organizing this great workshop. I'm very excited to be here and discuss all of this. I'll show a little bit about FOREST-2, about our recent calibration campaign, but before this, I'd like to say a few words about ORATEC, who we are. So we have the vision to provide thermal intelligence for a sustainable Earth. So in other words, we want to provide tools to mitigate the effects of climate change. For this, we already have, since a few years, an application on the market. That's the wildfire solution. And this is essentially, you can imagine it like a Google Maps for wildfires. So you have map-like features, additional satellite overlays, and you get information about fire clusters, additional information like weather and whatever you need to manage your wildfires. For this, we combine different data sources together, 21 Earth observation instruments from freely available missions, like mainly NASA and ESA missions, but also others. And the thing is that we want to improve this not only to monitor the fires, but also to really early detect them. And for this, we need a very small revisit time. So our goal is actually to improve from the several days revisit time of some missions to a 30-minute revisit time worldwide in the thermal infrared. And we're planning to do this with a constellation of 100 satellites. So our timeline so far, we launched our first mission, FOREST-1. It's a technology demonstrator in January last year. So far, it's quite a successful mission. If you're interested in this, we have several posters about this, showing some data and, for example, results on our on-orbit calibration. FOREST-2 is our second mission. It's the precursor for our constellation, and we will launch in exactly a month. We recently just finished the calibration campaign of this mission, and later in the talk, I'd like to show you some of the results. We are also planning to provide, on the first stage, top of atmosphere radiance values in MVIR and LVIR bands, and at a later stage, fire products and land surface temperatures. And this is not, so I mentioned the constellation of 100 satellites. This is not something in the far future we are thinking about, but the production of the first batch of 8 satellites actually started, and we are planning to launch them next year. So about FOREST-2, so to differentiate, FOREST is the name of our missions, while SAPPHIRE is the name of our actual payload. So this is what it looks like. You can see on the left side images, and we're using 2 cameras, as you can see, essentially with an angle towards each other to increase our swath. These cameras are based on uncooled microbolometer detectors, which drastically decreases complexity and cost. And with our optics together, we reach a GSD of 200 meters at a swath of 400 kilometers. We are imaging in several bands. So on the top, we visualize this as the wavelengths on the x-axis, and the orange one is our SAPPHIRE-2 payload. So we have this one band in MVIR, around 3.8 micrometers, and then the 2 LVIR bands, one around 8.7 and the other one around 11 micrometers. And if you compare this to other missions, there are also other missions listed there. You can see essentially the LVIR-2 band is a copy of the Landsat 7 thermal band, which makes it easier for us to develop LST retrieval algorithms. So what does our processing pipeline look like? We are operating this as a push frame sensor, so we're getting raw detector frames. We have to apply first detector corrections like nonlinearities, thermal drift, and correct defective pixels. Then the next step is the radiometric conversion. This is just straightforward applying gains, flat fields. And then something which I labeled here is offset and stray light to maybe explain this a little bit. So there's a small sketch of our payload of the camera. On the left side is the detector. Right in front of it are the filters. And then the thing is about these microbolometers, we only can measure relative radiances. And so we need an internal reference for which we use a high emissivity coated shutter. But if you open now the shutter, we not only see the target scene, which are these red arrows, but also the self-emission from the optics. So we have to do the calibration measurements to model the behavior of the optics, which we can then later subtract. So these are these offsets I mentioned. And in a later step, there are, of course, then geometric corrections, so removal of optical distortions, camera alignment, and the whole auto-rectification, geolocation, but I won't go into too much detail there. But essentially, this lists like this whole package of calibration measurements, which we recently did. So the calibration measurements actually finished only 2.5 weeks ago. So we'll show you some preliminary data. The evaluation is still ongoing, but to give like a small glimpse at the data. Here on the left side, you can see the flat fields of our different bands. So for both cameras and for each of the bands. These are only relative color maps, but you can see already stuff that we expect. For example, towards the edges, you see a decrease of the gains, just as we would expect from normal optics. It gets a little bit more interesting if you have a look at the MVIR bands here. I plotted here the histograms. So on the x-axis is the gains, and on the y-axis the distribution. And there are two things that we can see. On the one hand, these peaks of the MVIR gains differ by about 20%. And on the other hand, you can see that the distribution of the camera 1 MVIR gains is somewhat wider than of camera 2. And we can trace this back actually to manufacturing tolerances of the MVIR pixels, because we are using commercial off-the-shelf bolometers here. And they are quite sensitive to these tolerances. So this is still well within our specifications, but if you, for example, then calculate our defective pixels, one of these tests we're using for this is to apply relative thresholds in this histogram. We can see that the MVIR channel of camera 1 shows much more defective pixels than the other bands, which is essentially just due to this long tail of the MVIR distribution. In the end, these are not defective, these pixels are not dead, we can still use them, they just show a larger gain variation than the other pixels, and thus larger error bars. But this is just one of the smaller effects that come out of this. Another thing we also, I want to show are noise measurements. So these are the noise equivalent spectral radiances of the different channels we have. You see a small, so they match pretty nicely, except for maybe the MVIR of camera 1, which is due to the same effect, slightly larger, but also well within our specifications. These LVR values translate to approximately an NEDT of 0.2 Kelvin, so all is good. There's another effect that we also saw here. If we have a look at the per pixel noise of our two bands, of the two cameras, I compared here camera 1, so the LV2 channels, you see that there is some weird pattern. So yeah, I hope this is somehow visible, but there's some pattern appearing in the noise actually, which is spatially correlated. When we have a look at the histograms again of this distribution of noise, we don't see any real hints, maybe camera 2 is slightly wider, but what we actually found out, if we trace this back, ascribe a frequency to this noise pattern that appears, it really nicely matches a voltage regulator that is also close to the readout of camera 2. So still, all of this is well within our specifications, so we are really happy about all of these results. I just want to showcase a little bit that we still see some tiny improvements where we can also improve our payload for the future generations of our imager, especially on the Constellation. So yeah, about the constellation. This will be with quite some not problems but challenges, scaling up from 1 satellite to 8 satellites next year, and then maybe to 100 satellites at some point, or not maybe, to 100 satellites. All of these calibration measurements were done in a lot of manual work, and if we want to calibrate within a year 8 payloads, so 16 cameras, we have to automate all of this. So we are currently working on automating all of our setups to measure essentially day and night. We want to use Forest 2 also to implement an automated validation of all of our products, to constantly monitor our calibration parameters and also the performance of our satellites in the constellation. And another big thing is that we also somehow need to achieve a homogeneous calibration of the whole constellation. So we need to make the measurements of the different satellites comparable. And our current approach, our current preferred approach, are lunar observations, because the moon is a really nice target. We can see it most of the time. We can just make simultaneous acquisitions with all of our satellites. But this gives us only a relative calibration. To get an absolute calibration, there are 2 ways that I see currently. Either we need a thermal model of the moon to essentially predict the temperature distribution on the moon, or simultaneous acquisitions with one of the gold standard missions. And in the best case, actually both. So this is really open to discussion. We approached already a few people about this, but if you have any input in this and if you're willing to discuss, we are very happy to collaborate on these topics. Please approach us. So in the end, just a quick self-advertisement. I'm here with a few of my colleagues. So this is a picture of Forest 1 over Italy. The arrow points to Isar Esrin. And we have some posters about Forest 1. So Andrea shows her results on orbit fire detection. Julia has a poster about super resolution of LST data. And you'll find Diogo and me at another poster about Forest 1 results. Thank you very much.
Thank you very much, Mark. And we move to the next presenter, which will be Kevin Lally from Hydrosat, coming all the way from the US and giving us an oversight on the mission. Please, Kevin.
Thank you. Yeah, thank you to ESA for hosting. I'll skip through most of the formalities to try to keep us on time. I'm presenting on Hydrosat's Pathfinder constellations, which will be launching next year in a quantity of 2. And to give an overview, I'll give you a very high-level description of what that Pathfinder mission looks like, and also how we will build up to an eventual constellation capacity. I will go into a bit of detail on what we're calling the LERI flight model, and then the performance estimates coming out of some recent, similar to what you just heard, just a couple of weeks ago, lab testing combined with system-level modeling to give a first public presentation of our performance estimates. So we will be starting next year launching 2 satellites as ride shares. They will each have a thermal band long-wave infrared payload and a visible near-infrared payload secondary to support. The specs I have here for SWATH and GSD relate to the LERI, the thermal instrument. And the main takeaway here is that the primary evolution that has to happen from our pathfinders to the constellation is a increase in swath. So we're trying to over double the swath, and additionally decrease our resolution by a little bit at the same time. So effectively, that's 3 times more across-track pixels that we're looking to carry on the final constellation version of the payload. At that point, we would expect to roll out eventually to 16 satellites for daily revisit, so that is global imaging everywhere, every day. Here are some high-level specs again to show the differences between our Pathfinder missions and the eventual constellation. So we're taking some compromises on things like lifetime. Again, these are ride shares, so we'll take basically the transporter insertion altitude that we get using the placeholder of 525 kilometers for now. We will mostly be nadir pointed for both of these missions to support that global landmass imaging. And down towards the bottom, you can see at least a GSD spec for our VIRI instrument, and the swath will match in both cases. Quick overview of our data pipeline and some of the intermediate and final products we'll be able to deliver. We've heard a lot today about how land surface temperature can further be used as an input to evapotranspiration, and we will be supporting a number of products at that level as well. The ground processing pipeline leverages onboard calibration metadata. We have an onboard calibration system that you'll see a bit of in upcoming slides. So that basically gives us the telemetry to do on-the-ground radiance corrections to those images. Keep moving here and jump into some CAD models of our preliminary flight model LYRI payload. This system is well underway in production. We're targeting a first unit delivery this year to our mission integrator. And then the second satellite is just a few months behind the first. So some things to point out. You can see an RBF cover in red. That is a protective cover on our calibration surface. So that is a temperature-controlled, actuatable device that is used to generate that onboard calibration data. The payload, all in, it's about 15 kilograms, 12U without the baffle, more like 16U with the baffle, which you can see protruding in the Z direction in black. We're using an uncooled microbolometer detector. We are going with a 2-band system for our V1 of the LYRI. I'll include some more detail about why that is. It's a push broom imager, and we're using onboard time-delayed integration to reduce noise. Fairly simple refractive on-axis optical front end. And everything is very carefully temperature regulated and monitored. That is quite important for a microbolometer system from which we want to extract radiometrically correct data. Again, there is an onboard black body system to provide reference radiance. And we will also be using a number of on-the-ground calibration sites and other CalVal opportunities. We have a poster in the next room that my colleague Tanya put together. She was not able to make it, so I'll be around to answer any questions there. Going into just a bit more detail on imager specifications and how exactly we've configured that 2-band system to start. We are using a COTS microbolometer for the version 1 systems that has created some constraints in how the filter geometry comes together because of a COTS packaging. About a third of the detector is lost to unusable signal. We mask out the majority of that. And yeah, other first order optical specs for anyone that's curious. Okay, and hopefully I have a couple minutes left to get into the details of our performance estimate. So I think the original topic of the track was calibration, validation. We have recently done a lot of laboratory testing in most recently thermal chamber temperature stabilized conditions, which we think is a pretty good idea of our noise equivalent differential temperature under a couple of different cases of TDI. So one thing that I skipped over is we have a couple of different modes of operation. A 90 TDI stage that gives us a 1x1 pixel. If we want to, we can collect a 1x3 effective pixel that gives us 270 effective TDI stages. We do see some NEDT reduction, but based on how this rolls up to surface temperature, what we'll see is that the 90 TDI high resolution mode will really be the one that we operate with. The lower mode there may be useful for things like detailed calibration studies, but not so much for consumable images. So I've got a error tree for one of our bands for the onboard radiance error. So lots of different things that go into this, including how the instrument is changing in terms of its thermal environment, some potential for things like transmittance, drift on orbit. You can see the ones we're most sensitive to would be the responsivity drift, offset drift, all due to changing temperature near the focal plane. That's an incredibly sensitive contribution to our signal, and so we need on the order of, it's somewhere in here, I think around 20 millikelvin stability at the FPA to hit these numbers. So there are definitely some remaining engineering challenges to be validated, but relative radiance on the order of 1–2% is currently looking reasonable given our system error budget. Finally, this is a roll-up of the last two slides that you saw, so the NEDT error as well as our L1 calibration error. There are a couple of additional factors like stray light, scene emissivity error, which have to be included to get to our total LST error, which is the last line at the bottom. The parentheticals include stray light. The first number is without any stray light, so extremely optimistic for stray light as well as emissivity retrieval, but we do believe that less than 2 Kelvin total error, which is our constellation requirement, is possible with this system architecture. I threw really quickly a slide on our spatial resolution. There is an impact due to the microbolometer time constant. I thought maybe at least a couple of people would be curious about that. So there is a comparison here, and I thought it'd be fair to show some spatial performance metric before jumping into a quick image simulation in comparison. So on the left, we're looking at a fusion product that Hydrosat is currently offering. Anybody can reach out and get onboarded for this. It's a daily 20-meter product that's generated on demand for certain areas of interest. Using that as a high-resolution reference input, we have done an L1 radiance simulation for our Leary system. And then just below that, I have a TIRS L1 product. So that's just as you'd get it delivered. And then I just want to step further and downsample back to 100 meters, which is the native resolution of TIRS. If you're familiar with working with the L1 data, I could have gotten this on a request, but I didn't quite have time, so I just did the downsampling myself. But this is to give a closer comparison of native physical pixel size between the two imagers. I'd say we're still very close. We're not going to see completely new features that TIRS can't, but we're definitely coming in at a similar capability. That is all I have for the talk today, but again, please find me around the conference and I'm happy to answer any more questions. And thanks again for having me.
Thank you, Kevin. Yeah. So the next talk, you already heard a plug-in for the next talk from this morning. We're going to hear from Tobias Renick to talk about game-changing high-resolution mid-wave infrared constellation from Satellite Wu.
Thank you very much. Good afternoon. Hope everyone's enjoyed their talk so far. Talk about satellite view for a starter. We're a small company based in the UK, 40 people roughly, and we are launching a satellite in roughly 3 weeks. Which is super exciting. It's our first satellite, but I'll talk to you a little bit about what we're doing. So let's do that. There we go. This is our timeline, and this is our history a little bit. For the last 3 or so years, we've developed this process on this satellite and the technology in partnership with SSTL, our satellite manufacturer. We spent a long time talking about the sort of specifications that would be of use to end users and end customers, and iterated on the design and iterated on the requirements with them. It's taken up until 2 weeks ago for that satellite to have been created and be shipped, and we're happy to say it is now at SpaceX being put onto the rocket, so that's where we are. But in the meantime, we've been flying aerial campaigns with a flight prototype model of the camera, and we've been using that data to basically evaluate our offering, evaluate our process chain, and see what we can do in that sort of quality. Over the next few years, we are definitely going to improve our capacity of the satellite, both in spatial and quality. The plan is to launch an 8-satellite constellation, which will enable a revisit of any place on Earth between 1 and 2 hours a day. This is the team. I'll skip through this because it's probably not as interesting as most other things, but we've grown over the course of 3 years now to roughly 40 people. We have some excellent people joining us more recently. We have James, who's with us today, head of engineering, and he's also got a poster. Please go have a little look at that. We have Maria Gironi from Planet, previously in RapidEye, and some people may know her from the time. She's leading our product development, and with that team together, with the rest of our CalVal and scientists and the executive group, we are creating a company that's successful and moving forward. So a little bit of the team. So this is the spec. A lot of information on one slide. I'll highlight a few things. The difference between what you've seen in the last few slides or last few companies presenting and us is we are a video camera. We are a cryo-cooled medium wave detector capturing 25 frames a second. It's a frame camera. It's not push broom. We aren't doing TDI, which gives us some really unique challenges, but also opportunities. We clearly can't push broom because we'll be too smeared, and so we actually have to forward motion compensate the satellite. The satellite itself moves and stares at the target, which allows us to capture 25 frames per second, up to 60 seconds. So we can do 1,500 frames over the course of 45 plus minus degrees, which again is something fun to look at. But that allows us to do the signal to noise boost using extra frames, and allows us to derive motion and detect various things like that. Talked about the constellation plans. The team in the background for the last 2 years have also started developing, obviously, anything that we need to sell the data. That's the platform to put the data on to be able to sell. That's an API-first approach to selling data to partners and customers. We have the capacity of obviously imaging both night and day. We're launching it in SSO orbit. Daytime, as all of you will know, we have issues with solar reflectance, and therefore we do have a daytime filter that cuts out the solar reflectance part of the medium wave spectrum. What that means in reality is yet to be seen. The physics does say we will get some good data out of that, but we'll see what that actually looks like from space. Let's go there. So this is a little bit more about the forward motion compensation. The satellite itself is gimbal, well, not gimbal, it has reaction wheels on it. It will move itself in a process where it will stop and stare at a single point on the Earth. There is a small amount of error inbuilt into this, clearly, but that can actually also be used to our advantage. We have a co-registration algorithm developed already in-house based on our aerial data, so once this is in place and once we start capturing data at this frame rate over the same point on Earth, we're ready to go. Interestingly, the 1,500 frames we capture are obviously at different angles. We could do photogrammetry with that. We could see what we can do with 3D thermal, something we'll be looking for in the ITT that was mentioned before. And currently our modes are limited to video and snaps. We are looking very much at changing that to become a push broom strip at lower resolution in order to do large area monitoring. A sort of theater mode where we want to capture a lot of closely related images and targets, and then the mosaicing mode. Mosaicing thermal data and thermal snaps that haven't been taken in very close proximity makes very little sense, so we do need to have a way of doing it in close proximity spatially. I could have used very many of the other slides to say what I'm about to say, but clearly we have the same process as most other thermal companies when it comes to processing data. We do have to correct for the non-uniformity of our sensor, and we have an onboard calibration mechanism to do so. It's paddles that are heated and put into the line of sight of the detector, and we perform that at every imaging sequence, so we have a cold and hot version of that. We need to tackle atmospherics and we need to tackle emissivity, as we all know. There is an approach to emissivity that we are looking at which gives us global coverage at a rough resolution for the medium wave. And for the atmospherics, it should be straightforward, but that's again what's what the atmospheric team at Satellite View are looking at to right now. We have an in-house georeferencing solution built based on machine learning that was developed by one of our colleagues during an experimental hack day. It turned out to work really well, so it's now part of our pipeline. It again uses feature matching based on a reference data set that looks fairly similar. So all this data that we'll be collecting for Satellite View as such is we're looking to serve customers primarily. We're looking to serve domains and see what people want to use the data for. And half of the time over the last 2 years for the team has been spent on looking what can we do with the data? What does what look like from space? We've flown over things like factories or refineries. We've flown over lakes, all the usual things, and we're looking what does it look like from space? And who would want to know that information, and what would they need to be able to purchase that more effectively? So part of it is product research, product development. The other half clearly is product pipeline. How do we actually get that into the system? How do we catalog that? How do we serve that? We're very much a stack-based company when it comes to delivering our data. It's the Spatial Temporal Access Catalog, the sort of standard that we'd like to maintain, and we're looking very much at maintaining that pattern when it comes to our tasking, which I'll come to in a minute. So a shout out, I guess, to ESA, like most other people have, but we are obviously very grateful recipients of grants from ESA previously. We worked through a GSTP grant with them to help us look at the radiometry and the degradation requirements of our imagery. And this is what one of the outputs of that was an aerial image that we took all the parameters that we expected to affect the resolution and the quality of the image and applied it across our catalog. So any data that people now purchase or look at from our catalog, from the flight data, has all been applied, has all this degradation applied. And you can see what you can see. This is an oil factory in Liverpool. You can see outflows. You can see oil tanks that are storing hot oil or not. You can see flaring. You can see vessel activity based on the actual temperature of the engine in the back of the boat. And all this has very much helped our sales and BD team to go out and talk to customers about what it is that they want to actually get out. Seen a little bit of this just previously in the AuroraTech slides. This is not degraded data. This is actually just the high-res fire. We were in Berlin when we flew over there, and our pilot and the operator saw it out the window and thought we should just go fly over there. Turns out it was quite fun. This was a recent Grunewald fire, which was captured. Once we degrade that, we will still be able to see the fire front. But unlike AuroraTech, we have a small swath. We're not a large area covering, right? We will be capturing roughly 4 by 4 kilometers. So we are for the high-resolution specific targets only. Oh, good, it works. And then this is a time-lapse of the livable standard refinery that we've got as well, looking at water outflow. Depending on the temperature of the water, there's a few things you can derive. You can start looking at actual capacity production of the plant, or on a more basic level, is it producing something or not? There's environmental aspects of this as well. Hot water shouldn't be released into cool streams too much. There are legislations around that in the UK for sure and the rest of Europe. So again, this was an example of what we might show customers to prove what we can do. So moving on then, talked about what we've developed in-house in terms of the API and the UI. And on top of that, we've built from scratch our catalog, where people can go on, browse, search, and download imagery. Nothing massively special here, but it's specific to us. We've made it do exactly the way that we want it to work, which has meant that we've been infinitely flexible and can maintain that in the way that we want to. similar slide, but talking about tasking and being able to task the sensor with a super ease. We're looking at API-based tasking and also monitoring services, so you can task multiple times a month, a year, and receive the data accordingly. The next level across from just tasking and receiving data for us is people may not want to look at the data in the end, and customers have given us this feedback. They don't want to look at the data, they want to know the answer. And that's the timer, cool. They want to look at the answer, so we developed a temperature API, basically, where you take the values out of our temporal access catalogs, look at the time-based series derived to take that information from a polygon or a point and plot that either on a graph or just alert users accordingly. Lastly, and not least importantly for sure, but nothing of this could work unless we had customers that were willing to come on board as soon as we have data from the satellite. None of the products could have been developed without talking to the customers to understand what they want. And here are just a few of the 60, roughly, companies that have signed agreements with us to have access to our flight catalog data set across a multitude of applications, looking at things like solar and agriculture, not very much, but also building efficiencies and industrial monitoring. The future, and I'll be quick, we are looking at everything that the satellite is capable of doing to improve. And we are, again, talking to our customers to understand what is it that you want more. Most people say resolution, to be fair. However, there are things that we as internal would prefer to prioritize when it comes to giving more information, more spectral bands, being able to downlink quicker and having a lower latency of actual capturing data. So that's the future, and this is the present. Thank you very much.
Thank you, Tobias. And we move to the fifth presentation of this afternoon. So we'll be given by Ian Perry from the SuperSharp Space Systems, all the way from UK. So please.
Thanks for listening to my talk today. And thanks to the organisers for letting me have this opportunity to tell you about our startup company, SuperSharp, and the exciting technology that we're developing for very high-resolution thermal infrared observing. Okay. Okay. So I'll start off with some very good news, which is quite recent news. Some of you may have seen this. This is in the media. We've just had a very significant investment from Satlantis, and that investment into our small startup company, SuperSharp, will allow us to take our technology into space and demonstrate it in orbit. SuperSharp is a spin-out of Cambridge University. It's really a spin-out from astronomy, and Satlantis is also a spin-out from university in astronomy. So we're very well-aligned companies. We have similar ideas. Satlantis is about 5 years further down the development road than we are, but this is a very exciting partnership because we're on the same page, and in combination, we will hopefully achieve some really good things. So the picture over there shows myself, and George is next to me there. George is here in the audience. He's over there. If you want to talk to me or George, you can see what we look like now. So this was the signing and the official launch of this partnership with Satlantis. So we've got Marco, the CEO of SuperSharp there, and we've got Juanto and Ignacio from Satlantis there on the right. Okay. So, okay, this is the boring bit. A little bit of physics, very elementary. I know people don't like equations, but they don't really come much simpler than that. Basic optics. If you want to make a high-resolution image, then the rule is that the image detail will get smaller as the wavelength gets smaller, but the image detail will get worse as the telescope gets smaller, or it gets better as the telescope gets bigger, which is why it's on the denominator there. Okay. So it's very, very simple, and you can't really break that law. You just have to live with it. So there's some consequences of this when you compare thermal infrared to optical. So thermal infrared is, in our case, we're talking about 10 micron wavelength. Optical wavelengths, we might be talking about half a micron. So there's a factor of 20 in wavelength So the good news is, in terms of alignment, these telescopes are easier to align in the thermal infrared because they have to be aligned to a fraction of the wavelength. The wavelength is longer. That makes it easier to align. But the downside is, to get the resolution, it needs to be 20 times bigger. And I'm sure you're all aware that the resolutions we're talking about in the thermal infrared are way worse than the resolutions that people are used to using in the optical. And that's the reason for it. Basically, the telescopes need to be a lot bigger for the thermal infrared. So we've developed an unfolding self-aligning technology, and the reason we've done that is because we see that as the way forward to get big telescopes and therefore high-resolution telescopes in space. And we've also shown that this is feasible because the alignment is, as I said, easier to do at these thermal infrared wavelengths. Okay, so here's something showing the unfolding technology. It doesn't go as fast as that in real life. This is enormously speeded up, but it only has to do that once, of course. It's launched like it is over there on the left, and then it unfolds once it's in orbit. And so you see that you can see the mirrors there when they're fully extended out. That gives you a much wider telescope and therefore a much higher resolution by a factor of about 4 compared to what you would have got if you didn't do this trick. But when you do this trick, you then have to make it work as a telescope. It won't work after it's unfolded. It has to be properly aligned, so it has a system inside itself which can measure its own errors and then bring all those optics into alignment to these fractions of a wavelength that are required. And we've demonstrated that in the lab. This slide shows that there's many degrees of freedom on the optics, at least 3 per mirror, and each one has to be aligned to sub-micron accuracy. After it's unfolded, when it's initially unfolded, it's going to be very badly aligned, and then you have to, so you need a sort of, it's a bit like golf. You need something to get you on the green, and then you need a putter to get you into the hole. And so we have this system that brings it all together at the beginning, and then we have something which continuously keeps it in alignment once it's there. Okay. This is the only slide I'm going to show about applications. We're very much an upstream company working on technology, and our offering is to give very high-resolution optics to people. But we have been working with partners on applications. One in particular that we spent a lot of time working on is climate change mitigation by monitoring the built environment and looking at how much energy is being used, and hopefully, therefore, improving our use of energy to control the temperature of buildings. 28% of the total global fossil fuel footprint comes from controlling the temperature of buildings. And so this is a huge area where if you can make an impact, you'll do a really big impact on global warming for the whole planet. So it says here, one of our partners is British Antarctic Survey. That's not because we go down to the South Pole and do anything. It's because the British Antarctic Survey headquarters is in Cambridge, and they wanted us to do a survey of their headquarters. But we've found that high resolution is really important for this application, because with the resolutions that we can do, we can look at individual buildings. And you really do need to look at the built environment at the individual building scale. There are literally billions of buildings on the planet. We've also worked with company NIAB on agri-tech applications and water stress, and you've heard a lot about that, so I won't say any more about that. And we're also working with many partners on defense and security applications. And they are particularly, of course, interested in high resolution. Just wanted to say how our offering could possibly link in with some of the big missions that we've heard about this morning, and how we can have synergies and collaborations with those. So one thought is that LSTM, SBG, and Trishna, they're great at finding things, and they have a short latency, and they have high revisit rate, but they don't have the definition. So maybe there are applications where that triggers an investigation which is then more appropriate for a telescope with high resolution that can go and target that. And so we see that as a powerful combination because our system is basically a high resolution system that can go and target individual things rather than a survey instrument. So we see that as a powerful combination. Also, another thing is we're very much focused on high resolution, not particularly focused on getting accurate temperatures. We're more getting relative temperatures, and so again, the very well-calibrated missions will help us to calibrate our data. So here's a roadmap. We've done the prototyping. We're now doing later stage prototyping and technology development. This is where we are now. So we're building that thing you saw in the video. We're making a new one of those, then we're going to test it in a TVAC chamber this year, and we're going to try and produce one of those which is space qualified by the end of the year, or at least space ready by the end of the year. And the new investment I talked about at the beginning will allow us to get all the way through to the end of the in-orbit demonstration phase of our program. And then once we've got that in orbit and working and we've demonstrated it, then we go into the commercialization phase where we basically sell our telescopes to people who want them. And we expect at that stage to probably go away from the CubeSat format I showed and move up to larger format devices. So I'm running out of time, so I'll just skip through these very quickly. This is the in-orbit demonstration. If anyone wants to ask technical details, you can ask it later. That's the in-orbit demonstration. We want to scale that up to a small sat platform and also introduce mid-wave infrared capability as well and increase the size of the sensor. And if we just, this is my last slide, so this is just a comparison of the in-orbit demonstrator and the small sat version, which is probably where we'll start commercializing the technology. But I also wanted to put in here, I also wanted to think big. This is a very scalable technology. There's no reason why we can't just making it bigger and bigger. And so on the last line here, basically I have a satellite which will just about fit in a rocket about the size of an Ariane 6. But because it unfolds, it ends up being 12 meters across. And that gives you these crazy, crazy thermal infrared resolutions, 15 centimeters and 30 centimeters. You cannot do that unless you unfold. It's impossible. Okay, I think that's the end. Grazie.
Thanks, Ian. Very interesting design there. So next we'll have Harold Clinet to talk about introducing the Earth Daily Constellation, a scientific-grade Earth observation mission with daily revisit time.
Good afternoon, everyone, and thanks for this great opportunity to introduce our constellation in this wonderful context where we have so many missions that arrive and so many synergies that are possible. So today I will present the slide on behalf of the data science team at Earth Daily Agro's company, where I work with, and especially Arnaud Quesnay and Aubin Aliès, who worked on the thermal part, and Nicolas Karasiak, who worked on the simulated dataset I will show just later on. But obviously, if I'm presenting something about a new constellation, it's just not about team alone, but it's a whole company. So Earth Daily Agro is a subsidiary from Earth Daily Analytics. And Earth Daily Analytics is taking care of the ground and space segment of the mission. They have a strong expertise, and people in the team have been working in space and Earth observation sector for many years. And in Earth Daily Agro, we are more focusing on the delivery of products and services to our customers. And we span all major sectors of the agricultural industry and deliver products over 50 countries over the world. And so you have a quick map of where we have offices around the world. to focus on the Earth Daily constellation. So the mission was kicked off in 2021, and during last year and this year, we are actually building the satellites and the instruments. And instruments are currently on the test bench and being calibrated and so on. And we will have the launch in 2024 with the constellation being fully operational at the end of the year, so at the end of 2024. Except for the thermal infrared, where we will have a slightly more to wait, a little 6 months. But I just want to pinpoint here that the data will be acquired, so it's just on the processing of the thermal data. So as soon as the processing pipeline will be operational, you will be able to access the historical data as soon as the constellation is operational. So I have few elements on the space segments, and I will just point out some of the most important details here. So we will launch 10 satellites, and with a swath of 240 kilometers, which means that we will be able to cover 100% of load mass with a daily revisit time. And the mission is always on, always nadir looking, so which means that we will have every places on Earth available, even if you didn't request it before. So it's of great interest if you have new project and want to work with historical data. It's not small sats, it's actually bigger satellites, and we rely on hardware parts that have proven efficiency from well-known constructors. And we won't pass at 12:30, but at a little earlier, so it's also of interest with regards to other missions. The latency could be less than 12 hours, so it's also very important when we target some application where we need this low latency. Basically, we will have 22 bands covering the visible from up to thermal infrared wavelength range. So you have here all the bands that are planned with respect to what we have currently on Landsat and Sentinel. So you can see that we have some similar bands that will be used for cross-calibration, as we target to be a scientific grade mission, so we will have some cross-calibration and we will align on the Sentinel-2 specifications. And we will also have additional new bands that are also of interest for a various range of topics. So some are listed here, but any ideas of application is obviously of interest. I was planning to give you a little more details on band specification and so on, but unfortunately it's not publicly available yet. So it's something that could be given into further discussions with NDA agreements. But still, we have some value, we have some information on specifications. And what I can give you today is the ground sampling distance. So you see that for the visible, we go up to 5 meter ground sampling distance, while for the thermal infrared, which is obviously of interest today, we have a ground sampling distance of 120 meters. So it's maybe not as much as what we have seen with the previous mission, and especially the public one from this morning, but still associated to this high daily revisit time and the fact that it will be launched soon. It's obviously of interest to maximize the inputs and try to optimize synergies between all the missions. I want, in the second part of the presentation, to go a little further, and we started to produce a simulated data set. The idea was to be able to explore what we can do, what we will be able to do with our data. So we wanted to use actual observation, so we do some data fusion and spatio-temporal sampling to fit with the Earth Daily constellation specs. Additionally, we also added some clouds, so usually we want to remove them, but here we wanted to add them, so we have some realistic time series. And I won't go into detail, and this is something that we could discuss afterwards. But yeah. You have here the results over a test area, which is located in south of France, near Toulouse, so close to where we are, covering 2 seasons from 2018 to 2020. And you can see on this nice video how smooth it is when you have clear time series. You can really see and follow the different plots, the different fields. You can see how the vegetation evolves and detect especially some important events like harvesting or other. We plan to release this demo dataset so everyone could try to see what's available with our data. And it's still not done, but I hope it will be available soon. We were focusing on thermal, so we wanted to test what could be really a product, something that we could improve our knowledge of agricultural practices. So using this dataset, we focus on 2 plots where we have ground truth with 1 irrigated cornfield and 1 unirrigated cornfield. And we use surface temperature and vegetation index triangle approach to get an estimation of the evaporative fraction for each date. So I just have here a few examples of the images so you can see how it changed over the whole region. But the interesting thing is when you look specifically at those plots, you can see some evolution of the evaporative fraction. So I'm sorry because this is not the latest result we have. Because we are a private company, we also have to set our priorities regarding the customers. So preparing this conference was not in the scope here. But still, with this figure, you can see some events that appear. So we know that some of them are directly related to how we process the data for our simulated data sets. And so they will be removed when we will have the actual data, so like the first black box. But when you look at the 2 others, we can see events that are detected, and we have spatial patterns that correspond for the irrigated cornfield at a pivot, which is what we expect from this field. So we can really make the connection between the spatial pattern, temporal pattern of this evaporative fraction. So clearly, it's of interest, it's useful when we deal with agricultural application, and we now keep working and exploring this, and we hope to have additional results soon. One last slide regarding how data will be accessible. So we will have different services and products that will be available from raw data up to derived products that could be directly used by end users. We also plan to have a way to build your own algorithm. And we are pushing toward providing an access for scientists, so you can also play with the data and try it by yourself on a specific area over a specific period of time. So it's still under discussion on how it will be implemented and what will be actually available, but it should maybe be accessible through proposals, short proposal submission or hackathon or something like this. And through a collaborative funded project also. Because we are trying to push on this kind of R&D projects. So 10 minutes is quite short, so I get really fast on everything. So the good thing is we have time to discuss. There are coffee breaks, poster session, anything. So you can either reach to me or my colleague Anne Dubois, which is in the room with a white shirt. It's written Earth Daily Agro on it, so it's pretty easy to find. And we will be happy to give you more answers, more details, and try to see how we can work together. Thanks a lot.
Thank you very much, Harold. Very interesting presentation. And we move now to the 7th talk of the afternoon, given by Johan Barbetot from Planet Labs. So that will give us an insight on land surface temperature retrieval from synergy of passive microwave, optical, and thermal observation. So please, Johan.
Thank you. So good afternoon, everyone. My name is Johan. So we're going to take a little bit of a different angle here, and you might know Planet for like optical data and the CubeSat, but here we're going to do something different. Like about a month ago, we launched like a new set of products we call Planet Variable, and part of this set, we have the lens first temperature. And today I'm going to explain like a little bit how we do that. So some names of my colleagues where some of the results coming from, but also there is a lot of software engineers and many hours of coding there. So just a little bit of a context. We've been using the lens first temperature into some models already where we deliver soil water content, so-called soil moisture 2, and yield forecast to our customers. And we keep doing that. But we want to explore further. So this is why we launched this new lens first temperature data set, because we want to explore more applications such as like evaporation in the agricultural market or crop health monitoring, and we've seen that already today. But also heat and cold monitoring, and for that we can use a long time series and archive. I will explain that, and maybe also urban heat islands or like monitoring. And based on the great talk we had today, maybe there's collaboration to do like the tipping queues on this kind of thing. So this is how we can combine data here, the idea of fusing all this information together. So currently what we have like two data sets, one at 1 kilometer with like 20 years of archive using the microwave signal. So it's a bit different because here we'll use the thermal a bit later, and we have like observation every day or close to every day, and we have 2 observations a day at 1:30 a.m. and 1:30 p.m. We also have a new product which is 100 meter using a downscaling approach with Sentinel-2 near and sway bands. And we have an archive about 5 years, so since 2017, and we have also 2 observations a day. I want to highlight here that actually we make use of microwave because there's some advantages. First of all, we don't have the cloud issue. We have every day, we have data coming in, and we know exactly when it's going to come in, so our customers, they get a value. So this is a pretty good advantage because also we can have a consistent data set around the globe. And we do that over the last 5 years at 100 meter and 20 years for the 1 kilometer. We've been talking about latency. So we have like currently 24 hours near real-time feeds that's currently running. We can deliver the data already. And we even have like less than 6 hours for the 1 kilometer product. And to do that, we fuse different data sources. So I explained that earlier. Long-term series, been talking about it, and we compare the data, again, ground sensors, other satellite data, such as MODIS, Landsat. So this is a little bit about the methodology. So the idea of the downscaling here is that we use a microwave, and microwave is a footprint, and they have a large footprint, so we need to use a downscaling approach, which is described at the bottom. The idea is just to use overlapping footprints together, and we add also the information from Sentinel-2 data to downscale to 100 meter. We could actually go a bit higher resolution to 20 meter. Currently, we're exploring the 100 meter one for obvious sense of cost of processing and storage when we want to process global and we want to have low price for our customers. We have to consider all of that. So here an example of an area over the Netherlands. I believe this is the day I made the slide, so that was about a week ago, 10 days ago. But as I said, important thing is also to validate our data. We've been all talking about validation, calibration. We know that microwave signal come with some uncertainties also. We really wanted to understand that in details. So we've been validating our product across the US, and because we have 10 years of data, we took only the last 10 years, we could validate nicely the time series. So here it's a comparison against like Surfrad. I've seen in the presentation before, they're also using it. It's 7 stations across the US. It's very well known and very well used. So we can see some differences when we compare with MODIS. So it's a like for like. That means we only consider when MODIS observation is available. So like in the clear sky condition, we can see we can still improve our algorithm to reach for us a 2 Kelvin accuracy. So, but we're getting close, and this is the first version. But if we look across more conditions, landscape or climate conditions, we can have like an uncertainty close to the one of MODIS. This is what we're trying to do. So here, this is some results. We are working on finalizing all of that because it's a lot of numbers. You can imagine 10 years of data. We want to understand exactly what's going on. That will be published soon. But what is very interesting is like all the thermal data we currently have available, we can also look at the data like on the direct information for our customers. So if they say, hey, can we have this information? So here it's a random point near my hometown, and just like the same when I prepared the presentation, it's like how we're going to compare against MODIS. So this is an example here. We can see some differences, but what is interesting that we see we have like a lot more information, a lot more valid observation with the product at 1:30 in the afternoon, and we're at 100-meter resolution. We can also compare for the same resolution, which is at Landsat resolution, but we have a time difference, so it's important to consider in the statistics as well that, yeah, it might be a little biased because we don't observe at the same time. So we can do that across the globe, and this is why the thermal information for us is very important to understand and calibrate our models. We also do some exercises, obviously, because we downscale, so we want to look also at the spatial variability and how the downscaling method works. So to do that, we compare our data against Landsat. It's a snapshot. Here, the main challenge is getting a clear sky Landsat data over a large region. So here it's an example. We have a little corner cut on the right side. This is a Landsat image. The image that's full, it's us. And to avoid like noise in the comparison, these kind of things, we work mainly at the field scales. So we look at all the pivots. This is irrigated region. We selected a random number of 300, and we compare them spatially. And this is kind of result we obtain, and this is showing that the downscale approach makes sense. But we can also look at a bit more complex area where this is rainforest agriculture over Germany. Same, we selected X number of fields, and we also compare and we extract the same statistics. What is very important here is like now we want to do that in a more global way. Those data sets are available, and maybe we can provide uncertainty layer to our data set. So here what is important, it's just we want to give the information that we can combine all this information together, because the thermal, we bring the accuracy. We've been talking about that already all day. But the microwave signal can give us a consistent signal over a long time of period. So we can also relate all the temperature of today compared to the past. And this is something very interesting. Many applications, let's say if we look at the insurance market, they want to know like maybe other things, or in the yield forecast. So currently we use AMSER-E and AMSER-2 mission. We're trying to ingest now the GMI, so it's also a microwave mission. It's like currently a backup because we need to provide our customer data every day, so we need to ensure that we have a data feed every day. And we're looking also forward for the next coming mission, AMSER-3 and CMER that we've been seeing this morning during the first presentations. And also because of Planet, we have like a PlanetScope data at 3-meter resolution with a higher frequency of observation. We will only improve the spatial representation of those. And then obviously the thermal. So here I mentioned some of them, MODIS and VIRS and Landsat. That could be the first start for us because we want really to fuse this information of thermal together to get the best LST possible. And then all the upcoming mission already we will prepare for that and get information. So the first step will be add a quality layer using thermal data, because then we can provide the right information to the customers and the users. And this is what we call for us at least LST analytic ready. The data is there every day. Now it's up to the users, you to use it based on the different filtering you want to do or the different information we get. But also by including thermal information, we will improve the accuracy. And also using PlanetScope and the future PlanetScope missions with more bands and more information, we will also go towards higher resolution, so towards like 20, 10, maybe below this resolution meter, sorry, because yeah, this is what the users are going to tell us based on what they need. Obviously, this comes with cost. I don't know about time. This is my last slide. So yeah, we will have time for questions after the session or even during the coffee break. And if you have any question later, please, you can write an email. And the information will be also available online if you need more. Thank you.
Thanks, Jean. We arrive at the last talk for this session. Last but not least, we're going to welcome Wim Bastiaansen to talk about thermal SmartSats for gap-filling agricultural information services.
Thank you. And it's a real pleasure because some 25 years ago, high-resolution thermal was almost dead, you know, so now it's rocking, and I'm very pleased with this development. The purpose of my talk is to try to convince you of the need of thermal smallsats. So if you have listened very well to the talks before, I hope you are already convinced, and I don't need to give additional arguments for that. I think these thermal smallsats can really fill the gaps, and therefore my company AreaWatch is working together with Hydrosat. We really want to do this together, so I want to acknowledge here also my co-authors, Royce Delby and Josh Fisher. So, digital services to agriculture that we talk about a lot. It started some 15 years ago. You had providers of weather stations and soil moisture sensors, and suddenly they started on selling imagery to farmers. Okay? And then these farmers, they all got very excited because they got an NDVI image. I think NDVI is from 1969 originally. But the farmers are very happy because they could see all kind of variabilities within crop. But that did not last very long. In fact, now most farmers, they are less interested because they see that once the crop is covering the soil, when the crop is in generative growth stage, NDVI is not changing much. So they're really looking for something different. When I show them the thermal imagery, then they really get excited because they understand very well that if the crop temperature is almost the same as air temperature, then there is no stress. So it's very easy to explain. In fact, it's much easier to explain than an NDVI. Okay? So here is an example from Spain where actually farmers are using more and more thermal imagery on a daily basis, and they are very happy about it. But here comes something that, Gascon, I think you got compliments here because you created 10-meter spatial data. So when I show a thermal picture of 50 meters, these farmers are not happy. It's a bit like I'm getting a new camera, but this camera is not as sharp as my old camera, you know. So farmers really are very keen on getting super high resolution thermal images. So why is that? Well, because many factors control crop growth, plant development, and we talked already about it on water and light and disturbances and nutrients and everything. And really, this is very important because the temperature, and especially if we can bring it to a leaf temperature, you know, then we really know whether the crop is healthy. And so that's a very important thing. Now, then why every day? Well, if you go for drip irrigation, if you have invested all that plastic pipes on your land, then actually you really want to use it well. And many areas now, they are getting irrigated that before were not. So these are marginal land, sandy soils, not very fertile. And then if you want to bring the water there, you really have to do it every day. You have to do a measurement. Sometimes this root zone can only store 20 millimeter, 22 millimeter, if the roots are shallow. So if you don't irrigate on time, your crop is gone. So really you have to go to daily steps. But also 10 meter, because you know, those drip lines, they will be rolled out every 5 meters. If you go to sprinklers, they have every 10 meters, you know. So we really have to go to this kind of resolution. Also drainage, if drainage is there, if the crop is not having oxygen for 3 days, it's dead. Okay, we have to have daily imagery. Crop diseases, if you wait too long, then really the crop is gone. If you want to have just the right moment of sowing and planting, you have to know your moisture, the temperature in the soil, that you make the right decision of doing it. Pollination is another thing. And also, I want to mention water allocation and water compliances. Many countries are more tight in water. There are water rights in place, and they have to be measured. Farmers, make weekly plans, make weekly irrigation plans, and they really want to know, do I not exceed the amount of water that I'm supposed to give? So these are all arguments why we need the thermal data. The other aspect of the timeline of thermal data is the diurnal variability. And I'm showing you here from southern Portugal a thermal image from Sentinel-3 and from VIRS. There is a difference in about 2.5 hours. And today also we hear that 12.30 is a very good moment to measure stress. Yes, I agree. But that is not very likely to be the good moment to have the average stress for the whole day. You know, you can maybe overshoot on your stress level. So we've done a lot of studies comparing the relative temperatures on Sentinel-3 and VIRS just to find out what the differences are. And actually what you can see here is that, yes, many agro-ecosystems have the same thermal regime, the same thermal behavior, but you know, not always. You always find places where things are different. And that is very much related to you know, generic crop physics. So the stomatal conductance is changing from hour to hour, depending on light, but also depending on VPD, but also on the speed of moisture transfer within the crop. If the speed is a little bit low, then the moisture is not reaching the stomate. Plants will feel it, immediately the leaf water potential changes, and so on. So it is really important also to look at within daily variations. Shadow is another element. Now, there's a lot of impact of sun, and actually you always capture some shadow. So if you can measure on different moments of the day, you know, that would be very lovely. So yes, we all know that we have certain systems in place. We have the geostationary ones that are very good in the time domain, but bad in the spatial domain. We have the Landsats and so on, the ecostresses. And the good thing is we get now all these new extra sensors coming up. I'm looking forward to the year 2028 or 2029. You know, things are going to change. But still, I think that red dot is there, and I believe that's the red dot where also really the small sat companies can come. Kevin already had a very nice presentation earlier today on 50-meter thermal, 10-meter visible near-infrared, which means we can sharpen. We have to sharpen anyway. I think many of you here already do this in a practical way or for fun, but thermal sharpening is a really kind of must to have this data on time and in a high spatial resolution. So with that, you can have much more time series of thermal imagery, really, you can much better do the job. If you provide a weekly ET image to a farmer, he will run away. Okay? You really have to give them daily updates on very specific things. So we are also working on proxy data. I think the term was used before by others, and we do the same. We also look at VIRS and Sentinel-3, and we use Sentinel-2 for downscaling, Landsat, ecostress. We use a lot of ecostress images. I'm very happy, you know, all the bands are back. Ecostress is fantastic, and it works really everywhere in all the countries we work. We work, by the way, in 62 countries and bring really this LST data product to users. So a few messages. This is really a thermal comeback, and I'm really happy that this is happening. If we look at visible near infrared information, this is absolutely not sufficient. So many commercial companies have started using NDVI and other indices, and they're stopping with it. It's not a viable product, okay? Because if you really have to wait until the colors are changing, your vegetation indices are going down, then your crop is already, you know, dying. So thermal gives you immediately a signal something is going on. And farmers really, they like it. You know, they are open to it. There's not a big sales pitch needed. You know, they know that if their body temperature is low, everything is good. And if the body temperature rises, something is wrong. And, you know, you can easily explain that same as the crop. They want really the 10-meter data. You know, we have to think about that. So, absolutely fantastic that we have 3 musketeers lining up to help us on this gamble. But I think they also need some soldiers, some extra help. And I think the thermal small sats can help filling that gap. Thank you.
So we would call the speakers to come here to the scene. We'll take a few questions before we go to the coffee break.
Any questions? If not, we could just start with just anyone can comment, like how do you see the private industry role in terms of this future of like government-based global survey, global coverage, thermal, how can two like complement each other? Anybody welcome to comment? Or nobody? What's the role of commercial? Oh, there are questions? Oh, I'm sorry, we didn't see that.
It's a question for Tobias, actually.
Yes.
You showed, I'm here.
Thank you. Yes, hey.
You showed that you will probably have 25 meters accuracy with your system for now, and you planned to be a sub-pixeler. When do you guess, you propose is going to be happening that you're going to have like an accuracy that is precise?
Precise to sub-pixels. We're hoping that once we've launched and understand the error margins of the actual telemetry of the satellite coming down, it'll take a few months, maybe 6 months for us to actually characterize that and have sub-pixel available.
And this is after refinement, or is this going to be native? Because if it's native, it's...
It'll be with refinement, but based on evaluating a model that we can then not do manual stuff every single time.
Okay, all right, thanks.
Thank you.
And will it be available to the early adopters?
It won't be early anymore in 6 months' time. It'll just be perfectly normally commercial, so
okay.
Yes.
I have it already. Shall I start? Yeah. Thanks very much to all. Very, very interesting and exciting time, I think, all these forthcomers. I have many questions, but I just focus in one of the missions. On the HydroSat, maybe. Kevin, a question for you. Thanks a lot for showing a bit more details of your budgets. It's very, very interesting. Just to understand, just a question maybe on the overall absolute radiometric accuracy. You seem to suffer from stray light, if I understand correctly. In your radiometric budget, you include the absolute radiometry with and without stray light. Where does this come from, and how come it does not destroy your budget at the end?
Yeah, so correct, we have a placeholder right now for, I wouldn't call it a worst case, but a moderate expectation of our out-of-field and also some crossband stray light. So if we looked in a bit more detail at our filter stack, there are some potential paths there. We're including it to be conservative in that top level roll up because, for example, Tiers 1 had some stray light issues to contend with. Eventually they were able to solve it. We would hope to do similar. But right now we're keeping that number as a placeholder.
Okay, all right, I understand. Maybe a follow-up very quickly. You present also your MTF budget. It's something that we have not seen very often on the other small missions.
Sure.
Just to understand, you accumulate 90 TDI samples?
Correct.
And is this MTF budget includes the stability during this 90 TDI samples acquisition?
I would say, to be fair, we have not run all the way through platform stability, including that TDI number. We've looked at some high-level bus pointing performance and believe, it's in the realm of possibility to collect all those 90 frames in one go. If we have to, we can dial that back a bit and say stack.
I see. And your value was for the 50-meter product or for the 70-meter precursor?
70-meter Pathfinder, we would expect similar performance radiometrically at 50-meter Constellation GSD.
Okay, but the MTF was for the 70-meter that you showed, yeah?
Correct.
Okay, thank you.
Thank you.
Let's take one last question.
This question was really for Wim, or it was a comment. You mentioned the need for sampling the minimum maximum throughout over the day. And interestingly enough, when we get LSTM Trishna and SPG, we will actually be getting the first ever sort of thermal inertia data set as well, because we'll be getting daily minimum and maximum. And that's something that we haven't really started looking at yet. Philippe was talking to me about it earlier today.
Okay, and what time is that? Is that really very early morning, like sunrise, or mid-morning, like Landsat overpass time?
It should roughly match the sort of local crossing time.
Okay.
So it would be, 12:30, 12:30.
Right. Yeah. Oh, that's super good to know. See, every biome is responding differently to weather and soil moisture dynamics. And what we found out is that certain systems really have, for instance, a higher evaporative fraction, was mentioned a couple of times. So some of them have a higher evaporative fraction in the morning. Other agro-ecosystems have a higher evaporative fraction in the afternoon. So I think it's really depending on how ecosystems are adjusted to the climate, how the crop is responding. There's a lot of breeding going on getting more drought-resistant crop varieties. And so I'm really still a very strong supporter of having multiple day thermal acquisitions.
I think we'll conclude this session and thank all the speakers here. You can continue the conversation over coffee break. Thanks, everyone.
put there. So, please, I would like to ask everybody, please, if you could take a seat. So, good afternoon, everybody. So, may I have your attention, please? Welcome to the last session of the day. After so many interesting talks, we are just heading up to the last ones. I hope you still can bear with us and keep the attention to the end. We are a bit behind schedule, so we will start now. And we will really ask the presenters to keep their time so we can go finally to our drinking time. I will present myself. My name is Iciar Barat. I work at TISA. I'm the LSTM System and Operations Manager. And together with me is Jean-Louis Roujan.
Yes, thank you, Iciar. I'm honored to co-chair this session. So I'm Jean-Louis Roujan. I am CNRS Senior Research Scientist. I work at CSBio in Toulouse in France, and I am PI of Trishna mission. Actually, I am first speaker, so Can you hear me? Okay, yes, that's much better. Thank you. So good afternoon, everyone. And it's a long day. So I realized actually the title of my project is Tiramisu. Roma is a perfect place for that, for sure. And you can come to question when you come to the dessert, if you like or not the directional effects, but I hope you think about this project. So I'm going to talk about directional effects in thermal infrared. We already talked this subject this morning. Actually, what's all high-resolution TIR mission will observe the data. Orbit path will be in the middle of the day, and already mentioned this morning, we have some observation will be in the satellite will be aligned with the direction of the sun. We will have some hotspot effect. You can see on the bottom left in the visible, this creates some peak of light. You cannot see exactly because of the shadow here, but this is a really, really important peak of radiometry. Of course, you can see the visible. You cannot see in the thermal, but it's the same in the thermal. So we need to cope with that. So we have different options. We need to characterize, we need to model, and we need to eventually discard this data in the hotspot. And so we need to define a strategy clearly. And so actually what we need to characterize better the hotspot. We need also, and because in the thermal it's poorly explored compared to optical domain. And so some historical background. So we have actually different approaches. We can have 3D modeling. We can have 1D modeling with sophisticated model like SCOPE. And you also have some parametric model, which is only candidate to efficiently remove some directional effect from the data because they are fast to compute and they are not very eager in terms of parameter to adjust. So on the polar graph, you can see actually there is good matching between the measure and the parametric model, so-called Roujan-Laguarde model. So actually, recently, we tried to define a framework how to correct directional effects on the images. And so it's pretty simple. We start from the fact we can have sunlit or shaded pixels for vegetation and soil. And we define what we call the kernels. And we have one kernel for hotspot, we have one kernel for emissivity. And when we add both of them, actually, we combine somewhat artificially. We can have a signature with some hotspot effect. So actually, the hotspot depends really on the density and the structure of the canopy architecture. You can have the top left, you can have something very dense, where so you have very sharp hotspot. And you can, the bottom left, you have something more sparse canopy. And in this case, the hotspot is pretty broad, and you don't have so intense peak. But that's a problem that most of the time you don't know about the specificity of the target, except if you know about the BRDF. So actually, another experiment, we tried to characterize the Echelle effect on the same area with different kind of targets. So this is an experiment what was conducted in China. And what's going on actually, if you look at maize, other crops on forests and so on and so forth, in the middle here you have, what we call directional anisotropy index. That means the difference between nadir and in the different direction. So you can see you have by several degrees, and if you compare to absolute value of the temperature at the top, at the bottom of the image, you can see you can have error by a few percent in a relative unit. So other thing, some quite popular index is called TVDI, and combine NDVI and land surface temperature. And the question was, there is some compensation balance between hotspot between NDVI and LST, and the answer is no. It's still there, and the people they use some contextual approach, and which is quite popular. You can see still you have hotspot there, but you can see a different directional signature between dry and wet condition, which is quite interesting. We show actually this is a good index. The scope model, we use scope model to perform some simulation. Most of them you know in the room, this is also a model of reference for the FLEX mission for fluorescence. And we use this, I would say, abusively also to prepare the Trishna mission. So what we try to look at, scope, we took which parameters are really driving the signature of the hotspot, and one of them is the wind. So it's good and bad news, because most of the time you don't know about the wind in the canopy, because it's very linked to the air circulation and the turbulence. But you can see actually the peak of the hotspot has a different intensity according to the wind intensity. We look also from with scope different the directionality of emissivity for Trishna bands. So here you have 4 Trishna bands. The top is a low LAI, so you see mostly emissivity from soil. And the bottom LAI is high LAI, so you don't see the soil. And you can see actually if for different bands you have different results. And you can see the hotspot really on emissivity also if you have high LAI is the case. So actually we need to be prepared for that. That's from scope. And we know with the parametric model we are able now with the kernel approach we are able to simulate this. Now I really come to the dessert. Actually, that's a starter because this is project which is just starting now. So we tried to go. We went to the field last year, and it was a perfect year because we have a lot of stress. There was one wave in the south of France, and we look at we organize some field campaign. So actually, we design a system. So we have a thermal camera. And we have stacked on them. We have also optical camera, and this camera is moving. So very quickly in a few seconds, so you can capture the BRDF. And it was set up on a maize crop, and you can see it from May to July and August. Of course, it changed very quickly. It was not irrigated. It was a dry maize, not irrigated. And actually, we did perform different kind of measurements. We have UAV flight. We measure LAI. We have tetraprobe to measure the soil moisture and soil temperature, and also we have AFD to measure actually the spectral signature. So yeah, so we are able to pick up the hotspot actually in the middle of the day as it is foreseen to prepare the future mission. And yeah, so thanks to our partner from ONEA and José Subino's team from University of Valence, we are able to measure emissivity continuously for covering all the thermal spectrum. And actually, we see that we have different emissivity depending on the corn, the leaves, and different elements of the canopy and the stem. So that was quite a result. And also, it shows the spectral dependency of emissives. So we think that's a really good amount of data. About the mockup, I do a mockup because we wanted to have a 3D. So you just simply put white sheet at the end, and you look at the projection, and that's the way we are able to build a mock-up, because we need to build a mock-up to have 3D depicting of the canopy, maize canopy, and this is what we did. So this is the mock-up, so it's a lot of work, especially when in heat condition, you have to measure not leaf dimension, but almost. So, and we also put on this image some, you see in red, that's aluminum plate. They serve to anchor points for azimuth direction. And so you can see the mock-up from that in the thermal, and you can see different bands which match with Mica Sense camera. So this is the real data. Top is the LST, and bottom is different bands. And this is different sequences. So you can see actually on the hotspot, because you can see the shadow of the camera, of course. On the ground in situ measurement, you always have the shadow in the hotspot. That's a problem, except for the satellite. But the idea is to have a shadow mask. And so you can see the brightness, which is interesting. So there is really hotspot. And you calibrate this with DART, for instance, and DART will give you the real hotspot. This is what he did, and actually we performed a good comparison. We had really high temperature there. So you can see up to 60 degrees. This is because emissivity was wrong at that time. So we need to correct for emissivity for soil. But actually we had, that was the first step. We still work to try to co-register the images. This is long technical work, but it was good hope and between comparing these two systems. So another interesting thing, another spot in Guyana, which is this is Calval site between biomass. Also, we up really for Trishna, and you can see the antenna for radar. We set up a fixed system camera optrace, and we try to look at the NI cycle. So it's almost at the equator. So I mean, always the same story, except you have a dry season and you have a wet season. And interestingly, we see that a peak. And so we try to isolate in the field of view of the camera different sectors, different elements. And we notice a peak of the radiometry, I mean, of the temperature in the middle of the day. And we diagnose this with a scattering angle, because when you have scattering angle cosine, which is 1, you are really in the hotspot. And you can see actually the hotspot, we can measure the intensity of the hotspot was almost 4 degrees in this case. And if you really change a little bit the scattering angle, of course, you go back to something which is less contaminated by the hotspot. So this is quite interesting, because we need to define for this future mission with a strategy to try to discard or not hotspot, and to define an area of angle in which we could still consider the data or not according to the hotspot. So I came to my conclusion. So try to define a new experiment which was able to capture simultaneously and continuously the Venir and also Tyr hotspot. And what's confirmed that's the existence of directional effects. And also I refer to the presentation of my colleague Julien Michel, which show about results from collaboration with NASA between MASTER and Landsat and EcoStress. So we've gone on the way to monitor the stress, try to discard the directional effect, really detect stress. So we can also track the hotspot. You can also, if we discard shadow pixel from the camera, we'll be able to calibrate with DART. DART will give us the real hotspot, what we need to invert a parametric model. And also, we too found some interesting relationship between vegetation indices, LST, and land surface emissivity. The next step will be to have the same tiramisu experiment starting in India next month about paddy rice crop, and in Ahmedabad in collaboration with ISRO. And really, my feeling that more research is really needed about the directional effects if we really want to guarantee the success of our resolution Tyr mission like Trishna, SBG, and LSTM. Thank you very much for your attention.
Thank you, Jan-Louis. So our next speaker is Louis Snyders. He's doing his PhD in directional anisotropic corrections and evapotranspiration estimation for thermal infrared satellite imaging. So, floor is yours.
So I'll start again. My name is Louis Snijders, and as been said, I'm doing a PhD for VITO, which is a Flemish research institute, and the University of Brussels. It continues where the previous presentation left, so it's also about anisotropy corrections, and I'll first show you why we need them. Well, land surface temperatures retrieved from satellites depend on the sun sensor geometry. So, depending on the acquisition angle of your satellite and also the position of the sun, you will observe different values. As you can see from this rather simplistic simulation in DART, we see a scene of a forest on the left, and on the right we see the temperatures of that scene as if it's observed from different angles. What you can see is that if you start from the center of the plot, of that polar plot, and you move outwards, your zenith angle increases, and generally your temperature decreases. This is because the ground fraction that you observe decreases, and generally ground temperature is higher than your canopy temperature, and since you observe less of the canopy and more of the ground at a nadir position, you see higher temperature at a nadir position. Furthermore, at an azimuth angle of 225 degrees, you see a bright peak. This is the hotspot. So this is a position where the sensor and the sun aligns. So the reason that we observe higher temperatures in this region is rather logic. So here we only see sunlit parts of the scene and no shadow parts, and that's why we observe higher temperatures over here. So these directional corrections are definitely needed for missions that look at the Earth under large zenith angles, such as LSTM, but also for CubeSat constellations that would look under multiple angles or higher angles. This might be very useful. So how can we assign or correct these effects? We can make use of airborne campaigns. One such airborne campaign is the SWAT-SENSE campaign, which is a NASA-ESA airborne campaign set up specifically to investigate directional effects for LSTM. My research focuses mainly on LST, so I only look at the LST, and of the data set I use a sub-data set from Spain. So we collect measurements from Spain, both airborne and ground measurements. We need the ground measurements for a temporal correction, but I'll get back to that later. We use a thermal imager with a field of view of 40 degrees. This means that if we're looking from a nadir perspective, our largest zenith angle will be 20 degrees. So for this data set, we have 3 different days. For each day, we look at a field from 3 directions. We have one along the solar principal plane, we have one perpendicular to that plane, and then a third direction is the Sentinel-2 orbit track, if we have an acquisition before noon. If we have an acquisition after noon with our plane, then we take the LSTM track orbit. For each flight direction, we have 7 parallel flight lines, such that for a specific field, we have 7 different zenith angles for the same flight direction. We have multiple crop fields, but the most central field of our campaign is an alpha-alpha field, of which we also have ground measurements. So what is the strategy? Well, we select a field, we collect measurements from the 3 days, then we apply a temporal correction. I'll tell you in a minute why we need this correction. Then we separate a data set in training data and test data. Based on the training data, we build our directional model, and then we use that model to make our directional corrections on the test data. So why do we need a temporal correction? Well, because between the 7 flight lines, there is a time difference of more than half an hour. So between the first and the flight line in the same direction, temperature increases with, let's say, half a degree, approximately, depending on the plane. So this needs to be corrected because we're only interested in directional effects. How do we correct this? Well, we have some ground measurements every half hour. We can use them to plot a diurnal temperature cycle, and this diurnal temperature cycle can then be used for temporal corrections of our airborne measurements. So this is what I did, and then we can build our parametric model with the corrected data. So how do the parametric models look like? We have an isotropic part, we have a base shape part, and a hotspot part. So the isotropic part is independent of the sun or the viewing angle. Then the base shape part only depends on the zenith angle of your sensor. If your zenith angle increases, you observe a smaller ground fraction and your temperature generally decreases. The hotspot part only depends on the angle between the sun and the sensor, and it tells you how much sunlit parts of a particular scene you observe. The coefficients or weights need to be estimated based on observations because they tell you to what extent each part of that general model plays a role. So we can do this based on our training data, and then we get 3 different models. So actually, parametric model can be used to combine combine a hotspot function and a base shape function. The first one is a base shape designed by Vinnikov. Second one is a base shape called Listrauer-Friedel. And then the hotspot is described by Roujon-Lagarde, and for the second one, Chen. The third model is relatively similar, only here we make some assumptions about the geometry of the canopy itself. So we can select one of those models and use it to correct our test data set. If we do this for our different planes, we get the following results. So you can see the different directions of our plane, and you can see the results before and after the directional correction. I also included a target accuracy for LSTM of 1 Kelvin, such that you can see immediately that the directional effects are rather limited in the first place. After correction, there is an effect, but it's difficult to assess the accuracy due to the limited effects that are present. Why are these effects limited? Well, because the airborne campaign shows only data zenith angles up to 18 degrees, which is rather low considering that LSTM might have angles up to 35 degrees. We also have no pure hotspot observed, so there is no observation where the sensor and the sun are perfectly aligned. This makes it also very difficult to accurately predict the hotspot parameters. And this also causes that we have no significant parametric model outperformance because it's very difficult to see the directional effects because they are limited. How can we solve this? Well, later this year, there is a new SWATSense campaign planned where the zenith angles will be up to 36 degrees instead of the 18 degrees that we saw before. So this will definitely show us the directional effects to be more expressed. And furthermore, we will also look at the field geometry because row planted crops can have an effect on directionality as well. So that's it for me.
Okay, so next speaker is José Sobrino for University of Valencia.
Yes. Okay, this presentation, the idea is to the assessment of land surface temperature methods for future high-resolution thermal emission. This is the structure. Well, in first time we present the algorithms, then we use also the LIAISE campaign in order to obtain syntactic images with which we validate the algorithms. And finally, we also obtain the evapotranspiration. Regarding the split window, 3 different split windows has been proposed. Becker and Lee, and Guan and Dossier, the global split window, and one algorithm we developed some time ago that includes explicitly dependence of the water vapor absorption and also the emissivity. Also, we apply the temperature emissivity separation algorithm, very well-known algorithm, developed by Gillespie et al. In 1998. And in first time, we apply this algorithm, but to do that, we need to do some simulation, and for this, we use the instrumental spectral response function of Trishna and LSTM. Trishna has 4 thermal bands, and LSTM, according to the mission requirement document, has 5 thermal bands. Okay, then in order to obtain the coefficient, we use Mothran simulation using the global atmospheric profiles derived for analysis information, the GAPRI database we published some time ago, also emissivity from EcoStress library, and 7 surface temperature simulations in the range -15 +15. In total, we have more than 7 million of cases. You can see here the GAPRI dataset and also the water vapor dataset distribution. Well, from this, we use the best combination of channels to estimate the LST from split-window algorithms. The best combination for LSTM is to use the channels 4 and channel 5, and for Trishna, channel 3 and channel 4. This is the numerical coefficient for the 3 split-window algorithms. And also, we use EcoStress spectral library in order to obtain the correlation between mean and the maximum minimum difference, the spectral contrast. In this case, we use 3 different possibilities: the 4 thermal channels of Trishna, 3 channels of LSTM, and all channels of LSTM. Well, in order to obtain synthetic campaign, we use the airborne images obtained with TASI, a sensor, a push-run hyperspectral thermal sensor system, in the study area of JEDA, the LIAISI campaign in 2021. And from this data, we obtain, applying TESS algorithm, the LST and LS, and the land surface emissivity, that in both cases, we have validated this estimation using in situ measurements, using multi-band radiometers, a diffuse reflectance plate to address atmospheric Doppler effects, and the broadband sensor, 840 micrometers. What the validation for the 2 days is good in terms of temperature is between 1.2 Kelvin and 0.9 Kelvin. We also validate the land surface emissivity estimation using the TESS algorithm by comparing the in situ measurements with the thermal radiometer and the TASI emissivity, and the results in the most part of the situation are around 0.01. Well, from this data, we obtain synthetic images from the TASI level 2 images. This image has been generated using the EcoStress library, because TASI cannot provide values above 11.5 micrometers. And also, we use with these land surface temperature images, plus the simulated emissivity, plus atmospheric parameters, we can obtain the transmissivity, the upward and downward radiance. And finally, we can create the top of atmosphere radiance by the application of the inverse radiative transfer equation and Planck's law. And of course, we take into account the filter function of LSTM and Trishna to this TOA radiance. Well, this is an example of LSTM synthetic images for the 5 thermal channels retrieved from the LIAISI campaign on July, and the same has been done by Trishna. Well, when we have the synthetic images, we can apply the algorithms. In order to apply the algorithms, we consider that the TASI LST image are our ground truth for temperature and also for emissivity, and we validate, as I say, the TESS and the split window algorithm. This is some example of the validation of synthetic images for LST for the 2 days. You can see here the land surface temperature for LSTM, considering 3 thermal channels, 5 thermal channels, and all the thermal channels of Trishna. The range of validation is between 0.2 and 0.7 Kelvin. This is the validation, but for land surface emissivity, considering only the 3 thermal bands of LSTM, and the range is between 0.011 and 0.016. The same for the 5 bands of LSTM, and the range is a slightly better result than for the 3 bands configuration. And here we show the test validation of synthetic images for land surface emissivity using the Trishna thermal bands with land surface emissivity range between 0.010 and 0.023. And finally, we show the validation of a split window using the synthetic land surface temperature LSTM images. The validation of a split window against the ground truth images range between 0.7 and 1.4 Kelvin. And there are minimal validation with the land surface emissivity. There is not validation if you use the emissivity from the test algorithm applied to the TAS images, or if we use the emissivity measured in ground. Was the same for the split window for the Trishna images. Minimal variation below 0.1 Kelvin when the LS land surface emissivity is ingested from test algorithm results. In conclusion, this is the validation summary for the split window for the 2 days analyzed. In general, similar performance for LSTM and Trishna synthetic images are obtained. The first algorithm, the split window, show similar result and show the best results. And the higher root mean square error for the global split window algorithm in all cases. And this is we show that there is not important difference when the test emissivity inputs are applied to a split window instead of simulate emissivity values. Okay, then we move to the evapotranspiration. We have applied the SSAB algorithm, very well-known algorithm, and then we obtained the SSAB using calculating the albedo from the CASI bands and the solar radiation from the CMWF. In this case, we obtained the instantaneous evapotranspiration. The first images is from the original TASI with a spatial resolution of 4 meters, and then using the synthetic LSTM and Trishna images. For LSTM, we have considered the 3 and the 5 channels using 40 meters, and for Trishna 60 meters. And also, this has been compared with eddy covariance data available with average every 10 minutes or every 30 minutes. Here we show the plot of the representation between the eddy covariance measurements at the evapotranspiration obtained by TASI, by LSTM 3 channels, 5 channels, and by Trishna. And also when we use the eddy covariance data of 10 minutes, the result are worse in this case. Also, we can estimate the daily evapotranspiration. We convert the eddy covariance data to daily values in millimeters per day for the 4 cases. In conclusion, we observed that the difference between the eddy covariance and the comparison with TASI, LSTM3, 5 channels, and Trishna synthetic images are very similar and always are below 0.4 millimeters per day in this case. In conclusion, different split window algorithms and MMD relation was estimated for LSTM and Trishna filters and were proposed for both missions. Synthetic LSTM and Trishna images of land surface temperature were retrieved using validated TASI data, eco-stress emissivity spectrum, and atmospheric profiles. And the test LST validation show good results for all sensor and configuration below 1 Kelvin. And of course, when more channels are introduced in the test algorithm, better results are achieved. And the emissivity values show minimum difference of 0.1 independently of channels and sensor considering. Regarding the split window validation, in general, the uncertainties are higher than for the test algorithm, but are not important different when the land surface emissivity inputs come from the test algorithm instead of simulate LS data. The SSAB algorithm validation has shown results between 55 and 75 bytes per square meter with no significant improvement when different sensor or algorithm is considered, and the conversion to daily evapotranspiration value provide good agreement against in situ data, being the root mean square error values lower than 0.4 millimeters per day. That's all. Thanks.
Our next speaker is Emily Telogu. She is working at CNES and in charge of the development of the level 2 algorithms for Trishna.
Thank you. Hi everyone, and thanks for having me today. So I will talk about the different algorithms that are under study at CNES in order to retrieve surface temperature and emissivity for Trishna. First of all, to begin, a quick reminder on the problem we have to solve to retrieve surface temperature and emissivity. This is a non-deterministic process, and for any spectral band for any given sensor in the thermal infrared, what we know is the TOA radiation that reaches the satellite, in green in the equation, and the 3 atmospheric parameters in blue that will be computed with an atmospheric transfer code, which will be R theta for Trishna. And what we don't know when we want to access is the surface emitted radiation, which depends on the surface temperature, and the surface emissivities. So we have k+1 unknowns and only k equation. So we need to add information in order to solve our problem. Different algorithms are classically used to retrieve surface temperature and emissivities, and among them we have a split window empirical method that relies on measurement in 2 adjacent TIR channels in the 10-12 micrometer interval. The hypothesis under the algorithm is that most natural surfaces have a flat emissivity spectrum in that domain. And these algorithms are commonly used over oceans to compute sea surface temperature. These algorithms need to be calibrated at first, and a priori information on surface emissivity. Test algorithms were initially developed for Aster sensor, and they rely on an empirical relationship between spectral contrast and the minimum emissivity of the observed spectra. The hypothesis is that over 3 channels in the TIR domain, at least one value is close to unity. These algorithms need atmospheric correction at first and are not adapted for surfaces with low spectral contrast emissivity, such as vegetation or water. A third algorithm is direct test and developed at CNES. And these algorithms rely on a spectral database of emissivity. And the idea is to calculate the lens surface temperature for each pixel and each material of the spectral library. And if temperatures are consistent for a given material in the n spectral bands, we consider that the material is relevant, and so is the temperature. We have, with direct test, the possibility to add visible information in order to get rid of the obvious non-consistent material. And direct test needs also an atmospheric correction at first, and strongly depends on the spectral library that is used. Here is an overview of the different chain we like to have for Trishna. So overland, the chain is called TrishTest and is made of atmospheric data and radiative transfer computations, which will be done with R theta, as I said, and then with the temperature emissivity separation algorithm, which will be TESS or direct TESS. And over water, we'd like to use the same chain that will be used over land, but with only the direct test algorithm relying on a water emissivity spectra library, or a split window algorithm. And to make the choice for Trishna, we made different comparisons of these different algorithms, and let's begin with the result. We firstly compared TESS and direct TESS over end-to-end simulations where we managed all the surface reference data sets, all the atmospheric uncertainties, and all the instrument uncertainties. And over this theoretical data set made of soil, vegetation, water, and urban materials, with both sources of uncertainties, we got 0.1 Kelvin bias for direct tests and 0.3 Kelvin bias for tests over retrieval over soil and vegetation. The RMSEs were around 1 Kelvin for both algorithms. And when we use visible information into the direct test algorithm, we reduced the bias to 0 and the RMSE to 0.65 Kelvin. We then compared these two algorithms over actual eco-stress data, and to do so, we applied the TRISH test chain on eco-stress level 1 data in order to compute Trishna-like level 2. And then we compared this Trishna-like level 2 to eco-stress level 2 over 5 sites with evaluated uncertainties that were published in Hurley et al. In 2022. And here are the results we got. On the first graph on the up of the slide, you can see the RMSEs for direct tests with only TIR information in black, for direct tests with TIR information and visible information in red, and for tests in green. And on the second graph, you have the bias for the same three, and the eco-stress bias are marked in yellow. One must note that the eco-stress level 2 is very similar to our test results, because eco-stress level 2 is computed from RTTOV plus test algorithm. And we got RMSEs for direct tests that were stronger than for tests, but bias for direct tests that were lower than the one we got for tests. And the availability of only 3 eco-stress bands is not ideal for direct tests. We know that using 4 bands for direct tests gave a better result. I don't show the result here, but they were published a few months ago. We also made a comparison of the different algorithms in order to retrieve sea surface temperature, as following coastal areas is a design driver for Trishna mission. We compared the temperature of our algorithm to the temperature that were measured over Lake Tahoe, and these in-situ data were kindly provided by the GPL. So when we use the same calibration for tests and the same emissivity library for direct tests that the ones we use to retrieve temperature over land, we got the result you can see on the upper left and the lower left. So we got RMSEs around 0.9 Kelvin for tests and direct tests, and bias over 0.7 Kelvin for these two algorithms. And then when we use water spectra library for direct tests, because we know that we worked upon water, we reduced the bias to 0 on the lower right, and the RMSE to 0.65 Kelvin. We also applied a split window algorithm that was calibrated over RTTOV outputs over oceans. That was calibrated by Laura Orgambid at Ifremer, and she will talk about it tomorrow. But the result was not good. But there will be an issue because the split window was calibrated over oceans, and we applied it over Lake Tahoe, which is a high altitude lake, so part of the error may be contained in the altitude. To conclude, test and direct test performances for LST are similar, with slightly better results for tests. These results were evaluated over eco-stress retrievals, and we need to be careful on conclusions because eco-stress LST produced from RTTOV plus test algorithm. We made no comparison to actual in-situ data yet, and we know that direct tests can be improved with a multi-temporal approach to avoid ambiguity on materials, or with a better definition on the spectral library that is used. Regarding the sea surface temperature, the direct test performances are promising, but we need, of course, further comparisons with a split window before making a choice for Trishna. The interest to have direct tests for the SST is to process physical atmospheric correction, And what is under study is that we know that all the error comes from instrument and atmospheric uncertainties, so we studied the possibility to perform the inversion of a noisy atmospheric library in place of the spectral emissivity library, assuming water emissivity is known. And that's it. Thank you.
Thank you very much, Emily. I'm sure there will be plenty of questions, so there will be time for that. So the next speaker is Christopher Crawford. Yeah, please, Christopher, the floor is yours.
Thank you. Thanks to the organizers, the scientific committee, for giving Landsat the opportunity to speak at this workshop. The lead author here was unable to attend, so I'm standing in, but I'd like to thank our JPL, NASA counterparts, as well as the National Land Imaging, kind of representing the body of work here. So there's a lot to talk about when you talk about Landsat. So I'm going to try to provide a really quick, brief snapshot of past, present, future in context of thermal and infrared observations. Talk a little bit about the product that we're distributing today, where we're headed with Collection 3 at the end of the decade, and then just introduce very briefly the Landsat Next science mission concept. So Landsat's been making thermal infrared measurements, we all know this, since 1982. Interestingly enough, the instruments have sort of changed slightly over time in terms of their spectral response and their ground sample distance, but the current generation has converged where Landsat 8 and Landsat 9 tiers are nearly identical observatories with 100-meter spatial resolution. And then things continue to get interesting as we look ahead for Landsat Next, as the observational concept is going to continue to evolve, where we're planning to add measurements for emissivity in these critical wavelength regions. So our approach is that we do on-order calibration. We monitor instrument responsivity and stability using onboard blackbody. We also do per-orbit calibration sequences for cold, deep space looks. Our vicarious absolute radiometry is tied to the inland and coastal buoys where water is the primary target. And there's also a lot of other work that we do in terms of top-of-atmosphere intercomparisons using underflight opportunities with airborne platforms, as well as near-coincident observations and radiative transfer modeling to continue to evaluate and improve these observations. This is just a quick snapshot. So we're providing a level 1 calibrated product today. We're also then providing a level 2 surface temperature product, and then we've got to the point now at USGS AIRIS where we can do chain testing to run the products through higher level algorithms to kind of understand the sensitivities of the observations and the way the collection is processed. A couple of years ago, the USGS released a new collection, and so the thermal infrared global record is kind of a key part of Collection 2 that was never available until the past couple of years. So this is a relatively brand new global data record that hopefully is going to be exploited by this community alongside these other wonderful missions that are coming. The observations represent Kelvin in terms of units at the surface. I'm not going to go through the applications. We already know that. One of the things I really like about this product is that it has uncertainty built into, so you can evaluate the retrieval sensitivities along the processing chain. This is a really strong aspect of this. This product is also endorsed by CEOS, Analysis Ready Data for Land, which we're proud of that at the USGS. We use a single channel radiative transfer. There's one common channel across all Landsats, Landsats 4 through 9. We decided to go with this particular algorithm, radiative transfer-based algorithm that uses atmospheric real analysis to characterize the state of the atmosphere. We then use the ASTRA Global Emissivity Database with some temporal adjustments to bring that database up to the present with Landsat. And then we plug all that in and solve for the surface temperature. And so that's sort of a high-level, broad brush of how the product is produced. We provide those layers in the product so you can repeat the computations yourself as the user. JPL has done quite a bit of work on the validation of this product, showing quite good skill in terms of comparison over land and water. We tend to see higher performance over water, which is what we would expect to be seeing, because that's what we're calibrating to, and the nature of emissivity is very sort of smooth over that particular target. But if you move over to land, the accuracies are a little more uncertain, with sort of an accuracy of about 1/2 Kelvin, and then the precision around 1 degree. And so this is sort of our baseline. This is what we want to improve on in the future to get those numbers down even more accurate. We are working on a communication that summarizes this, and sort of I'm very excited to see so much work out on the posters and being talked about in terms of folks using the Landsat products, and it's good for us to hear and see what's happening there. In terms of where we're headed into the future, we definitely want to improve the sources of emissivity with the potential use of other sources along with EcoStress to fill in some of the gaps that are cloudy on the globe as a result of limited observational capacity with the ASTER static data record. We're looking at moving to the RT-TOV radiative transfer, which is shown to do operational processing more efficiently and produce the same outcomes. We're looking at developing potentially a product offer that gets better latency on the product, as well as producing data over polar regions, which we're currently not doing right now, but we are observing the polar regions in a fairly high-frequency way. And then finally, we're going to be starting to think about Landsat Next inclusion into the next collection as we prepare for that coming into the future. So just as a disclaimer, there's a lot of information. You can learn a lot more from NASA if you go to NASA portals and type in Landsat Next. I'm just going to provide just a really quick glimpse of what's coming as specifically as it pertains to thermal infrared. It's proposed to be a VSWIR TR constellation of 3 observatories flying at 653 and with a launch readiness date sometime in the late 2030s. This is basically improved spectral sampling in the VSWIR, as well as the thermal, improved temporal revisit with a 3 observatory constellation, improved spatial resolution to 60 meters for the thermal infrared. And then finally, this facilitates synergy with the current generation and next generation Sentinel-2 systems. And so this is sort of kind of what we're carrying out. This is going to be kind of a new era for Landsat. Specifically, we're following the Heritage ASTER responses, adding these new channels to retrieve emissivity. That's probably the biggest challenge we have right now. It's actually not having that instantaneous retrieval of emissivity, but hopefully that is coming in the future, and it's going to enable a range of new applications which have already been demonstrated in the literature over and over and over. Finally, just to finish off, we are planning to continue to produce a level 2 surface temperature product. We will then be adding level 2 surface emissivity to that product. We're going to be leveraging these new bands to produce much more high-quality information on emissivity. We're going to work on adopting the TESS approach, figure out how this broader algorithmic landscape fits together in terms of these observations, and so that we'll be ready to go in the next decade with a new collection and improved observations, and that's all I have. Thank you.
Thank you very much. And our last speaker of the session is Simon, the man who doesn't need introduction.
Thank you. So let's see if we can get a slide up here. Okay, so today or now, I'm actually going to talk to you about something that really hasn't been spoken about today, which is emissivity. So far, everything's been temperature, temperature, temperature. But in addition to the temperature, we get the emissivity, and the emissivity is incredibly useful in certain applications. And I'm going to talk about that today. And so this talk is about simulating SPG with EcoStress and EMIT. And as was mentioned earlier, SPG is in fact 2 instruments, a visible shortwave infrared imager and the thermal infrared instrument. and I'm going to talk about using those in applications, and I'm going to focus more on the emissivity side of the thermal infrared than on the temperature side. So first of all, I'll say a little bit about SPG and then EcoStress and EMIT, and I'll try and go over those fairly quickly because we've heard a lot about them. And then I'll show those same comparison tables, but this time I'm going to add in a comparison table of the VSWR, the SPG VSWR with CHIME and also with Prisma Next Generation, which are the sort of equivalents in the visible shortwave infrared. And then we'll look at using the EcoStress and EMIT products and their processing, and in particular for geological studies. So when we talk about SPG, there are two different platforms. We deliberately went for two different platforms because we wanted to have different overpass times. 1030 is better time for the visible shortwave infrared, primarily related to the clouds. The 1230 is better for the thermal infrared, specifically to look at stressing plants. So we have this two platform solution in SPG, and then within the TIR there are actually two instruments. There's the thermal infrared instrument, which JPL is providing, and then there's the visible near infrared instrument that ASI is providing. So it's this two instrument solution, if you like, within SPG TIR. And this just shows you a little bit of the specifications there. A couple of things to notice, as I mentioned this morning, is down there's a line that says VNIR, SWI, MWIR, and we have the two visible near-infrared bands from the ASI instrument. We have the two mid-infrared bands from the SPG TIR instrument, and then we have the 6 TIR bands, and that's in there as well. Any delta T less than about 0.2, and the accuracy about half a Kelvin. And then this next slide shows the visible shortwave infrared, and on the visible shortwave infrared, a key difference there is the revisit. On the visible shortwave infrared, the revisit is typically going to be less than 16 days, and that's because it's got a narrower swath. And this is sort of inherently related to the design of the instruments. We have the whisk-push design with the thermal infrared instruments versus a push-broom design. And with a push-broom design, you will typically get a much narrower swath. And you can obviously see that with the CubeSats as well, which often have that push-broom design. Now, obviously, we want to have very good performance. And so with the visible shortwave infrared, we have an imaging spectrometer operating from 0.4 to 2.5 microns with about 10 nanometer sampling. And so a very high performance instrument. So I probably shouldn't say very much about EcoStress because I've said this one already, but basically it's a 5-band thermal infrared radiometer, and we do the retrievals at about 70 meters by 70 meters. This just shows you a little bit more about the optics. It's this whisk-push design as opposed to a push-broom design, which we have with, on the VSWR side. So this just shows you the characteristics of EMIT with the push-broom design, and you can see that one of the differences is that with the SPG VSWR we'll have 30-meter resolution, but with the current EMIT VSWR we have 60-meter resolution. But apart from those two differences and the somewhat larger swath, it's essentially the same instrument. And then this is the characteristics of the telescope. It's a Dyson spectrometer, and for those of you who have been looking at HITEST and saying, how did they manage to get 256 bands there? It's because it's a Dyson spectrometer, it's a push-broom instrument, it has a narrower swath. That's what gets you more signal, but at the expense of that swath. So this slide just gives you that summary that I showed before. You'll notice that I only remembered to fix the slide this morning, which had the overpass time. This has the old Tichenor overpass time, so I have to remember to fix this particular slide as well. And then this is the equivalent information for the vSWR, and in here I have also added in QIIME and also Prisma Next Generation. But the key thing to notice really is that it's a less frequent revisit, many more spectral bands with the visible shortwave infrared compared to the thermal infrared. So what I want to do now is spend a little bit more time talking about the eco-stress processing flow, and then I'll talk a little bit about the emit processing flow, and then I'll give you some examples. So the eco-stress processing flow is sort of shown in terms of images here as opposed to the usual flow maps. And you can basically see that we produce the radiance at sensor. From that, we get the surface temperature and emissivity. From that, we get the evapotranspiration, and we use different methods to get that, but we have to have quite a few inputs in order to get the ET. And one of the things that we will keep pushing for is to make sure that you get those inputs with the data products, because it's no good if you don't have those inputs. And this was something that the Decadal survey called out as well. And then we have the highest level products, which really relate to how much crop you get for the amount of water that you use. This just shows you the processing flow for SPG. We will be using the visible near infrared to get at the NDVI, and then we'll be getting the albedo information elsewhere, and we'll use it to produce these high-level products. Now, one of the things that has been great about eco-stress, we have been able to develop error budgets, and we do intend to have error budgets with the, all the products that we're going to produce with SPG, and this is just the error budget for the LST product and for the ET product. As a general rule of thumb, you know, error budgets, it's typically around 1K for temperature, and for ET, it's typically around 1 millimeter per day. So that's a sort of easy way to remember it. So what I want to do now is just show the emit processing flow. So emit processing flow, very similar. We take the radiance at sensor. We then use the ISOFIT method to correct it to the surface reflectance. And then instead of producing these ecosystem-related products, they specifically produce maps of different minerals. And they do that because the goals of the mission are to look at mineral dust or dust, minerals in dust, and see how those, that dust is transported and what effect it has on the surface of the Earth, sort of from a fertilization point of view, but also from an opacity and in other areas as well. And this is just an example with EMIT, where they have where you see some data where you've got the model data and then you've got the actual retrieval. As you can see, the instrument is working really well. And then this is some examples of different minerals that can be identified using the EMIT data. And I should say, I realize it's very confusing that the emissivity part, when we're talking about LST, and then emit when we're talking about the visible shortwave infrared. So please take that into account. Anyway, when you look at these data from emit, you can see that you can recover a variety of different minerals on the surface of the Earth. And the minerals here are shown kaolinite, calcite, goethite, and hematite. Now, hematite, of course, is an iron oxide, and goethite is also an iron oxide. And they are characterized by having absorption features somewhere between about 0.7 and 1 micron. So if you look at these spectra, you can see those absorption features in those shorter wavelength regions. Now, in the longer wavelength regions, where you've got the calcite, the kaolinite, and other minerals, these are actually associated with a hydroxyl molecule in the material at the surface, and you will get these different absorption features, and these different absorption features are unique, and so we can use those to identify what the mineralogy of the surface is. Now, what's interesting there is that you can see the iron oxides and the clays. What you don't see is the fundamental rock-forming minerals, things like albite, things like the feldspars, albite, anorthosite, and so on, quartz and what have you. And that, of course, is what we actually get from the thermal infrared. So what I'm going to do now is go into just using those two data sets together for geological studies. Now, before I do that, I did want to just mention, as we said earlier, we have moved one of the bands into the thermal infrared. By moving it into the thermal infrared, compared with EcoStress, it's a big advantage in telling apart these different feldspars as well as looking at sulfates. And so this just shows you the position of the bands from SPG with different minerals superimposed. Now, these are all the rock-forming minerals. So these are the silicate minerals which you don't see in the visible shortwave infrared. And so by combining these two data sets together, we can do a much better job for surface composition mapping. And of course, the data are also useful for looking at volcanoes and volcanic ash, and this is just an example of that, looking at SO2 and ash in the plume, which you can also see in the long wave, which is more difficult to see in the visible shortwave. So what we end up with is this interesting pie chart, where if you look at this, you can see that on the VSWR side, they can map a whole bunch of different minerals. And on the TIR side, we can map a whole bunch of different minerals, which are complementary. And then, obviously, when we combine those two data sets, we can map all the main types of rocks, sedimentary rocks, igneous rocks, and metamorphic rocks. And that's obviously what we want to do with this emissivity information. We want to be able to map the surface composition. Now, one of the things that we can also do is map the weight percent silica. This is a very important measurement for geologists. And this is some work that we actually did with master data a long time ago. I shan't mention the date. But the long and short of it is there's an absorption feature. And when you look at that absorption feature, as the amount of silica in the rock changes, that absorption feature moves to shorter wavelengths, and we can map the amount of movement and we can relate it to the amount of silica in the rock. And we've done that just here in this particular study, and we did this with master data, and then we've also done it with test data, high test data, and we're also doing it with EcoStress data now, and this is all of that same area. And so this is just a weight percent silica map. So you can use that emissivity information for all sorts of things besides seeing it as noise on your temperature measurement. And then this just has the final spectral band positions. And so now let's look at some examples with EMIT. So the first thing that they do is obviously geolocate the data, and then they produce these products where they show different abundances of those different minerals that I showed. Now, in the case of EMIT, it's a standard product to get all of those minerals. In the case of EcoStress, it's additional work because we're really designed to get those ecosystem products, not designed to get those geological products. With EMIT, of course, it's the other way around. So here you can see the calcite spectral abundance that can be calculated and the relative soil fraction. And then we can get these iron oxides, goethite, which is shown here, hematite, the other main iron oxide. So for the same area, we can map those different mineralogies. And then these are the other minerals that have the features in 2 microns. These are the clay minerals. So we get the clay minerals with the 2 to 2.5 micron region of the VSWR instrument. And then this is just a nice map of those different minerals. And we're doing this now with EMIT. So this is all relatively new work that's these products have just been released really pretty much since Christmas. So really, the EMIT team is doing really well there. Now, obviously, on the thermal infrared side, we can get other things. We can look at volcanoes as well, as I mentioned. We can map the amount of SO2 in the plume, which is just shown here as an example. We can map also the amount of sulfate that's in the plume. And we can do that because of this extra band that we moved over. Well, we will be able to do that with SPG. Another example with volcanic ash. So to summarize, SPG is a visible shortwave infrared imager and a thermal infrared multispectral imager. Now, there are several areas where having the combination of both instruments allows us to do something that we couldn't otherwise do. And this is one of those areas. Ralph today mentioned looking at snow particle size. The other area mentioned was surface composition. And this is us actually trying to do that with EcoStress and EMIT. And we plan on doing more studies to just see how well that works, develop all the necessary algorithms that we're going to need for when SPG comes along. So they can be, EMIT and EcoStress are great precursors for both of these. And in the meantime, we can use airborne instruments to simulate it. And I will stop there. So you can all go and have a drink. But I should just want to finish that by saying there were a lot of other people who participated in this study who gave me data, particularly on the EMIT side, as well as, of course, all the EcoStress team. So a big shout out to all of them too. So thank you.
So before we open the time for questions, we have been requested by two ladies, Jennifer Susan Adams and Agnieszka Sosinska. They come for the Thermal Remote Sensing Special Interest Group. They are here to present a couple of slides with a special announcement they want to make, so please.
Hello. So this is Jennifer Susan Adams. I am Agnieszka Sosinska. I'll be short, we promise. So today we've heard a lot of very interesting presentations, and one of the words that we have kept hearing was discuss, collaboration. And this is exactly what we thought we need to do. So very recently we have revived the Special Interest Group of Thermal Remote Sensing. And basically our purpose is to bring all those possible actors together. Let's discuss and let's collaborate. And we would like to invite you to do that with us.
So we have a few ideas already how we can do this, and you can see a couple of examples on the screen. One of the most important things we want to think of is a communication platform for all of our users that we can really discuss things all the way from algorithm development all the way through to applications. We want to also organize workshops and seminars and try to stimulate the communication and exchange between all of these different actors. If you would like to sign up to the special interest group, you can use the top QR code there. And on the bottom, we have a user requirements form, which is basically for us to understand what you need, because we're really here for the community and to try to basically help this discussion and exchange and collaboration. And for those of you at the back that can't see us, here is a picture of us just from today, and we should look fairly similar. So yeah, thank you very much.
So thank you very much. And now, yes, please, I welcome all the speakers to come in the front and answer the questions that the audience may have. Is there any question? No question?
Sorry. I have one for Jean-Louis. Is he here? Yeah. I can't see from here. Okay. It's to do with the emissivity characterization in your presentation. You mentioned that it was done in a laboratory of Fera, I believe. What I was wondering was a couple of papers a few years ago by Mary Langsdale and her team suggested that there are significant uncertainties involved in laboratory-based emissivity characterization between measurements and between teams and so forth, and also, you know, differences between measurements out in the field and in the lab. What I was wondering was, in the error analysis that you'll do for your work, how will that be accounted for?
We did not measure emissivity in the field. It was just we pick up sample, and for vegetation it has to be in the white room necessarily, and for soil Jose Sobrino team that performed it. It was in a room also. You did not. It was also in a room. So I cannot answer for the difference you may observe between the field and in the lab, in vivo, in situ measurement for emissivity. I mean, for the different materials. If this is if you understood correctly the question.
Well, it's really more that by removing vegetation and soil and then transporting them to the lab. In the case of vegetation, it will immediately start drying unless it has adequate soil. And also, in the case of soil, any kind of vibration during transit will fundamentally change the grain structure and therefore the emissivity.
Yeah, okay. That's by the time I provided the samples to Jose, that was some several weeks after we get a chance to collect the samples. Yeah.
Okay, fair enough. Thank you.
So, Jose and Emily's presentation, you mentioned only the tests and the split window algorithm, and I'm wondering if you also considered the optimal estimation algorithm at all, and is there a reason why?
Yes, we do not consider that algorithm. We just focused on tests because it was classically used, and we try to develop direct tests for now. And so.
Okay, but there's not a reason why you would disqualify it?
No, no reason. It's a question of timing. And
okay.
Also a question on the tests and the direct tests. When you were comparing them to the eco-stress data, because the atmospheric correction, did you use the same data and methodology to do the atmospheric correction? Otherwise, how would you account for the bias there? Because if they have the same, I assume they will naturally do better than the split window, which has to do the atmospheric correction separately.
Yeah. You mean the same atmospheric correction for tests and direct tests?
No, but you're comparing it to the eco-stress data, which also has to do atmospheric correction separately. Do you know if the methods were the same? Did they use the same data?
The algorithm to do the atmospheric correction was iterative in the two cases, but the meteorological data were not the same because they were not taken from the same place.
No more questions? Then I think we conclude even 5 minutes ahead time. So I would like to thank all the speakers very much to stick to their time. Has been a long day, very interesting. Thank you very much for all the presentations. And now there is an ice-breaking drink together with the poster sessions. So please, it will be in the tent. So Please, we welcome to visit the poster session and keep talking to each other.